Hello and welcome to this introduction video about recurrent neural networks. So we're not only going to discuss recurrent neural networks, or RNNs for short, we're also going to discuss a variant of RNNs, which is basically called long short-term memory, or LSTMs for short. So let's start. First of all, why do we need RNNs? What's the real secret behind RNNs? So basically, RNNs, they're used for time series analysis. When we want to make predictions based on previous data, not only the current data, then we need to use RNNs. So basically, they make use of sequential information. So another way to think about RNNs is that they have memory. Okay, so they record memory on what happened previously. They capture this memory and they make the prediction based on this memory. So let me give you two examples of when we're using RNNs. So stock price prediction, right? So when we want to predict the stock price, we can't just look at the current input. So for example, the current input might be the previous day. So in order to predict the stock price, we can't just look at the previous day to predict it, okay? We need to look at previous months or sometimes previous years, okay? So they're all sequential information, and you're going to need to analyze all of them in order to make the prediction, okay? So you're not only relying on one input, the current input, which is, for example, the previous day, okay? Or for example, let's say the previous week, okay? You can't make stock prediction based on this input only. You need to remember what happened previously. You need to analyze what happened previously, and based on this previous information, this previous sequential information, then we only make a prediction. So another example is text generation, okay? Let's say we want to predict the word her, okay? So we have the sentence, she spoke to her husband, and we want to predict the word her. This is our objective. Our objective is to predict the next word based on the given current word. So we're going to give the network the word to, and we wanted to predict her. But realize that if you only rely on the previous word, which is to, then you won't get this word correct. You won't get this prediction correct. Why? Because her is dependent on she, right? Since this is a female, okay, then this network will learn that after to should probably be her. So the network needs to remember, it needs to have memory on what happened previously. Okay, so you need to analyze the previous words in order to predict this word. Okay, so that's where you use RNNs. Now, another way to think about RNNs is memory. So I said this before. So RNNs are basically memory networks, and they capture information about what has been calculated so far. So at the end of this video, we're actually going to walk through a practical example. Okay, so we're going to walk through a step-by-step example, and you'll get a more clear understanding of what RNNs really do. All right. So let's jump to the next slide and see what RNNs really are. Okay. So RNNs are just multiple copies of the same network. Okay, so you repeat the same network several times. Now, each time you repeat this network, then this network receives a different input and the previous hidden state. So this whole thing is a neural network with these input neurons and these hidden neurons. Now, the output of the hidden neurons are passed to the next neural network. So this next neural network receives the outputs of the previous hidden neurons and the next input. Okay, so these whole things are called time steps. Now, time steps are how many times you copy this network, and this might depend on your problem. For example, here, if we're using this sentence in an LSTM or an RNN, she spoke to her husband, then you're going to need 5 time steps. In other words, you're going to need to copy the network 5 times. She spoke to her husband. Okay? Each one receives this input. So she spoke to her husband. Okay? And it passes the hidden state, or the output of the hidden neurons, to the next neural network. So no worries if you still don't understand what's really happening here. Okay, there's still a lot of diagrams coming, a lot of visualization coming, and hopefully you'll have a better understanding after we go through them. Okay, but here I'm just introducing you to the general concept only. Okay, so let's see the relationship between RNNs and normal neural networks, normal feed-forward neural networks. So you have this neural network over here. Okay, it's a very simple neural network. You have an input layer, a hidden layer, and an output layer. Okay, so here you have 4 input neurons, here you have 3 hidden neurons, and you have 2 output neurons. So this is just a very simple neural network with fully connected layers. Okay, 3 layers only. Input layer, hidden layer, output layer. Now, what we're going to do is we're going to take this neural network and we're going to flip it. Okay, so take this whole thing. This is just for visualization of an RNN. Okay, this is what I want you to get. I want you to visualize the normal neural network and the recurrent neural network, the relationship. So if you take this and you flip it, then this is what you get, right? Now, what we're going to do is we're going to pack this whole thing up. Okay, so we're going to represent it as a multi-dimension. So let's go ahead and pack this whole thing up. This is what we get. So we have 4 dimensions. Okay, here we have 3 dimensions, here we have 2 dimensions. So what we did is we just packed this whole thing up. Now, what we're going to do is we're just going to represent the multi-dimension neurons as one neuron. Alright, this is just for visualization purposes. So, this is what we get. So this thing over here is a multi-dimension. Alright, remember it has 4 neurons, but we just represented it as one neuron. Why I'm doing this is because later on you're going to see the representation of RNNs as this shape over here. But you shouldn't be confused and think that this is only one neuron. Actually, this is a multi-dimension. You have here 4 neurons, and here you have 3 neurons, and here you have 2 neurons. Okay, so then what we're going to do is we're going to take this RNN over here, which is basically a neural network, okay, which is this neural network, and we're going to copy it for how many time steps do we want. So for example, if we're going to use 5 time steps, then we're going to copy it for 5 times. Okay, so this is what we get. The same network copied for 5 times, and each time is called a time step. So at each time it receives a different input and the previous hidden state. So each one of these is just a neural network, which is this neural network over here. Alright? So it's just a multiple copy of this neural network. So each one of these receives a different input at every time step, as well as the previous hidden state. So for example, this neural network receives this input over here, and the hidden state for the previous neural network. Okay? This one receives this different input and the hidden state for the previous time step. Okay? And so on. So what you're doing is you're passing information from one neural network to another. Or, in other words, from one time step to another. So if we go into depth of this visualization, this is what we have. So this is your first neural network, but here previously we have 5 time steps, but here we only have 3 time steps. Okay, so you have this neural network. These are the hidden units, the RNN hidden units, okay, which are basically the hidden neurons here. So you have this input, okay, and then you pass it through your hidden layer, and the output of this hidden layer gets passed to the next neural network or the next time step. So this neural network receives this previous hidden state and this new input, and so on. Alright, so this whole thing is the same neural network, it just receives different inputs at different times, plus its previous hidden state. So another way to think about it is just a neural network that passes the hidden state information back to itself. Okay, which is what's represented here. So you're processing this hidden state. Okay, you're passing the information to the hidden state, and this output of the hidden state is getting passed back to the neural network. So it's just passing information back to itself. And this is what's happening here. And each time the information is passed back to itself, then you have a new time step. So this is what's really happening here. I hope you got it by now. So now let's talk about the activation functions that are used in RNNs. Okay? So the first activation function that comes in mind is the sigmoid. Okay? We're going to talk about the sigmoid, and then the ReLU, and then finally the leaky ReLU, and then we're going to see all of the problems that they have, and then we're going to see why we need to use LSTMs to overcome this problem. So let's start with the sigmoid function. So first of all, remember why we need activation functions is to introduce non-linearity. Okay? If we don't use activations, then our output will just be linear, since we're just applying a linear transformation. Okay? So let's recap what this sigmoid function does. Okay? So what it does is that it transforms your linear output to a value between 0 and 1. Okay? So you give it a value, okay, whatever is your linear output here, x, and it transforms this value to a value between 0 and 1. So let's say you give it, for example, 0, it's going to transform it to 0.5. Let's say you give it 2, it will transform it somewhere around 0.8. Okay, if you give it 4, it will transform it to somewhere around 0.99. Okay. So if you, for example, if you give it -2, it will transform it to somewhere around negative 0.2 or 0.19, I guess. So you get the idea, right? You give it an input, and it transforms that input value to another value that has the scale from 0 to 1. Okay, it has the range 0 to 1. So any input that's passed through a sigmoid function will have a value between 0 and 1. Now, let's take the derivative of the sigmoid. So this is the derivative of the sigmoids. Okay, if you take the sigmoid activation function, which is 1 over 1 plus e to the power of -x, and you derive this function, then this is what you get. This is the graph that you get. And now let's realize what's happening here. The output that we're getting is, the output here are very small values. Actually, the maximum here is around 0.2. Okay? Now remember, the back propagation is composed of the chain rule, right? And one term of this chain rule is the derivative of the sigmoid. Okay? So now if this derivative, if we like take the worst case outputs a value of 0.2. Now imagine here we're doing an RNN, right? So we're copying the network multiple times. So when we're back propagating, okay, and this is called back propagation through time, okay, or BPTT, back propagation through time. So when we have very deep networks, okay, like practically when we have very deep networks, then we're going to multiply this value, this very small value that we get from the derivation of the sigmoid function, we're going to multiply these values all over again. Okay, so let's say for the sake of an example, we have 4 layers of 0.2 value derivatives. So basically what we're going to do is we're going to have 0.2 to the power of 4. Okay, and you can imagine how that already vanishes, that already goes to 0. So that, if I'm not mistaken, gives you an output of 0.0016. Okay, and this is only to the power of 4. So imagine when we have very, very deep layers, okay, or very, very deep architectures. Okay, so what's going to happen is that these gradients are going to die. They're going to end up being 0 because they're getting multiplied with, getting multiplied continuously with small values. So at the end, you'll end up with the gradient vanishing, and that's what's called the vanishing gradient problem. Okay, and if we visualize the vanishing gradient problem, then this is what we have. So you'd end up with the first layers of the neural network having their gradients vanish. Okay, so therefore they're not able to learn anymore because they have zero weights. So basically you cannot learn anything. That's what's called the vanishing gradient problem. But actually we need to ask ourselves, why do we need to care about these first layers? Like, are they important? And the answer is, of course they are important. So basically, now the first layers of a neural network, for example, let's take a convolutional neural network, a CNN. Now the first layers of a CNN are responsible for detecting low-level features, right? So for example, low-level features can be edges, lines, or anything that's the fundamental for high-level features. Okay, so the high-level features are the shapes or the things that we can realize. But all of these high-level features that are usually detected at the end of the network are built upon the low-level features. Okay, so these are the prerequisites for the high-level features. So if we end up detecting these wrongly, then actually we're going to end up classifying the image wrongly also. Okay, so let's take this for example. If we're classifying this image, which is of course a cat, but we actually did some mistakes in the low-level features, so we didn't detect these low-level features correctly. So for example, there's a problem in detecting the edges. So what you'd end up is classifying this as a mouse. So this is what the CNN will understand if you detected the edges wrongly. So you'd end up classifying this image as a mouse and not a cat. So that's why these layers are very important. And if gradients vanish from these layers, then of course would be in big trouble. So that's what the vanishing gradient is in RNNs. So what's the solution? So here we use the sigmoid function. So maybe one thing that comes to your mind is, let's change the activation function. Okay, so for example, let's change it to relu. So remember, our objective is to get rid of this vanishing gradient problem. We don't want the gradients to disappear over long sequences. So if we change the activation to relu, for example, then this would work if we didn't have negative inputs. Okay, now if you take the relu, okay, and you derive it, so this is the derivation of relu. It's very simple. It's when you have positive inputs, then you get a derivation of 1 because it's simply x. Okay, so the derivative of x is 1. That's why you have 1 here. And when it's 0, then it remains 0. Okay, the derivative of 0 is just 0. So meaning when you get negative inputs, then you have 0. Okay, so whatever negative inputs you have in this long sequence will end up being 0, right? So you're going to basically end up multiplying 0 with the other values. So the backpropagated error can be cancelled out whenever there's a negative input into a given neuron, right? So your gradient, okay, will basically disappear in this case. And you'd still end up with the vanishing gradient problem. And now one mitigation of relu that was proposed is leaky relu. Okay, so leaky relu doesn't give you a value of 0 when you have negative inputs. As you can see, this is not 0. However, it's close to 0. So the equation of this line is just 0.01 times x. Meaning you multiply the input that you have with 0.01, and then you get a number that is very close to 0 but not 0. Okay, now this is good, but doesn't really solve the problem, because remember we're gonna multiply this very small number over a long sequence. Okay, so eventually the numbers will get smaller and smaller, so this doesn't really solve the problem. Now what really solved the problem are long short-term memories. Now they were proposed in 1997, as I recall. So they're pretty old, actually. They are old. Okay, so they really solved the problem by introducing the memory pipeline. So let's go ahead and look at LSTMs. So this is what an LSTM is. All right, this is one LSTM cell. Now, before I go into the details of how an LSTM works, please remember that this is only one neuron. Okay, one unit, one cell only. If we go back here to this diagram, then this is our neural network. And as you can see, the hidden neurons here are 4. Okay, so we have 4 hidden neurons in the first time step. So basically, we have 4 LSTM cells in each time step. Okay, in each time step, we have 4. So each neuron of these is basically this LSTM cell. Okay, so let's go into the details of how an LSTM works. First of all, we have some gates. Okay, now these gates basically control the memory and the output. So let's see those gates in detail. First of all, what we do is we calculate a gate which is called the forget gate. So F stands for forget. Now this gate is responsible to how much to keep from the old memory. Alright? So this gate is a sigmoid. It has an activation of a sigmoid function. Remember, the sigmoid function outputs a value between 0 and 1. Okay, so you construct this gate based on your input and the previous hidden state. So this is our input and this is our previous hidden state. We concatenate them together, as you can see. This is a concatenation over here. So we concatenate these two and then we run them through a linear layer. So after we concatenated the two inputs, we run them through a linear layer. Now the output of this linear layer is your hidden size, or how many LSTM units you have, which is basically the number of hidden neurons. So here, for example, we have 4. Okay? So you're just taking the dot product between the weights and the inputs and you're adding a bias. Okay? Just a normal linear function. Now the output of this linear layer, okay, the output of this, which is of shape hidden size, enters through a sigmoid activation function. Okay? Now this sigmoid activation function outputs a value between 0 and 1. Okay? Now let's see what this output means. So 0 means forget all the previous memory. And 1 means keep all the previous memory. Now value between 1 and 0, which is for example 0.5, means keep some of the previous memory. So this gate is basically to control how much we want to keep from the old memory. So this is your old memory over here. Okay, and as I told you, LSTMs, the key concept of LSTMs is that they have this memory pipeline that goes through all your time steps. Okay, so this carries the memory. So here we're controlling of how much we want to keep from this old memory. Okay, let's go to the next gate. The next gate is basically how much to add to the new memory. Okay, which is called the input gate. So it's the same thing. We take the current time step inputs and the previous hidden states. Okay, we concatenate them both together and run them through a linear layer. And then the output of this linear layer is entered to a sigmoid activation function. So again, the sigmoid activation function outputs a value between 0 and 1. Now, a value of 0 implies that we don't add anything from what we're going to receive. A value of 1 implies adds all of what we're going to receive, and a value between 0 and 1 implies that we want to add partially of what we're going to receive. So what we're going to receive is basically, we're going to see it in the next slide, which is the new memory. Okay, here we're going to construct the new memory. Now, this gate controls how much we want to add from this new memory that we're going to construct. Okay, so let's go ahead and see this new memory, which is basically here. So this is responsible for generating the new memory. So how it's done is the same concept. You take now we have a third linear layer. Okay, so before we continue, please remember that each one of these is a different layer. They have different weights to learn. They're not the same layers. Okay, so this layer, we take the inputs and the previous hidden state, concatenate them together, and run them through a linear layer. Okay, again, this is a different linear layer from the the previous ones, which is this and this. Now the output of this is run through a tanh activation function. Okay, so we run the output of this layer through a tanh activation function. So this receives the new memory based on the current time step input and the previous hidden state, which is xt and ht minus 1. So okay, so we receive the new memory based on these two inputs, and we run it through a tanh activation function. Now this is the new memory that will be controlled based on the previous gates it we constructed over here. So this is where our new memory will be constructed. Now after we construct this new memory, we multiply it with the gates we discussed previously, which basically controls how much to add to the new memory. Or in other words, we're just controlling the memory. So how much memory do we want? How much new memory do we want? So again, I repeat, this is the layer that's responsible for generating the new memory. Okay, and this is the gate that's responsible of how much to take from this new memory that we generated over here. Okay? Okay, now we're going to basically construct our new memory. So the construction of the new memory is basically the old memory plus the new memory. But remember, we need to multiply them with the gates. So here we generated a gate basically of how much to keep from the old memory. So we're going to multiply this gate with the old memory. So ct minus 1 times this gate, which is ft. Okay, and this is the first term we have. And now the new memory, we also controlled how much we want from the new memory by this gate it. So we multiply it by the new memory we generated, which is ct tilde. All right. So basically now we're constructing our new memory. So this is the new memory that we have. Now finally we need to construct the outputs of this LSTM time step. Now the output is just a representation of this memory. Okay, so what we do is we take this memory, okay, and run it through a tanh activation function. But we also need to control this output. So let me go to the next slide to show you the construction of this output, which is basically here. Okay, so you take, this is just your memory, and we run this memory through a tanh activation function because we want to construct our output that is basically based on the memory. Okay, so our output is constructed based on the memory, which is this memory cell CT, memory state, sorry. So this output is based on the memory state. So we just take this memory state and run it through a tanh activation function to generate this new hidden state. But we also need to control how much we want to output. So this is the gate where we basically control how much we want to output, and it's constructed the same thing. Okay, it's a different layer though. Please remember that it's a different layer. It has different weights to learn. So it's the same thing. You take the current time step and the previous hidden state, you run it through a linear layer, and then you run it through a sigmoid activation function. This outputs a value between 0 and 1, and again 0 implies don't output anything from the new memory, and a 1 implies output everything from the new memory, and a 0.5 implies output some of your new memory. Okay, so this is the gate where we control the output of the LSTM. So one LSTM variant is passing the memory, the previous memory, to the gate. So the gate decides upon the current input, the previous hidden state, and the previous memory. Okay, so previously here we weren't passing the memory through these gates, but here one variant is to just pass the previous memory to the gates. So each of the gates look at the current input, the previous output, and the previous memory. Okay, and this last gate looks at the new constructed memory. So this is how it's mathematically represented. Okay, instead of just having xt and ht minus 1, we have ct minus 1, ht minus 1, and xt. Okay, except for the last one, we have the newly constructed memory and the previous hidden state and the current input. So basically we let the gate layers look at the cell state. That is one variant. Now another variant is to use coupled forget and input gates. That means we only forget when we're going to input something in its place. Alright, so if you realize the formula here, we get to decide the ft output, which is the sigmoid activation of this linear layer. So this outputs a value between 0 and 1, and then we just take the opposite, so 1 minus this value, and we multiply it with the newly constructed memory. So we only forget when we're going to input something in its place. And we only input new values to the state when we forget something older. So what they did here is they got rid of this gate. If you realize that there is a gate here, okay, that decides how much to output, how much to add to the new memory. So I went back to the slide over here. How much to add to the new memory. So what they did here is they got rid of this gate. Okay, so if we go back to the this LSTM variant, they got rid of this gate over here. As you can see, there's no gate, and instead what they did is they just did the opposite of this gate. They took this gate, they took the value, and they took the opposite of it. So this value outputs, this gate outputs a value between 0 and 1. Okay, and by taking 1 minus this value, then you just get the opposite, and this is how you decide. So let's say you want to forget the old memory. So basically the ft would be 0. Okay, 0 means that you want to forget the old memory because you're multiplying 0 with ct minus 1. So if you want to forget the old memory, then 1 minus 0 is 1 basically. So what you want to do is you want to add all of the new memory. So you want to forget all of the old memory, and you want to replace it with the new memory. If we take the opposite, let's say you just want to keep the old memory, so this value ft would be 1, and then 1 minus 1 would be 0, so that therefore you don't want to keep anything from the new memory. You don't want to take anything from the new memory, so you just remove this whole term over here, and you'd end up just remembering the old memory. So let's say you want to predict this sentence, I will swim today. So you're going to need 4 time steps, each time step for one word. Okay, so you feed in the first word to the first time step, which is the word I. So this first time step receives the current time step input, which is the word I, and the previous hidden states. Now the two previous states, which is the memory state and the hidden state, are initialized to 0 since this is the first time step. Okay, so you feed them through this layer, and then through this layer, then through this layer, and then finally through this layer, and you generate your output, which is the hidden states. Okay, the hidden state for the first time step. Now what's this hidden state? It's basically a representation for the outputs. It's a representation of the outputs. So for example, it may be a representation of the word will. Since here we want to predict the sentence, so we are feeding the first word and we want to predict the second word, which is will. So this second word is predicted through ht. So ht is the representation for the output of this LSTM. And since we're doing some prediction, so we want to predict the second word, then ht is basically a representation of the word will. So if you take this representation and pass it through a multi-layer perceptron to predict the vocabulary distribution, then you'd probably get the vocabulary for the word will. Okay, so ht is basically the output of the first time step, and it's a representation of the prediction, which is the word will in this case. Now, what's the CT? Is basically the memory cell, and it's a representation of what the LSTM knows so far about the sentence. So until now, we only know the words I will. Okay? So until now, here we only know the first two words, I and will. And remember, the output ht is done by activating the memory cell, which I told you what it knows about the sentence. So it knows I will until now, and when we activate this, we get will. We get the representation for the prediction, or the representation for the output of this time step. Now let's go to the second. This is the third word. Okay, so the second word is the same thing. I'm just saving time. So let's go to this word. So we feed this word swim, the previous hidden state and the previous cell state. Okay, and we feed them through this layer, and okay, we feed them through all the layers. I've skipped this in the slides, but basically it's the same thing. You just feed them through all the layers, and then finally you get again CT and HT. So CT is the memory state, okay, representation. So this is a representation of what the LSTM knows so far about the sentence. So right now it knows basically all of the sentence. Okay, so I will swim today. It's okay. So there's an encoding of the whole sentence inside this memory cell. So it has now encoded a representation of the complete sentence, and by activating this representation we get the output HT, which is basically the representation for the prediction, which is today. All right, so HT is basically a representation for the output. For example, it may be a representation of the word today, since we're doing a prediction for the next words. Alright, now we're going to start the topic of sequence-to-sequence models, or sometimes called seq-to-seq models. So basically, in a nutshell, sequence-to-sequence models allow you to encode and then decode information. Now we're going to see how it's done. Now, they're widely used in computer vision as well as natural language processing. Okay, so let's see the basic idea behind seq-to-seq models. So what happens is that you have an encoder and a decoder. So you have your input over here, and your input can be, for example, a sentence, an image, okay? And what happens, it goes through this encoder, which is later we're going to see, is a multiple RNN or LSTM or GRU cells. And what happens is that this network encodes your input. So it represents the inputs as a feature vector, or in other words, it represents your input as values, okay? And of course, these values are features that represent the image. So this information here is the encoded input. And then what happens is that we pass this feature vector, or the decoded, the encoded information of the image to the decoder. The decoder itself, as we're also going to see later on, is composed of multiple RNNs, and then this RNN will output the things that you desire. So let's say, for example, you're encoding an image, okay? So you encode that image. We're going to see later on, this is called image captioning. So you encode that image, and then this information here is a representation of an image in dense values, and then these dense values go into the decoder, and the decoder outputs, for example, a description of an image. Okay, so this is the basic idea behind seq-to-seq models. Again, I repeat, you have your input, it goes through the encoder, it encodes it or represents it as a feature vector, or just understand as a vector of values that represent the image, and this is what's called a feature vector. So then this feature vector goes into your decoder, and your decoder decodes that feature vector into the desired output. Now, one thing to notice is that the input and output length can be different. For example, if you're doing machine translation, then the input sentence, okay, let's say in English, can be different. The length of the input sentence can be of a different length than the output sentence. Now we're going to see an example of machine translation, and then that concept will be more obvious and clear. So let's see what this does. Machine translation. Okay, this is one of the most important applications of seq-to-seq models. As I told you, we have our encoder and our decoder. Okay, so what I meant by variable length inputs and outputs. So as you can see, we have this sentence, where do you come from? Okay, and the output sentence is just the translation of this sentence in German. Okay, so it's just German here. I chose German, but it can be, of course, any other language. This is just an example. So what we can realize is that you see this input sentence consists of 1, 2, 3, 4, 5 words, and the output sentence consists of only 3 words. So this is what I mean by the inputs and the outputs can be of different length. Okay, so they don't really care, the seq-to-seq models, they don't care about your inputs and outputs length. Okay, they just encode information and then they decode it, okay, to another representation. So we have this encoder that consists of 1, 2, 3, 4, 5 LSTMs, okay, long short-term memories. We discussed them in the previous intuition videos. And what happens is that you pass your input, which is in this case a sentence. So we're passing where do you come from. And now this state is nothing but the feature vector or the encoded representation of that sentence, which is where do you come from. Now, when you pass this encoded information to your decoder, then your output should be, in German, woher kommen Sie? Woher kommen Sie means where do you come from or where are you from? Okay, so the first LSTM of the decoder receives the states or the information or the feature vector or the encoded representation of the encoder, okay, as well as a start token. And then it generates this word, which is woher. And then this word comes to be the input of the next LSTM. And then the next now the next LSTM receives an input, which is the previous output. So our previous output is woher, and woher is coming here, okay, to the next LSTM. So this LSTM doesn't only receive this previous output, okay, it also receives the previous hidden state. So it actually receives two inputs: the previous hidden state as well as the input, which is in this case our previous output. And then generates the second word, which is common. And then this common goes down here. Okay, so this third LSTM receives common and this next hidden state, and it produces Z. Okay, so S in German is pronounced as Z. Okay, not always. In this case, it's Z. Just in case you're wondering. Okay, so this last word, which is Z, comes down here. Okay, and then finally, since the decoder is trained, okay, then it knows that this is the end, so it just outputs end. So whenever we output an end, we just stop decoding. This is how it's normally done. Okay, now this is done. This is important to note that this is done using test time, okay, or sampling, or inferencing, so whatever you want to call it. This is done only during test time. Now, during the training time, we need to prepare our labels, okay? So we need to prepare actually an extra, not only inputs and outputs, we need to prepare some extra things. So this extra is the encoder. So we need to prepare our labels for the encoder. In this case, it's where do you come from. We're going to see this also in the practical videos later on. And then finally, we need to prepare our decoder labels. In this case, we have an inputs and targets. So our inputs is start. This means start of the sentence, and then woher kommen Sie without an end token. And then our expected outputs or targets for this input is woher kommen Sie and then end. So if you want to visualize here, then you have start, and start should predict woher. Then when the input is woher, then our expected output is common. And when our input is common, then our expected output is Z. And finally, when our input is Z, then our expected output is end. So this is how we prepare the training data, and then during test data, this is what happens. Okay, now there's a special case which is called teacher forcing. This is actually teacher forcing. Okay, this is training during teacher forcing. Okay, I don't want you right now to worry about this thing. We'll talk about teacher forcing in detail while we're doing the practical while we're building the chatbot later on in the videos. So don't worry about this. Okay, so another example is a chatbot, which is actually what we're going to implement. So it's the same exact thing, but instead of having our decoder translate the input sentence, we have the decoder replying the input sentence. So our encoder this time is what do you work, and then the decoder replies, I am an engineer. Okay, so it's the same concept. It's just I'm just showing you that the different applications, and actually this is what we'll be doing later on. Alright, now we're going to talk about attention mechanisms. Now, I said to you in the previous video that attention mechanisms allow you to focus on specific parts of your inputs when generating the next word, okay, or the next prediction. So, for example, this is, okay, before I show you how attention works, I want to show you why we need attention. So maybe you can understand attention more by seeing the results of what attention does, and then we'll go back to how it works. Okay, so this is, for example, one of the results of attention that I got from this paper, which proposed attention, actually, neural machine translation by jointly learning to align and translate. So this is translating from an English sentence to a French sentence. Okay, so the English sentence is the agreement on the European Economic Area was signed in August 1992, and as you can see, this is the French translation. So my my French is not really good, but maybe I can read. I can read. Please correct me if I'm wrong. L'accord sur la zone économique européenne a été signé en août 1992. I'm not sure. Okay, so this is, for example, a translation. Okay, so now we're going to see how it did, how it was focusing on the input when generating the output. So the first word is de, and in order to predict le, okay, le in French means de. So it learned that you need to I need to focus on the, okay, in order to predict le. So when predicting le, it is focusing on the. As you can see, this is this gray pixel here is the weight, okay. So you see that this is focusing on the when predicting le. Same thing here. When predicting accord, then it's focusing on agreements. Accord in German, in French means agreement in English. So in order to predict accord, the model has learned to focus on agreement. Same thing here. Now, if we look at this word area, okay. So in order to predict area, then the model has learned to focus actually on this, which is zone, okay, la zone, because sorry, we're doing the opposite. In order to predict the word zone, okay, this is we're translating from English to French. So in order to predict the word zone, the model has learned to focus on two words, which is economic and area. So area has, as you can see, a higher weight. Okay, as you can see, this weight is higher in area. So it learned to focus more on area and less on economic. Okay, in order to predict the word zone. Now let's, for example, look at this one over here. So in order to predict août, okay, which is August, it learned, of course, that I should look at August. So this is why it's very white. It means that the weights are much more higher than these light gray ones. So it learned to focus on August in order to predict août. And then in order to predict 1992, same thing, it learned to focus on 1992. So as you can see, that is what attention means. Your model, in order to predict the French words, then your model is focusing on where to look at your input, which is the English sentence, in order to predict the French word or the French sentence. So I repeat again, in order to predict the word le, your model has focused on the. Accord, your model has focused on agreement, and so on. Okay, this is what attention mechanism is. Okay, so this is applied in machine translation. Of course, it will be applied. It has been applied in image captioning as well. Okay, research is very fast in computer vision. So this is some results of the attention mechanism applied to image captioning. And this is actually, I got this from the paper, which is Show, Attend, and Tell in 2015, neural image caption generator with visual attention. Okay, so it was published in ICML, which is the International Conference of Machine Learning. So let's see what some of the results here. You have this input image, and now when predicting the word stop, you see that the model focuses on this. The weights, the white things here are the weights. So as you can see that the model has focused on the stop, where the stop sign is in the image, in order to predict stop. Okay, same thing here, sign. For example, if we look at mountain, okay, so as you can see, the higher weights are for the mountain part. Wherever the mountain is, you have higher weights. A road, for example, if you see road, that so the road is here, okay, in this image, and as you can see, the model has learned to focus on this region when predicting the word road. So what's happening here is that the model is attending or focusing on where to look at the image in order to predict the word. Okay, and this is not the end of image captioning. There's still a lot of improvements that have improved this paper. Okay, but this is not the scope of this course. However, if you're interested in knowing more about image captioning and applying image captioning, maybe you can comment out in the Q&A, and then I'll try my best to add videos about image captioning and how you can apply image captioning in PyTorch. Alright, now we're going to talk about how attention mechanisms work. Now that you understand, now that you understood already why attention is needed, now we're going to see how it works. So as I said before, attention allows you to focus on specific parts of your input or your encoder in order to generate the next prediction. So this is the example that we have from the machine translation that we explained previously. So we have this sentence, which is what do you work? Okay, and this gets passed through an encoder. So in this case, the encoder is 1, 2, 3, 4 LSTMs. Okay, 4 time steps. Each time step receives a different word, and then what you do is you pass this encoded information to the LSTM, to the decoder. Then it generates the hidden state, and this hidden state gets represented as the word. Then you pass this word as your next input and generates the next hidden state. Now, this is what happens. This is what you need to do in attention. So, the first thing is that you take the outputs of the encoder. So, at each time step, okay, at each time step of your encoder, you take the output, and at the end, you have a combined encoder output. Now, what you do is you take this output of the encoder, okay, and you take the hidden state of the current decoder. Okay, so this is the decoder and this is the current time step. Okay, so this current time step has this hidden state. So we take this hidden state as well as the output of our encoder and we do some operation, and I'm going to call it the attention operation. And after I'm done explaining, I'll tell you what the attention operation is. It's something very simple, so you don't need to worry about this. So this operation can be a multiplication or a linear layer. We're going to see that later on. So this attention operation receives 2 inputs, which is your encoder output as well as the hidden state of your current hidden state of the decoder. And then this attention operation gives you an output. So you take this output as well as the output of the encoder and you multiply them together. Okay? Then after the multiplication, you get the result, which is the context vector. So again, we repeat, we take the outputs of the encoder, okay, then we pass them through an attention operation as well as the current hidden state of the decoder. We pass these 2 inputs to an attention operation. Then this attention, the result of this attention gets multiplied with your encoder outputs, and then this generates something called a context vector. Okay, and then this context vector that has been generated is passed as an additional input through to the LSTM, okay, or to the hidden state. So we're actually combining this context vector with the hidden state, and then this hidden state finally generates the word, which is am. So in order to generate that word, which is am, there's 2 inputs. With the hidden state, the original hidden state of the decoder, as well as the context vector, which is the result of the attention. So we combine these 2, okay? So now we have an additional input coming, okay? And then we combine these 2 and predict the word am. Okay, so same thing, okay? You pass this am to the next LSTM, and finally you get the description. So whenever you're predicting the word, okay, now of course this is repeated through all the time steps, okay, but I'm just lazy to repeat it again, so just keep in mind that this is done through all the time steps of your decoder. So whenever you're predicting the word, okay, you have not only your hidden state but also your context vector, okay. So you combine these 2, the hidden state and the context vector, and you predict the word, which is am. This is how attention mechanisms work. Okay, So now we're going to look at the attention operation. What is really happening in the attention operation? Now, there are several attention operations. I'm just going to talk about two, okay, and explain the basic intuitions behind them. Then you can understand the rest by your own. Now, one of them is an element-wise multiplication. So what you do is you multiply your two inputs. In this case, we have our encoder output as well as the hidden state, the current hidden state of the decoder. So what we do is we do an element-wise multiplication. We multiply the hidden state and the encoder output, and then this generates the results. So this is a multiplication, element-wise multiplication. And then after we've done an element-wise multiplication, we sum across all the hidden size, which is the hidden dimension. Okay. So this is one of the operations of attention. And then finally, we have another operation of attention that we'll be discussing, and it's a linear layer. So we take our encoder output, which is the input, the first input, and we pass it through a linear layer, and then this linear layer transforms your encoder output into another representation of different dimension, and you multiply this representation with your hidden state. So it's also an element-wise multiplication. However, we transform our encoder output into another representation before the element-wise multiplication with the hidden state, and then again sum across hidden. Okay, so these are two operations of attention we can see here, and there's a third one, but I'm not going to talk about it, and which is basically a concatenation, and then you pass it through a linear layer. Okay, so we're going to look at this in the implementation parts. Okay, but in the implementation part, we'll only implement. I'll show you the three, but we'll only implement the first one. Okay, so these are two results of attention. Sorry, these are two methods or two operations of attention you can do. So this is how attention mechanisms work, okay? And this is how these results are generated, okay? So these are the results of attention applied to image captioning, and here applied to machine translation. All right, now we're going to introduce you to PyTorch. Now, PyTorch is one of the deep learning frameworks. So nowadays, there's a lot of deep learning frameworks. For example, if you've heard of them, there's TensorFlow, Keras, Theano. There's a lot of deep learning frameworks used nowadays, and PyTorch is one of them. And PyTorch is actually one of the most powerful deep learning frameworks, and we're going to see why in a moment. Now, you can think of a deep learning framework as a library with ready classes and ready functions to use in order to build and structure and train your neural networks. Okay? So in this course, we'll be using PyTorch to implement our neural networks. And PyTorch is very simple to learn, and at the same time, it's very efficient. Okay? Now, also a lot of researchers in computer vision and machine learning use PyTorch to implement their research. Okay? So if the researchers release the codes on GitHub, most of the time they will be releasing the codes on GitHub. You can actually so if you want to take their implementation or refer to it for any other application, then you can do that easily. Okay? And also the community, the PyTorch community is big, and it's getting bigger and bigger as time moves on. And even if the author of the paper didn't originally implement his paper in PyTorch, then most of the time you'll find other people who implemented the paper in PyTorch. So PyTorch is developed by Facebook. Okay, so if we open the Wikipedia, then this is what we have. PyTorch is an open source machine learning library for Python based on Torch. Okay, now Torch is a GPU programming language that is based on the Lua programming language. So if you go to Torch, then this is the Torch website. So Torch is a scientific computing framework, and it's based on the Lua programming language, if you've heard of Lua. So PyTorch is just Torch implemented in Python. Okay, that's what PyTorch. That's why it has the name PyTorch, because it's Torch implemented in Python. Okay. Now it's developed by Facebook's AI group, and Uber's Pyro software for probabilistic programming is actually built on PyTorch. Okay. Now, PyTorch uses tensors for the computation. Now, if you think about a neural network, then it's just basically a matrix multiplication, right? You're just multiplying inputs with weights and so on. So these matrices, these multidimensional matrices, are called tensors, and basically these tensors can be implemented on a GPU. So you can do this computation on a GPU. Okay, and of course, if you run the computations on a GPU, then it's a lot faster than running the computations on a CPU. Okay, a GPU basically has much more cores than a CPU. Okay, and another thing, you can do parallel computation on a GPU, so you can process your data in batches. So if we look at the features of PyTorch, now I'm not going to read them. You can read them alone if you're interested. And actually, it's Python first, so it's built to be deeply integrated into Python, right? So that's something also very good. It provides also tools and libraries. So as you can see here, you can directly load some models, some CNN models like ResNet, AlexNet, SqueezeNet, BGG, DenseNet. You can already load a pre-trained model. As you can see here, it's pre-trained equals to true. We're gonna see this is one part we're gonna see later in the course in transfer learning. Okay, so we're gonna see how to implement and how to use these models, these pre-trained models. Yeah, so you can definitely read about the other features. There's a lot of other features you can use. Now let's go to the installation part. Oh, sorry, one more thing. Before we go to the implementation part, you need to understand something very important, and that's the key concept about PyTorch. PyTorch uses dynamic computation graphs. So I went to Google. I just Googled PyTorch dynamic graph because this graph is not available anymore in the PyTorch website. It was available previously, so I'm not sure why they removed it. But this is the concept of a dynamic computation graph. So in TensorFlow, okay, for example, in TensorFlow and other frameworks, they use static computation graphs, meaning that you need to define the graph first and then you can only run it. So you need to define your complete graph, your complete computation graph, and then you can only run the computation on that graph. But in PyTorch, you can actually create the graph on the fly. All right? So you're only defining the graph when you're running it. Okay? So as you can see here, when each line of code is being executed, then the graph is created. Now that's really helpful, especially when you're using RNNs, because when you're using variable length sequence, like in the case of RNNs, then this is very helpful, and we're gonna see why later in some of the applications in the course. Okay, you'll get more intuition about this thing. Okay, so before we go into the installation of PyTorch, you're going to need to download Anaconda. Now, Anaconda is a free and open source distribution of the Python and R programming languages. Okay, so basically what Anaconda did is they integrated a lot of packages. So packages, for example, like NumPy, Matplotlib, especially the data science packages, for example, like scikit-learn. If you know scikit-learn, it's a machine learning and data science package. So they integrated all of these packages and along with Python. Okay, so these packages along with Python. So rather than just separately installing each one of them, separately installing Python, separately installing NumPy, separately installing scikit-learn and so on, and all of these packages, then Anaconda offers the feature of integrating all of these packages, so you can just download Anaconda and you'll be able to use all of these Python with all of these packages. Okay, so we're gonna be using Anaconda in this course. So just Google Anaconda, and then you're gonna go to the Anaconda home, and then go to downloads. All right, and this is what we have. So just press download now. Okay, and this will start downloading. So let's go to the installation part of PyTorch. All right, so actually it's very simple to install. First of all, you want to select your PyTorch version. Now, in the course, I'm actually using the previous version of PyTorch. Okay, so I'm not using 1.0, the stable 1.0. I'm using actually 0.4, which is a previous version, and you can acquire it from here. You just go here and you can find version 0.4. but basically they're not much different. So you can go ahead and install the latest version. So go to the PyTorch stable 1.0, and then you need to choose your operating system. So if you're on Linux, then you need to press here. If you're on Mac OS, press here. If you're Windows, press here. And then you need to choose your package. So you want to go to Conda, and then you want to check your select your programming language. So most of the time, people use PyTorch with Python, and it depends on what version of Python you want to use. Now, 2.7, unfortunately, there's no PyTorch version for Windows. Okay, so if I select Windows and I go to Python 2.7, this is what PyTorch tells me. PyTorch does not support Python 2.7 on Windows. Please install with Python 3. So if you're on Windows, then you cannot use Python 2.7. Alright? But anyways, in this course, we'll be using Python 3.6. Okay? However, some people still use Python 2.7. Okay? But in this course, we'll be using Python 3.6. So select Python 3.6, and then you need to select if you want your computations to be on a GPU. Now, this is if you want this to happen, then you need to have an NVIDIA GPU. All right. So I'm not sure about other GPUs if they work. I'm not really sure about this. You have to do some searching to find out. So if you want your computations on a CPU, then you don't have to use CUDA, just press none. Okay, go to none. Now, if you do have a GPU, then you need to select which CUDA version. Now, I won't be explaining on how to install CUDA because there's tons of videos and tutorials on the web on how to do this. So I just recommend that you go to YouTube and type install CUDA on Anaconda. Alright? And you'll get a couple of videos, just choose any one of them and they'll show you how to install CUDA. Alright, now after you installed CUDA, then you're good to go. So select the CUDA version that you installed, and then you're going to copy this command. Alright, and then you're going to go to your Anaconda prompt. So just go to start. I'm here on Windows, and just type Anaconda prompt. Okay, so this is what you have, and then you're going to paste this command over here and press enter, and it will directly install. Now, I'm not going to install it here because I already have it installed. So after you're done, we're going to test if PyTorch has been successfully installed. So just go to Jupyter Notebook. Now, Jupyter Notebook comes already with Anaconda again. So Anaconda offers not only Jupyter Notebook, but it also offers the Spider, which is basically an environment written in Python. There's a lot of other things, but we're going to use Jupyter Notebook, okay, because it's the most convenient one to use, especially for explanations, because we're going to be running the output and showing you the outputs of a particular cell that we're going to run, so you can visualize the output very easily in this case. So just go to start and type Jupyter Notebook, okay, and just open Jupyter Notebook. So this is what you have, okay. Then you go to new and open up a new Python 3 notebook. Alright, and this will open your Python notebook. Now, to test if PyTorch is successfully installed, you want to go and import Torch, okay, and press Shift Enter to run the cell. So Shift Enter, and once it shows the number, that means it ran successfully and it executed successfully, so there's no problems. Now, another thing you want to do is import Torch Vision. So Torch Vision comes along when you install Torch. It's the same command basically. So we're going to go ahead and import Torch Vision, and if we run this, then we get this number. So that means this ran successfully. We get no error. So these two commands have been executed successfully. And the last thing to do is to check whether you've installed PyTorch with CUDA successfully. So how we're going to do this is we're going to go ahead and print torch.cuda.is_available. Okay? And this returns true. That means we have installed PyTorch along with CUDA. That means our computations will be on a GPU. Okay, so that's it. Now we're gonna proceed and introduce you to PyTorch tensors and how to work with PyTorch tensors, and basically you'll get an intuitive explanation of PyTorch. Now we're going to introduce you to PyTorch, but this time in Python. So we'll see how to implement all the PyTorch concepts and all of what we learned in the previous video here. Alright? Now before we move on, I'd like to inform you that this video is quite long, alright? And this is because it's intuitive. It's very intuitive. Now I've gone through all the tutorials, the PyTorch tutorials on the web, and I've made sure that all of what you need to know and all the basic and essential stuff in PyTorch are included in this tutorial. Alright, so this is very intuitive, and basically you don't need to follow any other tutorial. This is basically enough because it includes everything. So it's very intuitive, and that's why it's long. So sorry for that, but yeah. Okay, so let's start. First of all, we're going to import torch. Alright, so there we go. And then we're going to define a one-dimensional tensor. Alright, so one-dimensional tensor is basically just a normal array, or if you're familiar with lists, then it's just a list. Alright, however, a list is implemented in PyTorch is basically a tensor. Alright, so this is how you define a one-dimensional tensor, and if we print that out, then it's 2, 2, 1. Now let's define a two-dimensional tensor or a matrix. Alright, so this is how you define it, torch.tensor. If you realize, it's basically just as defining a list, okay, but you're including torch.tensor. Or if you're familiar with NumPy, then it's just the same way. However, instead of np.array, then it's torch.tensor. Alright, so there's two brackets because it's a 2D array, and this is how you define it. And then if you print b, then you get back this tensor, and this is basically a 2D array, a 2D tensor in PyTorch, and you can also call it a matrix. Now if you want to print the size of the tensor, so if we want to print the size of b, so b has 1, 2, 3, 4 rows and 3 columns. Alright, so if you print them out, this is what you get. A, the shape of A is 3 because it's a 1D, so it's just 3 elements. The shape of B is 4 times 3, and basically the shape and the size give you the same result. However, shape is just an attribute and size is a method because it includes two parentheses. So they give you exactly the same result. It's up to you to choose. Alright, now let's say that we want to get the rows, right, of B. So remember, B is a 4 times 3 tensor, and if we wanted to get the rows or the height, then we have to index this as 0 because the rows is in the 0 index. So we get 4. Alright, now we can also define a float tensor. So this tensor over here is not defined as a float tensor. Okay, if we wanted to define a float tensor, then we have to do torch.float. All right, tensor. So we have to include the float tensor over here. All right, and basically it's the same exact thing here. We just create our matrix or our tensor. Okay, so we've defined C, and if we want to define a double tensor, all right, so there's a lot of types of tensors. There's float, double. You can explore more about them in PyTorch, all right, in the official website. But for now on, if you want to define a double tensor, which has a more higher precision than float, then this is how you do it. Torch.double tensor, and you give it your tensor array. All right, this is another alternative way of doing it. All right. You give the tensor and then you give the data type. All right, it's basically the same thing. So let's run this. Now let's print C. All right, and we'll print D, and we'll also print their type. So their data type, which is expected to be float for C and double for D. All right, so as you can see, it's all good, and this is the same thing, but float 64. So float 64 and double are the same. Alright, and float 32 and float are also the same because double is just a higher precision than floats. We can also print the mean. Alright, so remember, mean is a method, and that's why we need to include two parentheses. We can also print the mean of D and the standard deviation of C and the standard deviation of D. So let's go ahead and print the mean. This is the mean of C. This is the mean of D. This is the standard deviation of C. This is the standard deviation of D. Alright, now let's move on. So this is some concept that actually is very important because you're going to need it while implementing neural networks, when you want to shape a tensor, or reshape a tensor, or resize a tensor. Okay, basically it's included in every single code. You have to find this. This is extremely important. So the method to reshape a tensor is called view. So you give the two dimensions that you want to reshape to, and this will be reshaped. However, one very easy thing that Python provides us is basically -1. So when you provide one of the dimension -1, then its size can be inferred, meaning that the remaining dimension can be inferred, and Python can find out what is that needed dimension. All right. So here you're just telling it that, all right, I need the number of columns as 1, so I need the second index as 1, which means the number of columns as 1. However, you can find out how many rows you need to reshape the B. Okay, so eventually it will be some number of rows that Python will find times 1. All right. So it will be just a single column, one column. All right. So here B is originally, if we go back, B is here 4 times 3. All right. Okay. This is the B. Okay. So now we're going to view it as something times 1. So basically you can refer to this, if you think about it. All right, you can refer to the B, and if it's 4 times 3, that means it's 12 times 1. So it will eventually shape it to a 12 times 1. Now if we type, okay, let me run this. Let me show you the output. Okay, so this is basically the output. So 12 times 1. All right, and this over here is basically the same thing. However, we're reshaping it to a one-dimensional array only. All right. So this is the answer. All right. So it's a 1D array, as you can see, because there's no 2 brackets. So it's a 1D array. However, this is a 2D array. All right. Okay. So this is a 12 times 1, and this is only 12. Now let's view it as -1 times 4. So you're telling Python that I need 4 columns, and you can infer this. All right, and this is what you get. So you get a 3 times 4. Okay. Now, if we wanted to shape it to 3, we don't need to use -1, right? However, it's more handy to use -1. Okay, but if you just directly want to shape it to the new shape, you can just directly give the new shape. So 3 times 4, and here you go. You have this 3 times 4 tensor. Okay, so these two are exactly the same thing. Okay. So whether you put -1 or whether you put 3, they give you exactly the same thing, the same result. Now, for example, we want to assign B to a new shape. All right, so B equals to B.view. So we're just reassigning B. All right, and we're telling it that we need 1 row. You can infer the number of columns. So basically, it's going to be 12 columns. So if we print B and B.shape, then we get 1 times 12. All right. 1 row, 12 columns. It's a 2D tensor. Now, if we want to create a 3D tensor with 2 channels, 3 rows and 4 columns, all right, then first of all, what we need to understand is this is how PyTorch, this is the format of a 3D tensor. So you start for the channels, then rows, and then columns. All right. Some other frameworks are rows, columns, channels, but in PyTorch it's channels, rows, and columns. So for example, if we created this 3-dimensional tensor, which has 2 channels, and it's basically 3 rows, 4 columns. So it's 3 times 4 times 2 if you want to put the channels at the end. So it's 2 channels, 3 times 4, and if we print that out, so this is what you get. Okay, this is the answer. So 2 channels, this is the first channel, this is the second channel, and each channel is 3 times 4. Okay. And then if we wanted to view this 3D array as 2 times 12, then you reshape it to 2 rows and 12 columns. And this is what you get. And this is exactly the same thing here. All right. So one is we're just putting the 12. We're sure that it's 12. And one, we're just letting Python infer. All right. The number of columns. So you'll get a 2 times 12. Okay. And this is the answer you get. Now, let's say we wanted to create a matrix or a tensor with random numbers between 0 and 1. So this is how you do it. Torch.rand without an n. Okay, we'll see when we put an n what happens. But this is without an n. So we want a 4 times 4 tensor. all right, with random numbers between 0 and 1. So if you print r, this is what you get, all right, 2D tensor with numbers between 0 and 1. Now if we want to create a matrix or tensor again with random numbers, but this time taken from a normal distribution that has a mean of 0 and a variance of 1, then this is what we do. So n stands for normal distribution. So torch.rand n, again 4 times 4, we print r2 and we print the type. Okay, so if we go ahead and print that, then you can see this 4 times 4 tensor, and the type is torch.float32. All right, so it's a float tensor. Now, for example, let's create an array of 5 random integers from values between 6 and 9, inclusive of 10. All right. So we need to write 10 in the code, all right? But in Python, the upper bound is not included. So let's do that. Input array equals to torch.rand int. All right. So this is the difference. Rand integer between 6 and 10, but exclusive of 10, and we want it to be shape of 5. We want it to have a shape of 5. Right, so if we print and print the type, then we get some tensor, right, with just normal numbers. So there's no decimals; they're just full numbers. As you can see, they're full numbers here. However, it's of type float by default. You can change the type, of course, but by default it's of type float, and that's why you see a decimal here. So integer stands for the one whole numbers. Okay, so as you can see, they're whole numbers. There's no decimals. They're not like 8.2, 6.3. Okay, as we saw before. So there's no decimals. They're just whole numbers. That's what integer is. Now, if we wanted to create a 2D or array or matrix of size 3 times 3, filled with random integers from values between 6 and 9, inclusive of 10, so it's the same thing, but this time it's just a 2D, so we just specify the size 3 times 3, and if we print it, then this is what we get. As you can see, they're whole numbers again because we put int, random. Now if we want to get the number of elements in the array, right, so this is what you do, torch.numl, so that stands for number of elements, and we specify our array, right, so this is the number of array elements in array, and this is the number of elements in array 2. Now if we want to construct a 3 times 3 matrix of zeros and that has a d type of long, so this is what we do, torch.zeros, and we give it the size 3 times 3, and we give it the data type, which is torch.long. If we don't give it the data type, then it will just switch to the default data type. And if we print it, right, so this is what we get in a full array of zeros with 3 by 3. If we wanted to do the opposite, construct a 3 by 3 array of ones, then all we have to do is torch.ones. And that's basically important when you need to initialize the arrays. So you can initialize it with ones, zeros, or maybe random numbers only. And if we print the type, so I told you before that by default, it's a float tensor. So here when we print the type, then we can see it's a float tensor. Alright, so let's look at this function, rand like. So this is just basically means the same function we learned before, torch.randn. However, when we put underscore like, then it takes the size of r2. Alright, so you're generating random integers exactly with the same size as r2. And the type is torch.double. So it's a double tensor. And we print it, then this tensor we have is just random numbers from a normal distribution. However, their size is just exactly the same as R2. Okay, so they're 4 by 4. Here maybe we can add 2 tensors. Okay, but make sure before you add that they are the same size and the same data type. Otherwise, this would give an error. So the addition result equals to torch.add, and we give the 2 tensors that we want to add, so R and R2, and then when we print the result, then this is what we get. So if you add R and R2, this is what you get. Very simple. You can just maybe do it on a calculator, right? Now, for example, this in-place addition is something also very important. You don't need to reassign it again. All you need to do is this underscore, and that reassigns directly R2. So this is instead of writing R2 equals to R2, R2 equals to torch.add R and R2. All right, so here you're assigning R2 again, but this time you don't need to assign it because this underscore here means an in-place addition, meaning that it modifies directly R2. So if we print R2, then we can see that it's added, R2 is added with R, all right? And this is the result that you get. So this is something very useful, okay? It means an in-place operation. It means that you're directly modifying the result of R2. You don't need to reassign it. So let me write this for you, because so you don't need to do R2 equals to R2, R2 equals to torch.add R with R2. You don't need to do that, all right? All right, you just need to put that underscore, and that will modify R2 directly. All right. So if we print, this is matrix slicing. This is something also very important. So here we want, from R2, we want all the rows in the first column, and that will give you all the rows in the first column. So it will give you this number, this number, this number, and this number. All right. Sorry, column 1, not column 0. And this is start at 0. This is somehow confusing, especially if you come from MATLAB, because MATLAB you need the MATLAB starts at 1, right? However, in Python they start at 0. So 1 basically is this column over here. So you want all the rows in the first column. So this is what you get, 0.7303 and so on, which are basically these numbers here. Now if you want all the rows from column 0 until 2, exclusive of 2, of course, we said that in Python the upper bound is not included, so you get this tensor over here. So basically all the rows from columns 0, 1, and not including 2, so only these 2. That's why it's 4 times 2 only. Alright, and this is the same thing. So we want all the rows until 2, so from 0 to 2, okay, and all the columns. This is what you get. This is called matrix slicing. It's somehow very important in Python. This is how we can extract a single number. So from R2, we want the number that has the index 2, 3. So let's go ahead. This is 0, 1, 2, right? And 3 is 1, 2, 3. So this is the number that you get. 0, 1, 2, right? And then 0, 1, 2, and 3. Okay, so this is the number you get. 0.2054. Okay, it's always confusing for people, especially people coming from other languages. Make sure that in Python the indices start from 0 and not from 1. So 0, 1, 2, 3, and then 0, 1, 2, 3. Okay, so this is the number you get. And then this is a tensor. So this is just a tensor with one number. And if you wanted to just take that number out of the tensor, okay, just access this number inside the tensor. All you have to do is this number dot item, okay, and this will extract the number from the tensor. This is another application, another example. From R2 we want from row 2, from the second row, all the columns, and this is basically what you get. Welcome to the first video of the implementation of a chatbot in PyTorch. Okay, now before we start, I'd like to highlight something. The code that we'll be writing right now is adopted from this link, which is the official tutorial of PyTorch, one of the tutorials. However, in this version, okay, we'll demonstrate more details. Okay, so we'll observe the outputs of each step to visualize what's really happening. And of course, we'll explain this tutorial in depth and make sure that you grasp all the concepts of LSTMs as well as sequence-to-sequence models and all of what is related to building a chatbot. Moreover, there will be some extra diagrams of the architectures as well as diagrams of some other important concepts here in the code. So we're going to visualize these diagrams together. Okay, I drew them to ensure that they will deliver a very explicit concept of the architectures as well as the important steps that are required to implement this chatbot. Okay, so without further ado, let's begin. Okay, first of all, we're going to start by importing our libraries. So the libraries that we'll require is of course torch and torch.nn. okay, which is the neural networks package. Okay, as we're going to see that we're going to inherit one class later from this torch.nn, which is the nn.model, which will be using it to build and structure our neural networks. And then we're going to import the optimizers. Okay, then we're going to import the functional torch.nn. The functional, these include relu and softmax and all of these other functionalities. Okay, so these will all be clear throughout the code. Right now we just need to import them. Okay, other libraries that we need to import are CSV, okay, for reading the data files, then the random library, the regular expressions library, since we'll be working with text, so definitely we will need them, then the operating system, the OS library, Unicode data, and these two. Okay, all of them will be clear later on when we're working with them. Okay, right now we just need to import these libraries. Okay, so I'm going to run this cell, and let's yep, we have no problem. So all of our libraries are imported successfully. Now we want to use a flag. Okay, so if we do have a GPU, then we're going to store that state, which is true or false, in CUDA. So torch.cuda.is available will return true if you have a GPU. Okay, or if you have a GPU, and you should have installed CUDA, as we said before in the installation section, if you want to have GPU acceleration. Now if you don't have CUDA, then this will return false. So now CUDA is either true or false. Okay, so then we'll be using it as a flag to switch between GPU and CPU computation. So then we're going to also define a device, which is our CPU or GPU device. So if we have CUDA, then our device is CUDA. If we don't have, then our device is CPU. So we'll also be using it to transfer our data and our tensors to the GPU and the CPU. So this is these two lines provide an easy switching between the GPU and the CPU. Okay, so let me run this. So if I go ahead and type CUDA, then this should return true because I do have the GPU. And if we go ahead and see the device, then the device is CUDA also. Okay, so this is the importing the libraries as well as the GPU or CPU definition. Now let's move on to the data pre-processing parts. Okay, so first of all, we need to define our data. Now you need to download the data first of all, and now I'm going to show you how to download the data. So you need to go to this website. Okay, I'll provide it in the description, sorry, in the resources part of this video over here. So I will provide a zip file, but in case you want to download it from the website, so this is the website, and this is the Cornell movie dialog corpus. So it includes, if we read here, then it includes 220,579 conversation exchange between 10,292 pairs of movie characters. Okay, so this is a large data set of conversations between characters of movies. So you can read more about this data set here. Now what we want to do is just download the zip file. So just click here, okay, and this will download the zip file. All right, and after you've downloaded the zip file, then this is what you'll get. So you're gonna need to unzip it first. Okay, so just ignore this for the time being. Okay, this is something that we will be processing later on. So you should have, after you've unzipped the file, then you should have something like that. Okay, this includes the movie lines, the movie conversations, the movie titles, and as well as the other data that you will need. So I have I have all of these in a folder called the Cornell movie dialog corpus. So this is the folder I unzipped. So make sure that you unzip this folder inside your directory that you're working on this Jupyter notebook. Okay, if you're working on a Jupyter notebook, otherwise, yeah, basically any IDE, even if you're working on Spider, then you need to unzip the file inside your directory. So make sure you do that. So you unzip the file, and so this is what the name that you get. And then we want to go ahead and take the movie lines.txt. So out of these files that we saw, we want to take the movie lines as well as the movie conversation. So we do create a path for this using the operating system.path.join. So this will create an OS or operating system path to this text file, which is the data file that we'll be using. So the movie lines and the movie conversations. Okay, so let's go ahead and run this. Okay, so let's now visualize some of the lines. So we're going to open the lines file path, which is this over here, which includes the movie lines. Okay, so this is how we do it in Python with open lines. You need to give the name of the path, which is the lines file path, and then this is to say that you're going to read it. So this is in reading mode because you want to read from this file, and then you open it as a file. So you can change this name, it's up to you, you can put any name. So then we're going to go ahead and read the lines of these of this text file. So this is how we do it. File, which is the file that you opened here, dot read lines. Okay, so this is to read every line of your data file, and we store them in lines. So then we loop through these lines. So for every line in lines, but we of course we don't want to loop through all the lines because here is just for visualization. So we only loop from 0 until 7. Okay, so this is how we index it in Python. Remember, the upper bound is not included, so this will return from 0 to 7 only. So we're going to go ahead and loop through our lines, okay, from 0 to 7, and print that line. And we want to print that strip to strip out the escape lines, okay, and as well as the extra spaces at the right and the left. Okay, so let's go ahead and run this, and this is what we get. So this is how our data set looks like. Okay, so we have this, which is the line ID. Then we have this, which is the character ID. Then we have this, which is the movie ID. Then we have the name of the character, and we have what this character said. Okay, so let's say we're taking this conversation over here. Then character U0 in movie 0, which is called Bayanika, said they do not. And then U2, okay, which is called Cameron, in the same movie, replied her, they do too. And then again, character U0 said, I hope so, which is of course Bianca. Then U2 replied, she okay, and so on. So you get the idea. This is how the data set is stored. Okay, you have a line ID, character ID, movie ID, the name of the character, as well as what this character said. Okay, which is the text that will be processing at the end. So this is how you can visualize some of the lines. So we visualized some of the data. Okay, so again, I repeat, this is the line ID, this is the character ID, this is the movie ID, this is the name of the character, and finally this is what the character said, or the text that we'll be processing later on. Okay, this is what we're going to teach the network to do. So now we need to process this data set. So this is what we're going to do. We're going to split each line of the file into a dictionary of fields. Okay, so first of all, we have to decide what those fields are. And as I said to you, these are the 5 fields we have. So we have the line ID, character ID, movie ID, character, as well as the text. So we insert all of these 5 into a list. Okay, and then we create an empty dictionary. And now we're going to go ahead and open the lines file path, which is the same as this over here. Okay, so this is exactly what we're going to do right now. We're going to open this file over here as the reading mode, and then we're going to encode it in one of these encoding formats. So this is ISO-8859-1. So what this does, it encodes the ASCII characters, and in fact it's one of the single byte encoding methods. Okay, so this is to represent this data, to encode it, and then we're going to open this data file, okay, as f. Okay, so f is going to be represented as our file or as our data set, and then we're going to go and loop through every line in this file f. So for line in f, that means loop through every line in f. And then what we're going to do is we're going to take each line, okay, that we're looping in, and we're going to split it. Now we're going to split it according to this character over this multiple or several of characters over here. So we're going to the split term is basically this over here. So that means whenever there is these multiple characters, whenever this line encounters these characters, okay, together combined, then it's going to split. So we're going to start with this, take this, then this is going to be encountered, so it's going to split it. Then we're going to take this, then we're going to take this and this and this. So these are all separated by this multiple characters. So what we're going to have at the end is a list composed of each of these 5 fields. Okay, so that's what it means by splits. So we're returning a list of the fields, and then we're going to create a temporary dictionary. Okay, so this is an empty dictionary called line object. So in this dictionary we'll actually only be processing one line at a time, because if you realize that inside the for loop, then this is going to be we're going to reset that dictionary inside every loop. Okay, so every loop we're doing this, every line we're going to reset it again. So this is going to be reset depending on how many times we're looping here. So now we're going to loop through the line fields, okay, but we're going to loop using enumerate, and enumerate, what it does, it keeps track of the index of the loop. So this I is going to be in charge of the index of the loop. Okay, so maybe in order to demonstrate for you what the enumerate method does, so for example, for I, let me call this D, for example, for I D in enumerate, then let's create a list, let's say 2, 3, 4, 5. Okay, so we're going to go ahead and print I and D. Okay, if we run this is what we get. So we get 0, 2, 1, 3, 2, 4, 3, 5. So D in this case is the values of the list, and I is the corresponding index. So 0, 1, 2, and 3. This is what's really happening in the enumerate function. So for I field enumerate line fields, we're going to enumerate through this over here, and then we're going to create a dictionary. Okay, so this dictionary has a key of the field, and then has a value of the line that we processed and we split over here. Okay, so what's going to happen right now is that line ID will have this, and then character ID will have this, movie ID will have this, character will have this, and text will have this processed text over here. Okay, so we're creating a key value depending on the field as well as what the field is, the actual value of the field. So we're going to loop and do this for all the lines over here. Oh, sorry, I forgot to explain this. So then at the end, what we do, this is in the outer for loop, okay? So it's not in this one. Be careful of the indentation. We're going to take that dictionary of line object, okay, and append it to the dictionary of lines as its value. Okay, so the key of this lines dictionary will have the line ID, okay, and the value will have all of these fields, which is the line ID, character ID, movie ID, character, and text. Okay, so that's what's going to happen. So let's run this, okay, and let's process. So now let's visualize some of the processed data. So let's go ahead and see the lines dictionary, okay, and this is what we have. So as you can see, the key is the line ID, okay, which in this case is for the first one, for example, it's L1045. So this is what we have. This is the key, and the value is all of this dictionary, which is the dictionary for one line. So as you can see, this is the dictionary corresponding to the first key of the lines dictionary. Okay, so we have the line ID, character ID, movie ID, character, and text. So we have this huge dictionary that corresponds to the line ID and all of what's corresponding to this line ID. Okay, so this is what we have right here. Alright, now we're going to do a very similar procedure to what we did in part 1, but this time we're going to process the conversation file path. Now the conversation file path, okay, which is defined here, is basically telling you which characters are speaking to each other and what they're speaking. Okay, so this is why we have 4 line fields. We have the character 1 ID, character 2 ID, the movie ID, and the utterance ID. Now the utterance ID is nothing but the line ID over here. Okay, so for each 2 characters, we're going to have, for example, 4 line IDs. So U0 and U2, okay, are, for instance, the character 1 ID and character 2 ID. The movie ID is movie 0. And then the utterance ID is, for instance, these 4 line IDs. So what's happening here is that we're saying that character 1 ID and character 2 ID are speaking in movie ID, let's say movie 0, and then what they're speaking is determined by the utterance ID, which is basically the line ID. So the utterance ID is going to consist of these 4 elements. So this is for the first element of the conversations, for instance. Okay, so you get the idea that utterance ID is basically the line IDs over here, which determines the specific details of what the character is, the movie ID, as well as what he is saying. So we define an empty list called conversations, and then we open the file, we read it, and then we loop through every line, we split it, and then we define an empty temporary empty dictionary, okay, that represents one object. Okay, and this is exactly the same. Actually, it's identical to what we did here, except that we're changing the lines. Okay, so now what we have is the conv object instead of the line object. Okay, so same thing. We loop through the enumerate function through all of these conv fields, and then we add these keys. So these are the keys. Okay, so for every key of this, we're going to add a value, which is going to correspond to what we got here from the values we split. So until here, okay, this is exactly the same thing. We're changing the string into a list, okay? Until here, there's nothing new. If you don't get this, then please return to the previous video. We explained this clearly. So right now, we're just repeating what we did previously. Now, this is where it's new here. We're going to add another key to this dictionary, which is conv object, called lines. Okay, and this is the value of this key, which is called lines, is nothing but an empty list. All right, so what we're doing here is we're adding an additional key other than the character 1 ID, character 2 ID, movie ID, and utterance ID. We're adding another additional key, which is lines, and its value is an empty list. Okay, so then we're going to loop through all the line IDs. So for every line ID in line IDs, and remember line IDs is this over here, which is the utterance ID, which is also the line IDs here. Okay, which is all of the line IDs here. So for every line ID here, okay, in this utterance ID, what we're going to do is we're going to append the information of the line ID to this key of lines. So remember, lines, line ID, okay, lines is over here, okay? So let's not confuse ourselves. Let's just work with one element. So lines is a dictionary, so I guess lines.items. Okay, this is how we index a dictionary, and we need to pass this through a list. Okay, so list, and then we're going to index the first element. Okay, so yeah, this is the first element of lines. So what we're going to do is we're going to take the corresponding line ID. So lines, which is here, okay? So we're going to take the specific ID with the key here is the line ID that is in the utterance ID. So we're going to take that line ID, okay, from this dictionary of lines and append it to our dictionary of conv objects lines, okay, which has the key lines. So this is what we're doing essentially. And then at the end, when we're finished, then we're just appending this whole object that we got, including the lines key, to this conversation list. Okay, so let's see the results so that can be more clear of what's really happening. So I'm going to run this. Okay, and now let's visualize conversations. Okay, so this is the conversations, and this is too big, so let's just visualize one element only. So this is what we have. Okay, so let's begin from the beginning. We've first added all of the fields, so conv object field should have character 1 ID, 2 ID, movie ID, and utterance ID, which is all over here. Okay. Now after that, we've added a new key, which is the lines. So this is the new key that we added, and inside this key, we've appended all of the corresponding line IDs of each of this utterance IDs. So for L194, which is over here, we've appended all of this dictionary that we got from the lines dictionary. So if we go back here, okay, let me just add a new cell and let's see the lines one more time. Okay, all of these. So L1045, okay, for example here, this is L1045. In fact, let me index this what was it? L194. So let's go ahead and type L194. Okay, and this is what we get. So this whole value of this key of 194, we're going to take all of this and append it to the lines of this conv object dictionary. Okay, so as you can see, L194 is going to consist of all of this that we got from here. So they're identical here. Okay, and same thing, we loop through all the other line IDs. Okay, and at the end we get this huge dictionary. Okay, which is a nested dictionary actually. And so every element of this, we're going to have all of the conversations inside this list of conversations. We're going to have all the conversations that took place. Okay, arranged in this format, arranged in a nested dictionary, which consists of the character IDs, the movie ID, and the utterance ID. Inside the utterance ID is another list. Okay, sorry, inside the lines is another list. Inside this list is a dictionary. So it's quite nested, but it's very easy to understand. Okay, it's quite, sorry, it's nested. So it's too much nested, I can say, because there's lists and dictionaries inside each other. But this is actually the best way in order to arrange our data. Okay, so this is how we process the conversation data file. Okay, so that's it for this video. In the next video, we'll be actually processing the key questions and answers together, combining them in order to process them for the encoder and the decoder part. Thank you very much, and I'll see you next time. Hello, and welcome back. All right, now we're going to extract pairs from the conversation. So we're going to arrange the data set into the form of questions and answers. Okay, so we're going to take the questions with the respective reply and store them all into one list. So this list, which is called QA underscore pairs, is going to have some elements, and each element contains the question with the respective reply. Okay, question or question with the respective answer. So let's see how we can do that. So first of all, we're going to loop through the conversation. So before we loop, let's go ahead and see what the conversation list looks like again. Okay, and again, I'm just going to take one element only. Sorry, I think I forgot to run. Oh, it looks like that. We forgot the S here. Okay, so there we go. We have our element of, this is one element of the conversations list. Okay, so what we're going to do is we're going to loop through every element of this conversations list. Okay, so this is, for example, one of the elements. So in each element, what we're going to do is we're going to iterate over all the lines of the conversation. So inside this loop, we're going to have another for loop. So for I in range length of conversation lines -1. So essentially what that means is basically how many conversations you have, how many questions and answers do you have. Remember the conversation lines, okay, which is this over here. This is the conversation, this is the lines. So inside this we have a list, okay, and inside this list we have this dictionary which contains the line IDs for every character, okay, and what he said. So we have this, and then this, and then this, and then this. So we have 4 sentences, 4 conversations taking place here by 2 characters. So we're going to take this length, okay, and -1 is to stop at the index 2, okay, and we're going to see why that happens later. So length of conversation lines should be equals to 4. Now 4 minus 1 is 3, so we're going to have I in range 3, so we're going to have 0, 1, and 2. Okay, now what we're going to do is take first of all the input line, So what we're going to do is we're going to go ahead and take the value of conversation lines for index 0, and we're only interested in the text. Then we're going to strip it. Okay, let's break that down. Okay, I'm going to break this down as much as possible. Now, if you already understand what's happening, then please feel free to skip it. Okay, so if we go ahead and okay, let's just ignore this for now. Okay, so I'm just going to comment this out. Conversation lines. Okay, so we're only working with one element, so let's just put 0 here. Okay, so if we take the lines of the first element of conversations, then this is sorry, conversations again. Okay, this is what we have. Okay, so the length should be 4. Okay, because we have 4 conversations going on. Okay, so again, let's go ahead. So we have these 4 line IDs. Okay, so this is character U0 is asking a question, U2 is replying, then U0 is asking a question again, and then U2 is replying again. Okay, so we're going to loop now through each one of these, through each line ID. So that's why we have I here. So therefore, if we have the I as 0, okay, then what you expect to happen is only to get this first element, which is this line ID L194, and in fact this is what we get, right? Now from this, okay, so we're looping, okay, so this is just to demonstrate, but this is actually I, so you're looping through every element. Now the text, okay, is to extract this element only, because this is what we're interested in, right? What this person said, or what this person asked. Okay, so remember, this is the dictionary. All of this over here is a dictionary, and we want to insert we want to take the value of the key text. So that's why we need to index text here. So let's go ahead and see what happens when we do text. And this is, oh sorry, I think I already removed these. So yep. Okay, this is what we get. Can we make this quick and until the end? So this is what the character asked. Now, why I'm stripping it, and you're gonna see the difference right now. So if I comment this out, okay, and if we strip it, then realize that this escape character, or the skip line character, goes away. Okay, so this is to avoid any of these characters, because we just want pure text. Okay, so this is essentially what's happening here. This is the input sentence. Now the reply is the same exact thing, however it's just the next index. Okay, so remember that this is the first index. Okay, this is 0, index 0, and then its corresponding reply should be 0 plus 1, which is this over here. So this is the reply. That's why we have I plus 1. So we're going to have I in range 2, so 0, 1, and 2. Okay, for I in range 3, so I is going to be from 0 to 2 only. So the first iteration, you get 0 and 0 plus 1, which is 1. You get the first 2, and then in the next iteration, I becomes 1. So then you get 1 over here and 2 over here. Okay, and then finally the last one is 2 over here, and then you get 3 over here. Okay, so this is the form of the questions and answers. Now, before we append these inputs and replies, we're going to check that they have been successfully extracted. So if input line and target line is going to return true if there is actually this input line and target line. So if they exist, if they were successfully extracted, there's no problems. Or in other words, if they're not blank, okay, they're not just empty strings, then we're going to append them. Otherwise, we're not going to append anything, because we don't want to mess up with the data. We only want to append if both the inputs and the replies, or the questions and the replies, are okay, and they do exist. So that's why we append this to the Q&A pairs. So we append the input line and the target line. So the question and the answer or the reply is going to be separated by a comma. So let's run this, okay, and now let's go ahead and see the Q&A pairs. Okay, this is what we have. So if we take the length, okay, then we're going to have how many conversations that we got, which is quite a lot actually, 221,282. Okay, so Again, let's watch. Let's just observe the first element. Okay, and as you can see, this is the first question. Can we make this quick and until the end, until again, and then the reply, which is separated by a comma. Realize this. Then we have the reply as well. I thought we'd start with a pronunciation, if that's okay with you. So this is how the questions and answers are combined together into one list. All right. So in the next tutorial, we'll be actually saving this into a text file, so we don't need to process it many times. Alright, now we're going to save what we have into a new text file called formatted movie lines. So we use the operating system path.join. This is to create the path of what we want. So we want to join these two. So this is the working directory that you have, okay, which is sorry, not the working directory, the folder that contains the data, the one that you unzipped, okay. This is the folder that you unzipped. So the folder that you unzipped should be called Cornell Movie Dialog Corpus, and it contains all the data that we're using previously. And then we're going to create a new text file, which is called formatted movie lines.txt. Okay, so this is how we do it. We define a new file, and then we're going to use the separator or the delimiter, which is the tab. Okay, so this is the tab sign. Okay, then we're going to decode the delimiter, which is the tab that we're using here. This will be more clear later on when we're talking about the writing to the text file. Okay, so now we're going to go ahead and use the CSV library to write to the text file. So first of all, we're going to use the open from the operating system. So with open data file, okay, which is this path over here, we need to give the argument. This is the first argument, the data file. Then we're going to need to give the mode, which is write, and then the encoding, which is the UTF-8, as output file. So we're going to open this file, okay, as an output file in the mode write, because we want to write to the file. And then we're going to create an object of the class, the CSV.writer. So we want to create an object of the writer class, okay, and the arguments that this class of writer expects is actually the output file, which we opened here, okay, and then the delimiter, which is the separator. So how to separate your inputs is by using this tab file that we defined over here. Okay, and then for each pair in Q&A pairs, okay, remember Q&A pairs has the questions and answers. So for each of these questions and answers, then we're going to write to that file. So we're going to use a method of that writer object, which is write row. Okay, so what it does is it's going for each of the pairs, it's just going to write and then skip a line, right, and then skip a line. That's why it's called write row, because it writes a row and then it goes to the next row and the next row. So when it writes, it just skips a line automatically. Okay, and what we want to do is write this pair that we're looping through here over here. Okay, and then after we're done, then we should get the file done writing to file. All right, so let's run this. And done writing to file. Okay, now if we open our directory or our folder, which is Cornell Movie Dialog Corpus, we should find this file over here. So let's see if we got that. Yep, there it is. Okay, so let me open it, and there we go. So as you can see, the questions and answers have been saved into a text file, separated by a row. Okay, so if we go ahead and scroll here, okay, so that's as you can see, this is the separator, the tab. So this is the question. If you remember, this is the question. All right, and so after the question ends, we have the delimiter, which is the tab. So as you can see, this is the separator over here, and then the reply. So this is the reply, and after the reply, we have a new skip line, or this is a new row. Okay, that's why it's called write row, because it skips a line after every loop. So then we have the second, then we have the third, and so on. All right, and as you can see, it's a very long list of questions and answers. Okay, now let's visualize some of the lines. So this is the same thing, but this time we're going to define the data file as the path that we saved. Okay, it's the same thing essentially, it doesn't really matter. Or as the path.join, here we also used. So this is just to generate the path. So even if you don't have it, it will create one. If you have it, it will just use the one that you have. Okay, then we're going to open this file as read binary. Okay, you can also do read. I tried it with read, it also works. Then we're going to open this file as file, okay, and then we're going to read all the lines. So this is one of the methods that we use also from the OS. So it's file that we open .read line. So this essentially reads all of your lines. So whatever is in your text file is going to be stored in lines. And then we're going to loop through all of the lines here. So for line and lines, and we only want to loop through some of them. So I just want to loop through the first 7. Okay, so from 0 to 7, and then we're going to print the line. Okay, so let's go ahead and see. Yep, there we go. So we have this question, okay, and then we have this answer, and as you can see, the two of them are separated by the delimiter, which is the tab which we defined earlier. And then we have the skip line at the end to indicate that this is the first pair. The first pair has already been done. Okay, so these are the first 7 elements of this text file. Alright, that's it, and we're done, mostly done with reading and processing the data. We just have one more thing to do, is to process the words. So we'll be doing that in the vocabulary class, which we'll be creating here. Alright, now we're going to look at how we can process the words. Now, we're going to define a new class called vocabulary, and this class is capable of processing the words. For example, adding words to the dictionary, removing words, filtering out the words, and so on. Okay, so now we're going to see how we can do that. Okay, before we begin with the class of the vocabulary, we want to assign a unique index to each of the pad token, start of sentence token, and end of sentence token. So the pad token is going to be used to pad the sentences that have a short length, because at the end we're going to use a fixed size length. Okay, so whatever sentence is shorter than the other, then we're going to just pad it with zeros. Okay, then we're going to also assign a unique index to the start of sentence token. So this is the start, and as well as the end of sentence token. So this is the end to indicate the end of the sentence. Okay, so these two are to indicate the start and the end of the sentence respectively. Now let's begin with the vocabulary class. Now, first of all, in the initialization of this class, we only need to pass one argument, which is the name of the vocabulary. In this case, it's what we're using. For example, the corpus. We're using the corpus data set. So we might want to provide the name so we don't confuse. That's if we're using, maybe I can say, various data sets, but in this case you can remove it because it's pretty obvious. So it's up to you. You can either keep it or remove it. It's not really necessary. Okay, so inside the initialization, we also have our class variables or class attributes. So we have an empty dictionary of a word to index, and this maps a word to a unique index. So for example, the word high would be mapped to a unique index of 5, let's say. Okay, so each word of our data set will have a unique index, and we store this, we arrange this in this word to index dictionary. Okay, so the key of this is the word and the value is the index. Same thing, word to count. Now the index to word is the opposite of word to index. Okay, so let's first of all cover what word to count is, and this basically counts the repetition or the frequency of the words. Okay, so for example, how many times did the word high repeat? Okay, so we want to store the frequency of the words. Now, index to word does the opposite of word to index. It just maps the index to the word. Okay, so the key is the index and the value is the word. Okay, now first of all, we need to add the 3 tokens here. Okay, the 3 extra tokens, which are the pad, start of sentence, end of sentence. So we assign the pad token, which is 0. Okay, so this is the index, and as I told you, it's an index to word dictionary. So index is the key and the value is the word, so the word is padded. Same thing, the start of sentence token, which is 1, we're going to map it to SOS, and 2, we're going to map it to EOS. Okay, end of sentence. And then we're going to start by initializing the number of words we have to 3, because we have the pad, start of sentence, end of sentence. So this is the initialization. We have 3 for the number of words. Now let's go to the methods of this class. So the first method we have is adding words to the dictionary. Now the user only needs to input the sentence, and then we're going to split that sentence and then add every word of that splitted sentence. So for every word in sentence.split, we're going to split the sentence according to the space. Now let me show you what sentence.split does. Okay, so let's say I have sentence, okay, equals to hello, how are you doing? Now if I go ahead and type sentence dot split, okay, then that will return to me the word split it out. Hello, how are you doing? Okay, so we have 5 words. We split that sentence and we get back a list of all the words in this sentence. Now by default it splits by a space, so you don't need to actually include the space, but if you want, you just get back the same results. Okay, so after we split the sentence, we're going to loop through all of that list of words that we got from the sentence, and then use the method, which is what we're going to explain just now. Okay, just in a moment. We're going to use this method to add the word to the dictionary. Okay, so we're going to use the method of this class, which is add word, to add each word of that sentence we split. Now let's see what add word does. So the first thing is to check whether that word is already included. And remember, the dictionary that's responsible to store the words and their corresponding indexes is word2index. So we're going to check that the word is not in word2index, which is this dictionary that we defined here. Okay, and if it's not, then we're going to use the this word that as the key of this dictionary word2index. So word2index word, okay, it equals to self.number of words. Now we're going to start with 3. Okay, now remember that this is 0, this is 1, this is 2. So the first number to start is 3. The first index to start is 3. So therefore this word would be assigned to the index 3. And then we're going to increment that, okay, because the next word would be assigned to 4, then 5, then 6. So we need to increment the number of words. So that's where we do it. You can also do it after this directly, doesn't matter. And then we're going to also update the word to count dictionary, which stores the frequency of the words, how many times the word appeared or how many times it's repeated. So until now we have 1 time only. All right, so self.word to count for this specific word, okay, equals to 1. This is the value of this the key of words. So we have this dictionary with a key of word and a value of 1 right now. Okay, and as you're gonna see later, that if the word does exist, okay, then we're going to go ahead and increment that value. So word to count for that specific word, okay, equals the word equals word to count word plus 1. Okay, so plus equals 1 just means this equals to this again plus 1. So we're going to increment that to tell or to store that this word has been repeated again. Okay, so we start with 1 and then we increment if the word exists again. And the last thing to do is the index to words. Okay, so is the same thing, but this time it's we need to assign or we need to initialize the index to word dictionary using this word. So remember, it's just the opposite. So we initialized first using the key was the word. This time the key is the index, okay, which is 3 for the first time, and the value is just the word. So this is just the opposite as this. You just swap these two, okay, because we're mapping an index to the words. Okay, so that's the add word method, which will be called every time we use the add sentence method. Okay, the last function that we're going to look at right now is trim function, and that basically removes the words below a certain count threshold. So the words that do not repeat a lot of times, okay, let's say we have a word that only appeared 3 or 4 times, then we're going to remove that word from our dictionary. And that is because it rarely appears. So we don't want this thing to confuse our network. So that's why we need to remove the words below a certain count threshold. So this trim receives only one argument, which is the minimum count. Okay, so this is the threshold, which is the minimum count. So whatever words that don't pass the minimum count, then we're going to remove them. Let's see how we can do that. So first of all, we're going to define an empty list called keep words, and then we're going to loop for the key and the value, okay, for every key value in self.word2count.items. So word to count, remember, maps the word to how many times it is repeated. Okay, so it maps the word to the frequency of the word. And then we use dot items because we want to get the keys and the values. That's what we're extracting here. We're extracting the keys and the values. And then remember, the value of each key corresponds to how frequent the words are. So if the value is bigger than the minimum count, which is the threshold we define, we want to keep the word. So we append the key, which is the word, to this list of that's called keep words. Okay, so we keep on doing this until we finish all the words. And therefore, we only have the words that have passed this threshold. And the last thing to do is to reinitialize the dictionaries, because remember, right now our dictionaries contain all the words. Okay, our dictionaries contain all the words here when we process them here. Okay, so we want to make sure that we only keep the words that did pass the threshold in this dictionary. Okay, in all of these dictionaries. So we do the exact same thing. We initialize them to empty dictionaries at the beginning, except this one we initialize it to the pads SOS and EOS. Same thing here. Number of words is 3. So this is exactly the same thing as the initialization of the class. And then all we have to do is just loop through this list of keep words and then use the add word methods to add all of the words in this list keep words. Okay, and this is to print how many words we kept. So we're going to see later on how this is going to be printed out after we trim the words. So we're just going to get the ratio of how many words we kept. We're just going to take the number of words that we kept divided by the number of words that we have in total, and then we're going to get this value. I'm going to show it. Alright, now let's continue the data pre-processing part. Now we want to define a function called Unicode to ASCII. And we're going to give this function any string as an argument, and it will return the plain ASCII of that string. Now, what do I mean by plain ASCII? Let's see. So first of all, in order to make this clear, let me run this function and then test it, as we're going to see here, and then this will get more clear of the functionality. Okay, we'll get more clear on the functionality of this function over here. So I'm gonna give it this string. Okay, so as you can see, this is the string that we're going to give it. It consists of Montreal and Françoise. Okay, I hope I read it correct in French, and as well as some other points, okay, or dots. So let's see what happens when we apply the Unicode to ASCII to this string over here. Okay, and as you can see, this is what happens. So it is removed the accents of the string. So we have an accent here. Okay, we have an accent here. So what it does, it removes them. Of course, we want to remove them before plugging them to our neural network. We just want to make the data as simple as possible. Okay, one more thing. NFD stands for normal form decomposed. And what it does, it decomposes the characters and then it combines them all together. And depending on which characters is basically the S, which is this argument to the function. And what we're doing here is we're doing a comprehension, okay? So we're doing a tuple comprehension, basically. So C for C in Unicode, I did that normalized. So we're going to apply this for every C, okay? For every C in this normalized string, okay? And we're going to join everything together using this. So this means, okay, let me show you actually what this actually means. If we do dot join, let's maybe give it a list of letters. So let's put H, okay, then we'll put E, then we'll put L, okay, and let's apply this dot join. Okay, this, and as you can see, what we have is a combined version of these characters. Okay, so we combine all of these characters using this dot join methods. Now, if I change this to a space, and then I want to join this character over here, which is a space, to these, then you can imagine what's going to happen, and they're going to be separated by a space. Okay, so what we're doing here is that we don't want to separate by anything, we just want to join them together. And basically that's what we get. Okay, so you get it here right now. So we're joining every character of the normalized string S if the category of that letter C that we're looping in does not equals to mn. Now mn stands for non-marking space. That's basically something also to deal with the character type. Okay, so then we have another function which is normalize string. So we also have an argument of this string over here. So the argument of this function is also a string, and what we're going to do is we're going to first of all lower the characters. So we're going to turn it into a lowercase. Okay, so whatever it is, if it's an uppercase or lowercase, all of them will be lowercase characters, and then we're going to strip it. Remember, strip gets rid of the new line or the escape line character, as well as the right and left white spaces. Okay, so we've seen how to work with strip before. And after we've lowered the case and stripped it, then we're going to pass all of this through the Unicode to ASCII function that we did over here. Okay, so that's what the first step of this function over here. And then we're going to go ahead and replace any of these characters, which is dot, exclamation mark, and question mark, by a white space plus the character. So for example, if we have this character, if we encounter this character, as we're going to test over here, so let's say we encountered this character, then we're going to replace it by a space plus this character. Okay, so it's going to be replaced by a white space plus the character itself. Now this /1 over here, okay, it means that the first bracketed group. So this is the bracketed group, okay, and /1 means that we want to take the first bracketed group, which is this over here. And R is to not consider the slash as a character, okay? So because usually the backslash in programming indicates something. For example, \n indicates a new line. So we don't want to consider this backslash as we don't want to consider this backslash plus the following character as one character. So for example, we don't want to consider /1 as a new as a complete new character. So that's why we need to put R. Okay, so R is to escape the backslash. And finally, plus means one or more. So essentially what we're doing is we're going to substitute, and this is basically a method of the RE, regular expressions model in Python. So we want to substitute any of these characters, okay, with a white space plus the character. Okay, so this is a white space and this is the character itself. All right, and actually the plus, we should put it here, okay, because here we have the plus. Okay, now let's see what this does. Again, is the substitute function from the RE model. So we're going to remove any character that is not a sequence of lower or uppercase letters, okay, and plus means one or more. So even if we have at least we should have one or more, or if we encounter at least one, okay, if we encounter at least one, then we're going to perform this. So this can be performed for one or more. That is what the plus means. So we're going to substitute any of these characters over here from A to Z in a small case or lowercase, sorry, A to Z in uppercase, the dot, question mark, and the exclamation mark. Okay, so any of these characters, one or more of them, we're going to substitute it with nothing, and that's basically just like saying that we're removing this character. Okay, so we're removing any character that is not a sequence of a lower or uppercase letter. And one more thing, this is a sequence, okay? So we're not saying that it's one letter, it has to be a sequence. So there has to be more than one letters following each other. Okay, that is what this dash means. It means a sequence. And finally, we're removing a sequence of white space characters. So again, this S corresponds to the white space. Okay, so plus means one or more, and we're going to substitute it with nothing, or in other words, remove it. Okay, and then we're going to strip it in order to get rid of the right and left white spaces, as well as the escape character. So let's run this, and let's, for example, apply it to this string over here. Let's see what's going to happen. And this is what happens. So as you can see, this is a sequence of numbers, okay, which is not a sequence of lowercase or uppercase characters. So that's why it got removed. And remember, we replaced it by nothing. So that's why it's removed over here. Okay. And then, for example, when we encounter this over here, this explanation mark, then remember we're going to replace it by a space plus this explanation mark, which is over here. This is the space and this is the explanation mark. Similarly, this is some white spaces, a sequence of white spaces, and they got removed. And then a question mark is also replaced by this is a question mark. Remember, we did this functionality over here, and it's going to be replaced just like the explanation mark by a white space plus the character. So this is a white space plus the character. So this is basically using some methods of the regular expression model in Python. Okay, and this is very helpful for processing the text. All right, now that we've saved our processed file, which is called formatted movie lines. Okay, so I repeat, this is the formatted movie lines, which is the file that we processed and saved. So each line of this file consists of a conversation between two people, separated by a tab. So for example, the first line, this is the line of the first or what the first character says. So the conversation that taking place for the first character. So the first character says all of this until here. Okay, and then we have a tab. Okay, so we're separating it by a tab, and then we have a second person replying. So basically that's what the formatted movie lines is. Okay, so now what we're going to do is we're going to define the path to that file. So it's, in that case, it's called data file, and we just join the path between our directory and this text file that we processed and saved. And then we're just going to print an indication that we're going to read the file, because that is going to take some time actually. So we need an indication when so we can know when the process is done. Alright, now we're going to take the lines. Okay, sorry, we're going to take the data file. Okay, so that text file, we're going to open it using the IO open function. Okay, using encoding UTF-8. We've explained that previously, why we used encoding UTF-8. Okay, and then we're going to the same thing. This is exactly the same thing as what we saw before. So we're just opening the file and reading it using the .read function, and then we're using .strip to strip the right and left white spaces, as well as the escape characters. Okay, escape line characters that indicate a new line, and then we're splitting it. So actually what's going to happen right now is that lines is going to be a list. Okay, and each element of that list is going to contain the pairs of conversation. Okay, so the first character and then the reply of the second character. Okay, so we split by the new line escape character. Okay, and remember that originally the data file format is separated, the conversations are separated by the escape line character. Okay, as we saw previously here when we save that file over here. Okay, so now we have a list called lines. Okay, and this list consists of the pairs of conversation. So now what we're going to do is we're going to process all of these pairs. So this is a list comprehension. Okay, before we go into this, let me explain this in detail, how list comprehensions work, because we're going to actually work a lot with them. So what I can do is, let's say, define A, okay, and then I can say I for I in range 0 to 10. Okay, and that will return a list for me. Okay, so now if I go ahead and run A, then I get a list of numbers between 0 to 9. Okay, so I for I in range 0 to 10, that means I is going to loop from 0 until 9. Okay, and each time it's looping is going to append that number to that list. So eventually you're going to have this list. Okay, and that is what a list comprehension is basically. So what we do now is we loop through all of the elements of the lines. So again, we're looping through all of the conversations, okay, the pairs of conversations. So for every pair in these lines, okay, and the lines list that we saved here, this is what we're going to do. Okay, we're going to normalize the string s for s in paired split. Okay, so bear with me now. Right now, this requires your attention. So the first step is that we're processing each pair of the lines. Okay, so right now we're working with a pair. Now this pair, okay, we take it and we split it according to the tab. Remember, the two people that are speaking to each other are separated by a tab, okay, as we saw before. So we're going to take that pair, okay, in the lines, okay, and we're going to take each element of the lines. So in other words, we're taking each pair, we're splitting it by the tab. That means we're getting back two elements. The first element is the first person, and the second element is the reply by the second person. And what we're going to do is that we're going to loop through every character. So there's a a double for loop here, which is for s. So for each character in the two characters, okay, after we split them, okay, so for each of these characters, we're going to normalize the string. So we're going to normalize what the person asked or replied. So let's explore that more in detail. Okay, so first of all, I'm going to run this, and it's going to take some while. Okay, it's going to take a while to run and done and finish. Okay, so so it's done reading. Okay, and so that's why we need to print actually something to indicate that we're done. You can just skip it. It's okay. It's not really important, but I just prefer to keep things arranged. So now if we go ahead and I'm gonna explain this process again. Okay, so if we go ahead, now we have our lines, and if we take the first element of our lines, then this is what we get. Okay, and then if we take this returned element and we split it according to the tab, okay, then this is what we get. We get a list of the two sentences. Each element is what the character said. So this is what the first character questioned, and this is what the second character replied. So now what we're doing here for s in paired split, so this is the result of paired split. So for s, which means for this character, we're going to go ahead and normalize the string, and then we're going to go and normalize the string as well for this character. Okay, so this as well as this, the two of them. That's what we're doing here eventually. So at the end, we'll just end up with a huge list of pairs. Okay, that includes the normalized strings or normalized text for each of the characters. And then finally, we just create an instance of the vocabulary class. Okay, so we're just creating an object of the vocabulary class. Remember, the only argument is just the name of that vocabulary, as we said here. Okay, so remember, this is the only argument we need to input to initialize our class, which is the name. Okay, so yep, we're done with this, and now if we go ahead and look at pairs, it's going to be something very huge. Okay, a huge list. If we in fact take a look at the length of this pairs, then we're going to see how many conversations we have, and we have 442,563 conversations, and we're going to filter them actually later on. So as we can see, we have a list containing elements. Each of the elements of that list is basically the question and the reply. So the conversation between the two pairs. Okay. Now this should not include if you're using PyTorch 1.0, which is currently the newest version or the most recent version of PyTorch. Okay. However, if you're using PyTorch 0.4 or lower, then you'd find this. Okay. And we're gonna filter this later on. So do not worry about this. All right. Now we're going to continue on and do some more processing. So we're going to get rid of the long sentences. We don't want any long sentences. So we're going to define the maximum length of the sentence is 10 words. And whatever sentences are over or exceed 10 words, then we're just going to get rid of them. Let's see how we can do that. So we're going to define a function called filter pair. And what we're going to do is we're going to pass this pair, which is a list of two elements, okay, as we saw here. from this pairs function. Each element, remember, is a list of 2 elements containing the conversation of the 2 pairs. So what we're going to do is we're going to take the first element of this, P0, which is what the first person said, and we're going to split it. So after we split it, we get back the number of words of with the number of words of the first sentence, and the same thing, we do the same thing for the second sentence, which is the reply. We split it, and then we're going to get back how many words that we have, okay? And then we're going to compare it. So we're going to do a Boolean function actually here, which is the length of this of these words, which is the words that we split, okay, is smaller than the maximum length, which is 10. So this will return true if the sentence is under the maximum length threshold. All right. So let's explore in depth what's really happening. So remember that we have our list pairs, okay, and we're going to take one element, for example. So this is the first element, and then what we're going to do is, again, so this is 0 here, so we're taking the first element over. So this is I, okay, this is the loop. So let's just imagine that we're just working with the first element, so 0. And then we have a 0 here, okay? So this is the first element. And then if we go ahead and split according to what's written here, okay? So this is what we get back, a list of the words. And then if we take the length, okay, then we get 25. And now if we compare, if we do the Boolean function, smaller than 10, this will return either true or false. In this case, it will return false because the number of the words are bigger than 10. Okay, so that's essentially what's happening here. That's in detail what's happening here. So we do the same thing for the first and second sentence. So the second sentence is 1, and again we get false. Okay, now if that's correct. If either the first or second sentence exceed the maximum length, then we're just going to get rid of the whole thing. Okay, so it's only one. Okay, one of the conditions, either the first or second sentence exceeds the maximum length, then we're just going to get rid of the whole thing, because realize that we use the AND. Okay, this AND means that both of these conditions have to be correct in order for this to be returned. So therefore, if any of the sentences is below, exceeds 10 words, then we're just going to get rid of it. Okay? So this is actually what we're doing here. Okay, here we're just returning the true or false. Okay, so that will just return true or false. Okay, and then what we're going to do, that we're going to say that if this is true, then we're going to keep the pair. If not, we're just going to get rid of it. So what we're doing here is we're looping through all the pairs. So for every pair in pairs, if the filter pair, okay, which is going to be either true or false. So if it's true, it's going to keep the pair. If not, then it's just going to ignore it, because there's an if condition here. So that's essentially what's happening here. So let's run this function. Okay, and the last thing is to check these guys over here, which, okay, let me show them for you. Remember that we have the pairs, okay, and we can realize these elements, these empty elements. So for example, pairs 1, okay, is nothing. So the length of this should be equal to 1, okay, because we have only one empty element, okay, which is this. So we're gonna check that if the length is bigger than 1, okay, that means there's actually a conversation between two pairs. So then we're gonna keep it. So for pair and pairs, okay. So we're gonna loop through all the pairs, and then we're gonna check if the length of this pair is bigger than 1. Okay, that means this is not true. So then we're gonna keep the pair. So that's what we're doing over here. Okay, and then we're going to print originally how many pairs do we have. Okay, so originally we have how many pairs or conversations in the data set, which is just the length of the pairs. And then we're going to call this function, which is the filter pairs. Okay, filter pairs, which is this over here. And that's going to filter our pairs according to the maximum sentence length. So after we filter, then we're going to print again how many sentences are left, or how many pairs or conversations are left. Okay, and then we're going to see how many sentences have been filtered. So let's go ahead and look at that. So if you run this, there are, first of all, there's 221,282 pairs or conversations in the dataset, and after filtering, there's only 64,271 pairs or conversations left. So as you can see, we've reduced the amount immensely after filtering. Alright, now you can play with this threshold, you can increase it, decrease it, it's up to you. Okay, but 10 is actually a very good value. Alright, so now after we've filtered our sentence, then we're ready to add it to the vocabulary object that we created here, which is VOC. So remember the sentences we had was this amount, and we filtered them to this amount. So we have 64,271 pairs of conversations between two people. Okay, and now what we're going to do is we're going to take all of the words, okay, and add them to the vocabulary class. So what we're going to do is we're going to loop through these pairs, and for every pair, so for every sentence or for every character, we're going to use the add sentence method of this vocabulary class. Okay, so this is an object of the vocabulary class, and we're going to use the add sentence method to add the first pair and the second pair. Okay, so the first pair is the first character, and the second one is the second character. Okay, so we're looping through the pairs. Okay, so for every pair, we're going to take the first character and the second character, and we're going to add this whole sentence using this add sentence method of the vocabulary class, which I remind is here. Okay, and this actually calls the add word method. Okay, so the add word method is inside the add sentence method. Okay, so after we've added them out, we just print the number of words. Okay, remember the number of words is an attribute of the vocabulary class. Okay, so we go ahead and print the number of words, and then finally we go ahead and visualize some pairs. So let's just visualize the first 10 or 9 pairs, and then so we're just gonna loop through all the first 9 pairs and print them out. So let's just, this is for visualization, nothing more. And these are the pairs. Okay, so you have the first character, the second character, the first character, the second character. They're separated by a comma. Okay, so yeah, this is the pairs, and now what we're gonna do is we're going to trim the words that are not really frequent, that do not appear often. So if a word only appears 3 times, then we're going to get rid of it, because we don't want to confuse our model with words that are rare to appear. Okay, so that's why we're going to trim the rare words. So our function is going to take 3 arguments. It's going to take the vocabulary object, it's going to take our pairs, the list of pairs, and it's going to take the minimum count, which is 3. Okay, now you can change this, it depends on you, but also a good value is 3. So you may change it if you want. Now what we're going to do, first of all, we're going to call the trim function in the vocabulary class. Okay, so remember what the trim function does. Okay, this is what the trim function does in the vocabulary class. It does actually all the work. We've already coded this down, so we just need to call it. Okay, we've explained this previously, so we're not going to go ahead and explain this again. But the only thing that we need to do right now is we just call this function from the vocabulary class. It does all the work already. So we call this trim function. Okay, so trim the words used under the minimum count from the vocabulary. And now remember, after we've trimmed the words, okay, then we still need to reconstruct our pairs. Okay, because our pairs include the words that whether or not they include frequently or infrequently, they include all the words. Okay, but we need to find the pairs that correspond only to the words that do not appear that do appear frequently. So we need to find their corresponding pairs. So let's see how we can do that. We define a new list, an empty list called keep pairs, and then we're going to loop through all our pairs. We're going to take the first input sentence and the reply, which is the output sentence. So the input sentence, remember, is the first element of the pair, and the output sentence or the reply is the the second element of the pair. Yeah, 0 is 1, 1 is 2, because the indexes start at 0. So then we're gonna give a boolean function, or boolean variable, sorry, for keep input and keep output. So we're gonna set both of them to true, and then we're gonna go ahead and take this input sentence, okay, which is, remember, the first element of the pair. I repeat again, and then what we're gonna do is we're going to split it. Now you can also ignore this; it's not really important, because by default it splits by a space. So we're gonna split it, and that's gonna return a list of words of the input sentence. And then we're going to go ahead and say if the word, okay, if the word in this splitted sentence is not in vocabulary.word2index. Now you remember the vocabulary.word2index contains the filtered words. Okay, remember that we filtered them here. Okay, when we called the trim, we now, what we have in our word2index dictionary, the new one, is only the filtered words. So if this specific word that we're looping through in the input sentence is not in this dictionary, then we're gonna say keep input equals to false. So we're gonna switch this variable to false, and we're gonna break. Now when we break, we're just gonna break off that whole loop. So we're gonna stop the execution of that loop. Therefore, it doesn't really care of what the next words are. It just breaks from the whole loop. All right. So therefore, we just ignore the whole sentence in this case. And we do the same exact thing for the output sentence. Okay, we break off the whole loop if it's not if the word is not in the dictionary. And remember that we're setting both of these to false. Okay, if the word is not in the dictionary, and you're gonna see why we're doing that right now. If keep input and keep output, that means if both of them are true, then we're going to append the pairs to the keep pair list. Okay, keep pairs list. Now, if only one of them is true and the other is false, okay, let's say, then this will not be executed. Okay, because remember, the AND requires both of these to be true in order for its execution. So therefore, what we're doing is we're only keeping the pairs of conversation where every single word of them appears more than 3 times in the whole data set. Okay, or the data set after we've filtered over here. Okay, so here, here. Okay, so right now what we have is only our pairs, the pair of conversations that in which every word of them is appearing more than 3 times. Okay, so that's what we're doing here essentially. And then we're just gonna print the ratio, okay, of what we kept. So we're gonna say trimmed from the length of the pairs, okay, originally the original length of the pairs, and then to the length of the key pairs. So this is the original length of the pairs, and this is the original length of the key pairs, the ones that we kept after we filtered out according to the minimum word count threshold. Okay, and then we're just gonna print the ratio, which is the key pairs divided by the length of the original pairs. So we're just gonna this function just returns this the key pairs, okay, as well, and as print out the ratio. Okay, and then what we're going to do is just call this function. So we're just calling the function here. Remember, we need to pass 3 arguments, our vocabulary object, okay, which we created here. Okay, so here's where we created our vocabulary object, our pairs that we created previously, as well as the minimum count, which is 3 in this case. All right, now we're going to prepare our data. Okay, so we're done with the data pre-processing part, and now we're going to take this data that has been pre-processed and prepare it in a form that suits our model. Okay, so that's what we'll be doing here. Okay, so remember, each word is represented as an index. Okay, remember that we had our word to index in the dictionary, in the vocabulary class. Okay, we had a dictionary that stores the index of every word. So for example, take this as an example. Okay, for 25 represents a word, 858 represents a word, 48 represents a word, and so on. So right now what we have is a 2D matrix of size batch size times maximum length. Okay, So the number of rows is the batch size, and the number of columns is the maximum length. So the maximum length is just the maximum length of the sentence, the longest sentence that you have, which is, if we scroll up, okay, so yep, that's it. Maximum sentence length is 10. Okay, so therefore the number of columns should be 10. Okay, so you have 10 columns that represent the, sorry, here you have 10 columns that represent the maximum length of each sentence. Okay, so the rows that have the sentences that have 10 words, okay, should be occupying every column. Okay, and the words that have, let's say, the shorter sentences, so let's say for example the words that have 5 words only. Okay, so the sentence that has 5 words only. Okay, so the first 5 columns are going to be occupied with these indices, and the rest of the 5 are just going to be zeros. So for example, here we have this sentence of 2 words only, so we only have 2 words and the rest are all zeros. Okay, so that is what we want to reach at the beginning. Now then we want to take this and then we transpose it. Why we want to do that? Because we want to process in batches. So then what we end up doing is just passing this whole row, okay, to a single time step, to a single LSTM. And then each column represents a batch in this case. So then we have the number of rows as the maximum length, okay, which is 10, and then the number of columns is your batch size. So we end up taking one row at a time and feeding it to the time step of the LSTM. Now this will get clear more, maybe it will be more obvious when we're demonstrating the diagram. Okay, so we're gonna have some diagram, okay, and let me show you that diagram, but I'm not gonna explain it because it's not the time to explain it. I'll just show you the diagram, and then when we'll reach to this section or this portion of the code where we'll be explaining the diagram, then we'll speak more on this in depth. Okay, so this is the diagram that we'll be working on. Okay, so for example, you have batch size and maximum length. So we have, let's say, 5 sentences. We're just working with 5 sentences. Okay, so the batch size is 5. So we have these sentences: hello, how are you today? Can you say that? You are good. Well, okay, sure. We have these 5 sentences. Okay, and realize that the maximum length here is 1, 2, 3, 4, 5 also. So the sentences that have words less than 5 end up being a 0 to the spaces left. Okay, so for example, this has only 2 words, therefore we have 3 zeros. We pad the rest of the columns with zeros. Okay, so then we transpose it, so we can have the maximum length times the batch size. So therefore the number of columns here should be the batch size. So one time step here ends up being your batch size. So when we pass this, when we take this whole row and pass it to this time step, the first LSTM, then actually we're passing 5 batches, so 5 different words: hello, can you, well, and sure. Okay, so realize that this whole thing becomes your sentence. Okay, these whole columns becomes your sentence. Okay, and then one row becomes your single time. One row becomes a single time step of the different batches. So that's why we're doing this. That's why we're transposing this. So we have this LSTM. So it's an LSTM composed of 5 time steps. Okay, and why 5? It's because the maximum length is 5. So in our case, the maximum length is 10. Therefore, we should have 10 time steps of the LSTM. Or in other words, we're going to unroll the LSTM 10 times. All right. So at each time step, we're going to have these lengths. These lengths over here. Okay, so for the first time step, we're gonna have 5 words, then we're gonna have 4, then we're gonna have 3, then 2, and the last one we're going to have only 1 word. All right, so that's what we're doing. We're doing all this just to process in batches, just to process our data in batches. Okay, so let's get back to the code. Now we want to define a function called indexes from sentences. So what we're going to do is we're going to take a sentence and get the indices of it. Okay, so let's say we're going to take the first sentence, and this in the first sentence that was in our previous diagram, hello, how are you, then we're going to get the index for hello and for how and for are and for you. Okay, so we're gonna end up with something like this. Okay, a row of indices. Okay, or a list of indices. So let's see how we can do that. We're going to input the sentence as an argument to the function, and then we're going to call from our vocabulary object, okay, from the vocabulary instance that we created. We're going to call the function word to index, and then we're going to pass the words, okay, and then we're going to do that for every word in the sentence that we put here, okay, as an argument. And of course, we're going to split that sentence because we're processing words. Okay, so remember, when we split a sentence, then this will return a list of words. Okay, so we're splitting it here actually by the space, and even if you don't put this, I repeat again, I think I said it more than 3 times, but I'll say it again. So even if you don't put this, it's okay, because by default, this is the parameter. So we're gonna, once we split that sentence, then we get back a list of words, and then for each of these words, okay, we're going to get the word to index from our vocabulary class. Okay, and then we're going to, of course, append the end of sentence token. Okay, so let's go ahead and run this function, and now we're going to test this function. So we're going to test it on pairs 10. Let's see what pairs 10 is before we test. So pairs 10 is, you have my word as a gentleman. And now let's turn this into indices. Okay, so if we call this function and run this, then we get back 7, 8, 9, 10, 4, 11, and so on. Okay, so what happened is each word here got transformed to its unique index. And remember, we have one extra one at the end that represents the end of sentence token. Okay, so this should be 1, 2, 3, 4, and the full stop is 5, then 6, 7, 8. Okay, 8. Now, therefore, this should be 9. So let's see if that's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, correct. Okay, so each word here is transformed to an index plus the end of sentence token. Okay, so now let's go ahead and test some more samples. So we're going to do the exact same thing, but this time we're just going to do it for the input and the output. So we define 2 lists, input and output, and then we loop through the first 10 pairs only, and we append the 0 element, which is the question, and the first element, which is the reply. Actually, there's no need for this. I was just trying something else, so no need for it. So yeah, I repeat again, for every pair and the first 10 pairs. So every pair, remember, has two elements, okay, which is the question and the answer, and the question is element 0 and the answer is element number 1. So we append the question to the input list, and we append the reply to the output list, and then we're going to print the input. We're going to print the length of the input, and then we're going to transform this input, okay, using the indices from sentences function that we defined here for every sentence in the input. So actually, we're just demonstrating for the input right now, okay, and then we're just gonna see what the indexes are. So let's run this, and there we go. Okay, so we have this is the input, okay, print input there. Okay, so you have I told you 2 elements in that list. Okay, the first element is the question and the second is the answer. So here we're appending the first 9 questions, so therefore this should be there should be 10 elements inside. Okay, so here, that's why the length is 10 here. This is the first 9 because remember, the indices start from 0. Okay, so we have from 0 to 9, but actually the length is 10. Okay, because then we're counting the 0. So we have this list of 10 elements. Each element is the input, or in other words, the question. So then what we do is we go ahead and transform them to indices. So we're going to do this for every sentence in the input. So for every sentence here, we're going to transform them to some indices. So remember, this this function returns a list. Okay, so therefore we should have a list for every sentence, or for every question. So for example, let's say if we take the first word, then we have one word here, and the full stop is another, and then we have the end of sentence token. So 3, 4, 2. Okay, realize that the end of sentence token, which is to, is included in every sentence or in every question. Okay, so for example, if we take this, you have my word and full stop. So this is 5, 6, 7, 8. All right, and then we have the end of sentence token 9. So here we should have 9 elements. So yeah, if you count it, you'll see that it's 9, and so on. So yeah, you get the idea. That's what we're doing here. We're transforming the sentence to indices. So that's it for this video. In the next video, we'll be applying the zero padding. Okay. All right. So let's recap what we did last time. We obtained this tensor, which represents the indices of the sentences. So for example, here we have we visualize 10 sentences, okay, and each sentence has the corresponding index of the word. So for example, there, okay, there's the index for the there's the index for the full stop, as well as the index for the end token. So right now what we have is the number of sentences, or in other words, the batch size. Here we're just assuming the batch size is 10, okay? We're just assuming the batch size is 10, so therefore we have batch size times a variable length, because here you see the number of columns are variable. Here we have 3, here we have 10, here we have 3, here we have 5, for example. So what we need to do is we first need to make the columns, the number of columns, consistent. So in other words, our objective is to make this tensor the batch size, so the number of rows times the maximum length. Okay, so this is what we need to do over here. Then we just transpose it, so it's not really a big problem when we transpose it. So our objective is to make the batch size times the maximum length. Therefore, there should be first of all, they should be arranged in decreasing order. So the maximum length, so this should be at this should be at the top, then this, and so on. So they should be arranged according to decreasing order. But actually, we can do a small trick to directly get this tensor, or something like this tensor, okay? So we can get this tensor. We don't need to do this, then transpose it, because there's already a trick or a function in Python to do something like that. Now, this function doesn't arrange it in order. So it will fill zeros, okay, in the empty spaces. However, it will not be arranged according to decreasing length. Okay, so let's see how we can do that. But before we see, I'd like to introduce you to some of the functions that will be very helpful in Python. So let's just ignore this for now, and let's just learn some other things that are essential to understand this. So for example, we have one list called A, okay, and this is going to be A, okay, then we're going to have B, and then we're going to have C. Okay, then we're going to have another list, let's say B, and this is 1, 2, 3. Very simple. Now if we go ahead and zip these two, so if we go ahead and zip A and B, okay, but remember, zip is a generator, so therefore we need to cast it to a list to get the results. Okay, so, okay, sorry for that. This is what we get. So A is with 1, B is with 2, and C is with 3. Therefore, we've zipped these two lists. Okay, so every element with its corresponding element in the other list. So that's what the zip function does. Now, let's say I increase this to 5 lengths, so A, B, C, D, E, okay, and then we zip it again. Let's see what happens. We get back the exact same results. So what happens is D and E are just ignored. It just keeps on zipping until the maximum length of one of the lists, and then it just ignores the rest. So that's what happens. So in order to overcome this problem, we may use another function called zip longest. Okay, so zip longest. However, this is part of the iter tools class. Therefore, we need to call the iter tools object first. Okay, so iter tools dot zip longest. And now if we go ahead and run this, then as you can see, the D and E are not ignored. However, the other element, which is supposed to be in B, is just zero or none. Okay, so that's what that is what the zip longest does. Okay, so this zip or zip longest zips these two lists, okay, and it actually returns an object which is an iterator. I think I said generator first, but it's not a generator; it's an iterator. Sorry. So an iterator, in order to print the items of that iterator object, then you need to loop through it, or you can pass it through a list, like what we just did. Okay. So if let's say this is just for like an extra thing you can put in mind. If we go ahead and just zip A and B, then you can see that this is a zip object, okay? And in order to get the items of that object, we either have to iterate through it using a for loop, okay? Or pass it through a list like we just did before, okay? So by passing it through a list, by passing this iterator through the list, then we get back this over here. Okay, so now that we understand the zip function and the zip longest, let's go ahead and see the zero padding function. Now I'm going to show you in the case of a two-dimensional list. Okay, so let's say, for example, remember this tensor or this list, this 2D list that we have, okay, which consists of the indices. All right, so let me just copy this, okay, and let me just define a new list called A, and let's just paste this over here. Okay, so this is our new list. Now if I go ahead and zip that A, okay, so realize I'm not zipping two lists. I only have one list, okay, but this list is a 2D list. So let's see what happens if we go ahead and zip that 2D list. Okay, so the same thing, we're going to use zip longest, and for of course the iter tools, it's because it's the method of the iter tools class. Okay, and finally we need to cast it through a list. Okay, and we're not forgetting, of course, the list that we want to zip. So in this case, we want to zip the list A. So in that case, we need to put this star over here. Okay, and then A. So let's see what's gonna happen now. You can imagine what's gonna happen right now. Each element of every list inside this big whole list. So you see this big whole list, okay? That is the list that contains the 10 lists, okay? So basically these 10 lists, okay, are all included inside this big list. Okay, so this is a 2D list. So what's gonna happen right now, you can imagine that every element of these lists, okay, that are inside this big huge list, okay, are going to be zipped together. So let's see what happens. If we go ahead and run this, then this is what we get. So 3, 7, 16, 8, 33, and so on. Okay, and realize that by default, the fill value is none. Okay, so for example, here we have 3 with 7 and with all of these, 4 with 8 and with all of these, 2 with 9 and with all of these, and now we don't have anything to zip with 10 and with 6. Okay, so therefore the fill value will be none. So that's why we have a none here and a none here. Okay, so whenever there's no space, then there is a none that is going to appear. Now the same exact thing, if we want to replace the none by 0, okay, there's nothing going to change. However, we only need to specify the fill value equals to 0. Okay, if we go ahead and run this again, oh sorry, oh yeah, we forgot to remove this. Okay, so yeah, let's go ahead and run this, and oh, what's the matter? Oh, these simple mistakes, I forgot to close the bracket again. Okay, so this is what we get. So realize that the none over here is replaced by a 0. Okay, now we can change this to anything we want. Let's say we want to replace it by W. Okay, so W, okay, and there we go, it's replaced by W. So we can play with this value for whatever character or whatever number we want. Okay, in this case we want 0. So now all we have to do, this is the maximum length times the batch size. All we have to do later on is just arrange them in descending order according to their lengths. Okay, so essentially that is what's happening over here. This is the zero padding function. We input the tensor that we want to zip, okay, or that we want to zero pad, which is L in this case, and our fill value, which is by default equals to 0, and we go ahead and just return that whole thing that we just explained. Okay, I told you that we're going to also arrange them. Okay, so we're going to sort them in descending order according to their lengths. So the longest lengths the longest, the sentence that have the most amount of words is going to be at the beginning, and then we're going to sort it in descending order. So we're gonna have this list, okay? So we're going to do a list comprehension. We're going to append this length of every tensor. So this indexes list, okay, which is over here, okay, which is this over here. We're gonna loop through every list of that, okay. So we're gonna loop through this, then this, and then this, and then we're going to take the length of this. All right. So we're going to take the length of every list and append it to that list of that's called length. All right. So this is going to be 3, then this is 10, I guess, 10 or 9, this is 3, this is, okay, I'm not going to count them, but you get the idea. So the length of the list, okay, that's what we're going to have right now. And then if we go ahead and see the maximum length, then we should get probably this one, which is, I think, 10. Yes, 10. Because remember, the maximum length over here is 10. What we defined here, the maximum length. Okay, it's 10. So therefore, our maximum length here also should be 10. So let's go ahead and see if that's correct. Okay, so I'm going to run this function first, and then I'm going to run this function also. Okay, so there we go. The maximum length is 10. And let's actually visualize this list of lengths. Okay, so we should get back 3, 9, 3, 5, and so on, which represents how many elements are in each list. Okay. So that is essentially what's happening here. So then we're just gonna test the function. Okay, so we're gonna run the zero padding on the indexes, and that's what we did actually previously when we were explaining. And then we're going to print the length of this test results. Okay. So as I explained, that this function will return a tensor of size maximum length times the batch size, right? So that's why the maximum length here is now the number of rows. This is wrong, I think. There's something wrong here. Okay, it's a typo. So the maximum length right now is the number of rows. So let's go ahead and see the test results. And as you expect, we're going to get back the exact same thing that we just showed you before. Okay, so here is the maximum length times the batch size. So remember, our maximum length is 10. Therefore, we have 10 rows over here. Our batch size is also 10 because remember, for this sample, we were only getting the first 10 elements, okay, from 0 to 9. So basically, we have only 10 elements, and that's just to demonstrate the batch size. So the batch size here in this case is 10. Okay, so there we go, and we're done actually with most of the functions. We just have, I think, 2 more videos to go until we start to define our model. Alright, now we're going to define a new function called binary matrix. And what this does, it converts your index tensor, okay, the ones that we saw here, okay, to ones and zeros only. So it's going to convert all of this into a binary matrix, which consists of ones and zeros. Now, if I explain why we want to do that now, it's not going to be very clear. You're not going to really understand, okay? So I'd rather wait for this portion of the code where we're going to use this function, where we're going to utilize this function, and then I'll explain why it's useful, okay? But now we're going to implement it, and then we'll understand why it's useful. So we're just going to define a new list called M, okay? And then we're going to iterate through our tensor, which is called L, or our list, sorry, which is called L. So remember, this list contains the tensor values, the index values of each word. So this is the list, okay? And what we're going to do is we're going to start by iterating through every sequence of that list. So for I sequence and enumerate L, now we're using enumerate, so I keeps track of the number of the sequence. So therefore, the first one is this whole tuple over here, okay? So we're going to take this sequence, okay? So then we're going to append a new list because we also want to have a two-dimensional list. We want to mimic actually that whole thing. So remember, this is a list inside the list. This whole thing is some sequences of lists inside one list. So we want to do the exact same thing here, but binary, in a binary form. So that's why when we're going to start a new sequence, we're going to also append a new list. And then we're going to loop through every index or for every token in that sequence, okay? So let's say we're taking this, for example, okay? So this is the sequence, then we're going to append a new list, and then for every token in that sequence, so for 3, 7, 16, 8, 33, and so on, these are all the tokens. So we're going to loop through each one of them, and then we're going to check if this token equals to the pad token. Remember, the pad token is 0. Okay, if we scroll back here to our vocabulary class, then we can say that the pad token is 0. So we're going to say that if this index is a pad token, which is 0, all right, then we're going to append to that list M, okay, in the position I, which is in this case 0, and then 1, and then 2, and so on until your sequence ends. Okay, so the M0 in this case is actually this first list that we appended. So we're actually appending to that first list, okay, either 0 or 1. So it's 0 when it's pad token, and it's 1 when it's not the pad token. That means when it's a normal index. So for example, let's take this. This actually has no pad token, so it's going to end up all 1s. So for example, let's take this over here. All right. So when this is our sequence, and therefore the I should be 0, 1, 2, 3, 4. Okay, so the I should be 4 in this case. So we append a new list, okay, and then for that list, so M4, okay, so for the fourth list, we're going to append either a 0 or a 1. So we're going to append a 0 for 0, then we're going to append the 1 for 4, then this is going to be 0, this is going to be 1, 1, 1, 0, 1, 1, 0. So whenever there's a 0, we're going to append a 0, okay, and whenever there's a 1, we're just going to, whenever there's a normal value, which is not a 0, so basically a non-zero value, then we're going to append a 1. So at the end, we're just going to have this, so we're going to loop through every sequence, okay, and we're going to loop, after we've looped through all the sequences in that list L, right, then we're going to end up with a binary matrix. So let's go ahead and run this, okay, and then let's visualize the results. So I'm going to run this binary matrix function on the test result that we got, which is this over here. Okay, and as you're going to see a matrix of 1s and 0s. So there we go. For this first one, for this first tuple, we have they're all non-zero values, so that therefore that's why we have them all 1s. Okay, for example, if we take this, all right, then all of them are 0s except this middle one. That's what we have here. So that's going to be more obvious why we're doing that later on. Okay, so you'll understand the reason later on. So that is the binary matrix function. Okay, now I have actually some very good news, and it's that most of these codes over here, most of the lines of the code over here are going to be very familiar to what we did before, so it's going to be like a piece of cake to you. So we define a new function called the input variable, all right, and we're going to pass actually our vocabulary object and our list L, okay? And L this time is our inputs or the questions, okay? Which what the first character said, okay? Not the reply, okay? Only what the first character said or the question, okay? So same exact thing, we did this before. We're going to loop through every sentence in L, okay? In that huge tensor or list. Actually, it's a list in this case. Okay, so we're going to loop through every sentence, and we're going to run this index from sentence, okay? And we're going to give the vocabulary object and the sentence. So remember this index from sentence we explained before, and we did test this function actually. So this is going to return this is going to return this indexes batch, all right? And this indexes batch variable is going to represent the index of the words, okay? And we're going to do the same exact thing later on. Right now we're going to take the lengths, okay? And we're going to take the length of every sentence, okay? So we did that again previously. This time we need to cast it to a torch tensor, okay? So we're just converting that list to a torch tensor. That's what we're doing, just casting it to a torch tensor. So the length of indexes for every index in indexes batch. So for every sequence here in this indexes batch, we're going to take the length of it. And then we're going to apply the zero padding function, all right? So this is the pad list, and then finally we just cast this whole pad list to a torch.long tensor. So we're just changing the type of the tensor to long tensor. All right, that's what we're doing over here. Now, pad list is a list, and then we're just casting that list to a tensor, a torch tensor of type long. And then we're just going to return the pad variable and the lengths. Okay, so most of these functions we did explain previously in detail. So if you're not familiar with what's really happening right here, then please refer to the previous videos. Okay, same exact thing here, but this time for the replies. Okay, so for what the second character said or what the second character replied. So exact same thing with nothing much more. Oh, there is actually something more. It's the mask. We just have to run the mask. Okay, the binary matrix function that we did on this pad list. Okay, so this pad list that we got from the zero padding, we need to run the binary matrix to get back the binary outcome. Now remember, this will actually not return a byte tensor. A byte, that means it's just zeros or ones or purely binary. The type is purely binary, not the data that's inside. Okay, so we just need to convert it to a byte tensor because we want it to be a logical tensor. Okay, so either 0 or 1. That's what we do here. Okay, so other things there, we just return all of these. Oh yeah, and the maximum target length. Okay, this time we're not gonna get the lengths, okay, of every sentence. Instead, we're just interested to take the maximum length. Okay, so the maximum target length, and it's the same exact thing. We have this list over here, so we take the length of the indexes for every indexes in this list of indexes batch, and then we take the maximum. And why, you'll also understand later on, because now if I explain it, you also won't understand, and it's not going to be really obvious. So again, I say once the portion of that code comes where we need to use this function, and all of these functions, then I'll explain why we only use the maximum target length and not all the lengths. All right. So we have one more video to go, okay, which is explaining this function. Is something actually very simple, so it's going to be a very short video later on, and then we're going to be ready to define our model. And now what we're going to do is we're going to create a function called batch to train data to prepare our training data. Okay, so this will receive two arguments, our vocabulary object and our batches, our pairs. So remember, the pairs is what we got here. Okay, so after we trimmed the rare words, then we have these pairs. Okay, so this is where we're going to utilize these pairs right now. Okay, so before I start this, I'd like to explain one concept, which is the lambda function, because people, especially with no Python background, can find this confusing. So if you haven't learned Python before, then you obviously you're not going to really understand what this lambda is, okay, and what it does. So let me just okay, if you do understand what's happening, then please feel free to skip some of this video until we finish the explanation of the lambda. So what lambda does is this. Okay, when you have a very short function, let's say I have a very short function, define add, let's say, and I want to add, let's say the input argument is x, so I want to add 1 to this input argument, which is x. So I'm just going to return x plus 1. Okay, so I'm going to input an argument here, and this will add 1 and return. So let me run this, and then let me put some new cells here, and then if I go ahead and run this function add, so add 2, then this should return 3. Okay, if I add 4, then this should return 5, and so on. So realize that this function is very short, and I can actually replace it. There's no need to write this def, okay, and then this return, because it's a very short function. So what I can do, I can replace it with lambda. Okay, so lambda is to specify that this is a function, and then I have to put the input argument inside this parenthesis is x, so I need to put x, and then what I want to return should be separated by a colon. Okay, so I need to put a colon, and then I put what I want to return. So I want to return x plus 1. So this is my input argument, and this is what I want to return. All right, now if I run this, okay, so it tells me that this is a function of type lambda. So now if I give a name to this function, let's say I call this function add, okay? You can call it anything you want. And then I run this, and now if I go ahead and press add 2, then this will give me the same exact results. So this is what the function, this is what the lambda function is used for. So if you can visualize here what's happening in the lambda function, we're giving an x, okay, which is actually one of the pairs from this pair batch, and then we're returning the length of this over here. Now this right here is x0 is your question. Remember, the pair has two lists. One is the question and another one is the answer or the reply. So what we're going to do is we want to sort the questions in descending length. So the first element of this x, okay, which is the pair, is basically the question. Okay, so what we're going to do is we're going to take this question, we're going to split it. Okay, so then we're going to have how many words that does this question contain, and then we're going to take the length of this and we're going to return the whole thing. So we're going to return how many words are in the question. Now then we want to use a sort function. Now when you use a sort function in Python, okay, so then it expects a key and this reverse argument as well as other arguments, but we're just interested in key and reverse. So this is actually dot sort is a built-in function, okay, a built-in method in Python. Okay, so we can directly use it. Now the key is basically what you want to return, or what you want to do, the functionality you want to do. So in this case, the functionality is taking the length, okay, taking the length of the question. Now since we want to sort, then we need to also tell Python whether we want to sort it in reverse order or not. So in this case, yes, we do want to sort it in descending order. Okay, so that's why we need to specify the reverse equals to true. Okay, so then we're gonna have our pair batches sorted out. Okay, so now let's speak about the processing the pairs. So we define two empty lists, input batch and output batch. Now we take this pair batch over here, which is basically all our pairs, okay, which consists of, again, two lists, our questions and our replies. And then for every pair, which consists of the question and reply, the input is going to be the question, which is pair 0, because the first element is the question and the second element is the answer. So the output batch, we're going to append this answer to the output batch. So we're just taking these two empty lists and appending the questions and answers every time. Okay, so therefore at the end, after this finished looping, our input batch would contain the questions and our output batch would contain the answers. And then, as you expected, we're going to utilize these functions. Okay, so the input variable, remember, it returns the padded input sequence tensor, as well as a tensor of lengths for each of the sequence in the batch. And then this also returns the padded targets sequence tensor, padding mask, and maximum target lengths. So we're going to call this function on the input batch. So the input variables for the input batch. Okay, and remember, we also need to pass out not only our input batch, which is the L, we also need to pass our vocabulary object. Okay, so this will return the inputs, okay, which is the pad variable and the lengths. Okay, and then we also run this function, which is the output variable, and this will return all of these three arguments. Okay, now this whole function at the end just returns everything. It returns the input, the length, and all of these. Okay, so that's essentially what's happening in the batch to train data function. So let's run this, and now we're going to test this function. So let's run this. This is the testing code. So we're just going to define this very small batch size of 5 just for testing. Then we're going to run this batch to train data. Okay, so remember, this expects our vocabulary object and our batches. So what we're going to do is we're just going to randomly choose some pairs of these batches. Okay, so random.choice. Random.choice is a function also built in Python. Okay, so remember, here we did import random. Okay, here import random. So that's why that's how we're using the random function, because we did import it actually. So random.choice just randomly chooses some random pairs. Okay. For this element, just doesn't allow Python to store, so it just loops and then destroys it. So it doesn't really matter. You can put I, you can put anything. in range small batch size, which is 5. Okay, so essentially what we're doing here, the whole thing is just giving a list of randomly chosen pairs, okay, from this pair batch, which is our pairs of questions and answers. So again, we're just going to take 5 pairs according to this for in range 5. We're going to take 5 pairs, random pairs, okay, and pass them to this batch to train data. Okay, we're going to store all the outputs in batches, and then we're going to separate them using this normal unpacking. Okay, so let's have a look at the input variable, the target variable, the length, the mask, and the maximum target length. So if I run this, this is what we get. So this is the input variable, all right, and as you can realize, it is sorted in descending order. Okay, so these are the maximum lengths, okay, and then this is the least maximum. Okay, so this only contains 2 words. Now the length for this is 7, because here we have 7 elements. Here we also have 7 elements. Now here we have 6, okay, because here it's just a 0. Here we also have 6 because the last one is just a 0, and then here we have 5 because the last 2 are zeros. Okay, same exact thing for the target variable, okay, and then the mask for this target variable, which is just the binary version of this, and then the maximum target length, which is 10. So remember, these are of shape maximum length times the batch size. So therefore, we'd end up giving all this to a single time step. So this single time step includes different words. Okay, so here we're using a batch size of 5. So here we have 5 different words for a single time step. So we did call the 0 padding after we sorted them out. This is where we called the 0 padding function in the input variable here. Okay, so we sorted them out right here. Okay, pair batch.sort, and then we called the input variable function, okay, which in turn calls this 0 padding function, and then this returns the maximum length times the batch size tensor. And remember, we also need to keep the lengths, okay, because later the elements that have zeros, we're not gonna consider them. So that's why we need to keep the lengths of every batch. Okay, so the length of every batch, which is this whole thing over here. The columns right here is the batches but the batches for all the time steps. All right, because each one of this is a time step. So therefore, for all of these, then we're just taking the batches for all the time steps. So this is the diagram. Now I think you should master this diagram. We have our maximum length times the batch size. So this is exactly what we have here. This is exactly what we have over here. Okay, so this is the indices, and these are the zeros right here. So this thing is exactly the same as what we have in this visualization, in this diagram visualization here. And what we're going to do is we're going to keep the lengths. So here you can see the lengths is the length of this is 5, here is 4, here is 3, here is 2, here is 1. Okay, so we're just keeping the lengths because later we don't want to process these zeros. So at every time step we pass this, we pass the whole row to every time step. So therefore you'd end up with passing this whole time step over here. Passing this whole row as one time step. So this first time step would include hello, can, you, well, and sure. Okay. The second time step would include the second row, so how are you, okay, and then and so on at the end. And of course we store the length of every sentence. So later on, when we have outputs of every batch over here, so then we can just get rid of the zeros that we did not process later on. So that's why we're keeping the lengths over here. Let's start a new section, which is defining our models. So remember, in the intuition videos, we explained the sequence-to-sequence model. So generally, it consists of 2 RNNs. The first RNN is the encoder, and it encodes the input into an encoder state, or in other words, a fixed size feature vector. and then you pass this feature vector to the second RNN, which is the decoder, decodes the information. So you take the output of the first time step, you give it to the second time step, it gives you the output, you take this output, you give it to the third time step, and so on. So we explained in detail actually how sequence-to-sequence models work and how attention mechanisms work also. So make sure to visit the videos in case you missed them. Alright, so remember that each of these is a multi-dimensional cell. Okay, so if we go back to the slides where we visualized the RNN, then this is what we get. So this is our this is what you see over here. Okay, what you see is this is the RNN that you see. Now each of these, remember, is a multi-dimension cell. Okay, so we're just representing it as one cell, but actually it's a multi-dimensional cell. It's actually called the hidden size, as we're going to see later on. So we take this and we unroll it the number of time steps that we want. So let's say we have 5 time steps, so we therefore copy the network 5 times, or unroll it 5 times. So that is exactly what we're doing here. We're unrolling the network, and here, for example, in this diagram, we have 4 time steps, and in this we also have 4 time steps. Okay, now we're going to see how many time steps do we need for both the encoder and the decoder, as well as many other crucial concepts. So we're going to learn them all here. Okay, so first of all, before we begin, we'll be using here a GRU, which is a gated recurrent unit. Now it's another variation of the RNN. So it actually was developed after the LSTMs. Okay, it's new. I think it was developed in 2013 or 14 or 15. I really don't remember, but it was recently developed. As far as I recall, it was 2014 when they introduced the GRUs. Now they proved that it can achieve better results than the LSTM. Okay, so what they did is actually they combined. This is in a nutshell what they did, of course. Okay, they combined the hidden state and the cell state. So there's only one output. Now the LSTM outputs, you have the hidden state output and the cell state output. Okay, so there's actually 2 outputs. Now the GRU only outputs 1, which is the hidden state. Now this, of course, includes information about the memory because it also includes the cell state. So they just merged the cell state and the hidden state together, and actually this is like much easier rather than having 2 outputs. Okay, but still LSTMs are widely used. Until now they're widely used. Okay, so GRUs, they proved to have better results than LSTMs, but however LSTMs still give amazing results. Now for me personally, I still prefer using LSTMs. Alright, so let's go ahead and start with our with defining our encoder class, okay, which is basically represents the encoder RNN. Now there's also one thing here. We're going to use a bidirectional GRU. Okay, so that means there's 2 directions. The one, let's read here. So there's 2 independent RNNs. One that is fed the input sequence in normal sequential order. So we feed the input sequence in the normal order, okay, and then another one, okay, which is independent of the other one, gets fed the input sequence in reverse order. All right. Now, if you do not want to use the bidirectional GRU, then all you have to do is just remove one very small thing, which is the bidirectional equals to true. You just have to remove this if you don't want to use a bidirectional GRU. All right. So these are the steps that we're going to do. First, we're going to convert the word indices to embeddings. So remember, in the intuition video, we had a section for word embeddings. So that we're going to implement that actually right now. Then we're going to pack path sequences. Okay. Now this one I'll be explaining in detail with a diagram later on. I'll be explaining pack padded sequence and what they really do and why we need them. Okay. I really had actually. I really spent time creating diagrams for you guys so you can understand everything in detail. So we'll be visualizing one of these diagrams that I drew, which is also about padded sequence. And then we're going to forward pass through our gated recurrent units. Then we're going to unpack this padded sequence. And then finally, we're going to return the output and the final hidden state. Let's begin by defining our encoder class. So we're going to name this class encoder, and we're going to inherit from NN model. Now, NN.model is this model that includes all of the structures and the functionalities of neural networks. So, for example, the linear layer, the convolutional layers, the pooling layers, for example, the RNN, the recurrent neural networks layers, and all of these, they're all included in the NN.model class. So we need to inherit from the NN.model class. And this is how we do inheritance in Python. Okay, then we need to start by defining our methods. Okay, so the methods for that class. Now, we all, in case you're not familiar with Python, or you're not really familiar on object-oriented programming in Python, then this is how we define a class and its methods. So we have this first method, which is the initialization method, and it's used to initialize the class. Okay, so we need to specify init, okay, that stands for initialization, in between two underscores. Okay, and then we need to pass self. Now, self refers to the object that we'll be creating later on. Okay, and this needs to be an argument for every method. So we're telling Python that we want to associate this object to that method. Okay, this object to that method. So this function is used to initialize the class, and we need to have it basically for every class. So what we want to initialize, okay, the arguments of this initialization of the class are these. So we first have our hidden size. Now our hidden size, I told you before, is the dimensions of the RNN cells. So how many cells are there? This is the hidden size. And if we go back to this diagram, then this is the hidden size. All right, okay, if we're just considering a normal neural network, then this is the hidden layer, okay, and the hidden size is how many neurons we have. Now, it's the same thing in RNNs, okay, so we flipped it here, so this is still the hidden layer, so this is still the hidden layer, and this is the hidden layer. So this is what the GRU, this is our GRU. So the dimensions of this is how many hidden neurons we have, okay, so this is the hidden size. A lot of people actually, a lot of students I've seen that don't dive deep into how RNNs work think that it's just one cell, okay, or one neuron. So just be careful on this thing. Remember, it's a multi-dimension neuron. Or just understand the very simplest, in very simple terms, you have this normal neural network. This is your hidden layer. When we flip it to become an RNN, then, okay, we're just doing this for visualization, okay? So this becomes your hidden layer, and then we represent it as a multi-dimension neuron. So this becomes your hidden layer, and therefore that's why you have multiple hidden neurons, or hidden size, or multiple RNN cells. And this is what the hidden size is. So our hidden size in this case is how many neurons we have in our hidden layer, okay, or how many RNN cells we have. Now, embedding is, as we're going to see later, our embedding layer, and which is responsible for converting the index to a dense value, okay, sorry, a dense vector of values. So so we also explained this when we were talking about embedding, word embeddings in the intuition videos. So this takes an index and converts it into a vector of dense values. Okay, so each index, or in other words, each word, will be represented as some values. Now, the number of layers we're going to use is one layer for the encoder, all right? And we're going to initialize a parameter, which is dropout. Now, in this case, we're just gonna by default set it to 0, and later on, if we want to set a dropout value, then we just set it, okay? But right now, we just give it default as 0. And then we use a super function. So again, if you're not familiar with object-oriented programming in Python, super is the method that is responsible for inheriting all the methods and attributes of the parent class, which is in this case the NN.model class. Okay, so we use the super function. We need to pass two arguments. our current class, which is the encoder RNN, and our object, which is self, and then dot init. Okay, so whenever you're using classes in Python, okay, and whenever you're using PyTorch, then actually you need to implement your neural networks in classes. So definitely you'll be using this one. Okay. Now you don't have to, but I mean, why would you make your life hard if you don't want to use classes? Classes really arrange your work. If you don't want to use classes, then you're just going to make your life 100 times harder. Okay. So now let's start with initializing our variables, class variables. So we initialize the class in Python. We initialize the class variables inside this initialization function. So the attributes or the class variables, we need to associate each one of them to self, because we're associating it to the object. Okay. So we have the number of layers, okay, which will be set by the user here, the one that creates an object of this class, okay, which is us, of course. So yes, the number of layers is set here to 1 by default. So therefore, we just if the user if we later on when we're creating the object, if we did not specify the number of layers, then it will default to 1. So this is the first attribute. The second attribute is the hidden size. Now, why we're defining them as class variables is because we're going to need to use them here later on. Okay, that's why we're defining them as variables. And then the embedding is just our embedding layer. Okay, and now we need to initialize the GRU. So if we go to the PyTorch documentation, then we can see this is the torch.mn.gru. Okay, so this is the GRU that we are using, that we're going to use. So let's see the parameters. We're going to need the input size at the beginning, which is the expected features. Okay, and then we're going to need the hidden size. I explained before in detail what is the hidden size. Okay, so please go back to if you still don't get what's the hidden size. Then the number of layers, then the bias, batch first, dropout, bidirectional. Okay, now we're not going to use all of them, so let's see what we're going to use. So first of all, the input size. Okay, if we go back here, then we can see that the first one is the input size, which is the number of expected features in the input X, or the number of input neurons, in other words. So in this case, the number of input neurons is the size of your embedding. Okay, I told you if you go back to the intuition videos, then you can see that the size of the embedding, okay, is how many values we represent each word. So this is going to be the number of input features, and in this case, we're just going to keep the word embedding the same as the hidden size. Okay, so if we're using a hidden size of 5, let's say, then the word embedding size is also 5. Okay, so we're just going to keep things simple, but you can change it. So we're going to define the number of input features as the hidden size. Okay, then the hidden size is just the hidden size. So the hidden size here is how many neurons we have in our hidden layer. Okay, or the number of RNN cells. Again, I say the number of layers here, which is by default 1 if we do not specify. Okay, so this is the number of layers over here, which is also specified by us when we're going to create the object. And then let's see what we have. Dropout. So this is the dropout parameter. Okay, so we're going to set the dropout to 0 if the number of layers equals to 1. Else, if the number of layers are more than 1, so let's say we're using 2 layers, then we're going to set the dropout as this parameter that we used when we were initializing our class. Okay, so dropout is either 0 or 1. 0 if the number of layers is 1, and we're gonna have no dropout if our number of layers is 1, and we're going to have a dropout if the number of layers are more than 1. And then bidirectional equals to true. So I told you this is where we switch between bidirectional or non-bidirectional. Okay, so this is if true, then it becomes a bidirectional GRU. Okay, so if you don't want to make it a bidirectional GRU, you just have to remove this. Okay, so now let's go ahead and define the forward function. Now the nn.model already has a forward function. So what we're doing here is we're overriding the forward function. Okay, so this is actually the function responsible for the forward propagation. Okay, so let's see what input arguments we need. We need the input sequence, we need the input length, and we need the hidden. Okay, this is the initial hidden state. So here I specified for you, I've written for you all the arguments and the respective shapes. So the input sequence is the batch of input sentences, which is of size maximum length times the batch size. This is returned previously in the data preprocessing part. Okay, so if you still miss that, then you can refer to the data preprocessing part when we returned a batch size of 10, as I recall, that specifies some of the examples of the input sequence. Okay, so the shape of this is the maximum length times the batch size. The input length, okay, we also returned this previously. So it's the list of sentence lengths corresponding to each sentence in the batch. The hidden state is of shape number of layers times the number of directions. Now, in this case, the number of directions we have is 2 because we're using a bidirectional RNN. Then the batch size, then the hidden size. So if we go back here, we can actually see the shape that is required. So the hidden state, okay, which is over here, the H0, as you can see, the shape that we need is the number of layers times the number of directions, batch size, and the hidden size. Okay, and the input is of shape sequence length times the batch times the input size, which is not going to be this case. Okay, so it's not, we're going to have our input as our maximum length times the batch size because we're going to use a padded sequence later on. So if we go ahead, we can see that the input can also be a packed variable length sequence. Okay, so it doesn't need to be like this. We can also have the padded sequence, and this is what we're going to use. So we start by running our input sequence, okay, which is again of shape maximum length times the batch size. We run this through our embedding layer, okay, and then we run a padded sequence, okay, and in the padded sequence we're going to specify the embedded sequence over here that we got and the input length. Now the next video will be specially for padded sequence, for understanding padded sequence. So don't worry right now, okay, in the next video we'll be explaining in depth about padded sequence. So after we've got our padded sequence, then we run this padded sequence through our GRU, okay, and if we go back to the documentation, then we can see that the input, okay, of the GRU has to be our input sequence and our H0. Now our H0 is the hidden, okay, state that we defined here, or we set here by the argument, one of the arguments of the forward function, okay, and is of shape number of layers times number of directions times the batch size times the hidden size. And our input sequence, okay, is the padded sequence. So this is the result of the padded sequence, and we're going to pass this result to the GRU as well as the hidden state that we defined here. Now by default this is none, okay, so later on we're going to see if we put any hidden state, if we initialize the hidden state, then we're going to need to put it here, but by default it's none. So these are the inputs, okay, the padded sequence and the hidden state, okay, and both of them are here. And now this returns the outputs and the hidden. So as you can see, the same exact thing as the documentation, it returns the output, okay, and the hidden. Now we're passing a padded sequence, so therefore the output is a packed sequence also, okay, and the HN is just of shape number of layers times number of directions times the batch times the hidden size. Okay, so let's understand why the outputs have a shape of sequence length times the batch times the number of directions and times the hidden size, and why the hidden state has this shape over here. So let's begin with the output. The output has a shape of sequence length times the batch size times the number of directions times the hidden size. So if we go back to this diagram, then you can see that the output of every one of all of the time steps is basically the sequence length, right? So that is why the output starts with the sequence, okay, sequence length, okay, because it's the output of all the time steps together. And then the batch size is depending on how many batches we're using at our inputs. And finally, the number of directions times the hidden size. Now, in bidirectional GRUs, okay, remember that we're using 2 independent RNNs, so that's why we need to multiply it by 2. And the hidden size is just the last features, or sorry, the output features of the RNN. Okay, so it outputs some features of size, hidden size, or basically, again, I repeat, how many number of neurons in the hidden layer. Okay, that is what the hidden size is, or in other words, how many RNN cells. I think after this explanation, I've repeated this actually many times, so I think there should be no more doubts about the hidden size thing. And for the hidden state, okay, we have number of layers times number of directions. So let's say we have one layer only, so the output of this layer, okay, will be the hidden state is actually this state from here, okay, that is going to be passed to the next time step. But actually the hidden size that is returned, if we're going to read here, the hidden state for the last time step. Okay, so the sequence length is the number of time steps. So basically, let's say you have 10 time steps, or 10. Your sequence length is 10. So t equals 10 is basically the hidden state from the last time step only. So basically, what's happening here is we're getting back the hidden state from this time step only. So the number of layers, that's why number of layers is 1, okay? Because we're only getting back from from this last time step. So if we have 2 layers, then the output, the first dimension of the output, which is the number of layers, should be 2, because we're using 2 layers. Okay, so the 1 from each of the final time steps. And if we're using bidirectional RNN, then we need to multiply it by 2. Okay. This is times the number of directions, and then the batch and the hidden size, I think there's no doubt on them anymore. Okay, then finally what we do is we do the opposite of the backpacked sequence, which is the pad-packed sequence. So we return it back to the original form, okay, and then we sum the bidirectional GRU outputs. Now remember, the GRU outputs, we have 2 independent GRUs working, so we need to sum their outputs together, okay? So this is a diagram I drew to illustrate to you what's really happening over here. So the input to our GRU, okay, is the input size over here, is the number of input features is 6, the hidden size is 20, and the number of layers is 2. Okay, and then I'm just going to create a random input. So the input, remember, should be of size sequence times the batch times the inputs, and then I'm going to initialize the hidden state to a number of layers times batch times hidden. Okay, and I'm just assuming that the number of directions is 1, okay, for simplicity. And then I'm going to run this through the GRU, and then I'm going to print the output.shape as well as the hidden state.shape. And as you can see, this is the shape of the output and the hidden state. So the output is of shape sequence times batch times hidden, and the hidden state is of shape layers times batch times hidden. Now this is our input. Okay, so this is the number of input features, which is the number of columns here. We have 1, 2, 3, 4, 5, 6 columns. Okay, so this is exactly what's written here. So what's gonna happen is that each of these columns, which represent the batch size, because here you can see the input is of shape sequence times batch times input. So the channels right here, these channels are which is the sequence. Okay, we have 5 channels over here, and each channel consists of 3 rows, which is the batch size, and also 6 columns. Okay, this is the 6 represents the features of the input. So at each time step, we're going to pass these. Okay, so we have 6 neurons at the inputs, and we're gonna pass this value, okay, to each neuron, and we're using also a batch size of 3, so we're passing 3 values actually. And this is the first layer, this is the second layer. So the output, now I want to demonstrate the difference between the output and the hidden. Okay, so the output is basically all your time steps together, okay, and then the batch and then the hidden size. So I repeat, the hidden size is actually the number of output features of this RNN, okay, or in this case we're using a GRU. So as you can see here, how many channels we have is basically the number of time steps, which is here in this case we have 5 channels, and that's why we have 5. Okay, this is the output. This is the output from all of the time steps. Now the hidden is just the output of the final time steps. Okay, so if we have one layer only, then we only have this. But since we have 2 layers, then we're going to consider 2 of the final time steps. So therefore the number of channels here is 2. Okay, and this represents the number of layers. So 2 times the batch times the hidden size. Okay, I hope that clears out all the doubts. Okay, so let's continue our code. Now, so we go ahead and sum the outputs of each of the independent GRUs. Now this, if you're not familiar with Python, means all the elements. So for in this case, all the channels, this means all the rows, and this means the columns from 0 until the hidden size. Okay, so let me demonstrate that very fast. If we go ahead and create a torch tensor, so first I actually cleared all the outputs, so I need to import torch again. Okay, and then if we go ahead and create a tensor of shape, let's say 5 times 4 times 3. Okay, so therefore now if I go ahead and see and visualize my A, okay, then this is what we have. We have 5 channels, 4 rows, and 3 columns in every channel. Now if I go ahead and type all the channels, so I want all the channels and all the rows in column number 2. Okay, or let's do it for example from 0 until 2. Okay, so this is what I get. Okay, all the I've included here all the channels, which is the 5 channels, and in each of these 5 channels I've included all the rows, so we still have 4 rows, and the columns I've just taken from 0 to 2. Now 2 is the upper bound, so it's exclusive, we're not including it, because in Python the upper bound is not included, so we only have 0 and 1. Okay, that's what we get. So exactly, we're doing the same exact thing over here. And here is just the hidden size. So this is the last dimension we stopped from here. Okay, so we're gonna pick off where we stopped here, and then until the end. Okay, so just a dot without anything just the column after without anything after this column means until the end. All right. So here we're taking from 0 until the hidden size, and then from the hidden size until the end. And then finally we just return the outputs and the hidden state. Okay, so the outputs is of shape maximum length times the batch size times the hidden size, and the hidden is of shape number of layers times 2, batch size, hidden size. Okay, so that's it for the encoder. In the next video we'll be talking about the decoder. Alright, and it's going to be in fact very easy, because if you follow the tuition lectures, then you probably have a very clear idea of how this whole thing works. So it's just an operation of multiplication, addition, and so on. And actually we also have a diagram to demonstrate how it works. Now we're going to talk about padded sequence in PyTorch and what it does and why we need it. Now you're going to encounter padded sequence a lot, especially when you're working with RNNs and LSTMs. So any problem or any topic you have that includes RNNs, LSTMs, GRUs, or any of these variations of recurrent neural networks, then most probably we'll find the padded sequence function there. Okay, now let's see what this function does. So I have a tensor of shape batch size times the maximum length. Okay, so just imagine that we have this tensor which is which has a shape of 6 times 7. Now 6 is the batch size, 7 is the maximum length. So it's the maximum a maximum of 7 words per batch, meaning that the maximum sentence has only 7 words. So this is our A tensor. Let's look at this A tensor. This is one sentence here. Okay, so this is the batch size. So here we have 6 sentences, and these sentences have variable lengths. So this first sentence, for example, has 7 words. The second sentence has 7 words. Now the third sentence, as you can see, there's a 0. So there's only 6 words, so the lengths represent the number of words in the sentence, or the sentence length. So 6, and then we have 5, so there's 2 zeros. Then we have 4, so there's 3 zeros, and finally we have 2. So all of them are zeros except for the first 2 words. So you can, for example, imagine the last sentence as thank you. Okay, so some sentence with 2 words only. Okay, so we have this tensor of shape batch size times maximum length, and also we have this list, which is length, and it represents the length of each sentence in this tensor A. So if we go ahead and sum all of the elements inside this tensor length, then we get 31, which represents how many words do we have inside this A, not considering the zeros. Okay, so it's just how many words we have here. So if you're considering the pad as a word, then it ignores this pad. Okay, so in other words, it's just the sum. It's just the sum of how many words do you have in your sentences. So if we go ahead and run a pack-padded sequence on this tensor A, okay, now pack-padded sequence, we need to give 2 arguments. The first argument is the tensor, which is A, and the second argument is the length of the sentences in that tensor, which is length. Okay, so this is the list. Now, batch first equals to true is not compulsory, but if you'd like your output to be if you want to give your inputs in this shape of batch size times maximum length, then you need to put batch first equals to true. Now, if your input is not in shape batch size times maximum length, so let's say it's of shape maximum length times batch size, okay, as we have in our chatbot tutorial, chatbot videos, when we were implementing the encoder, so then you do not need to put batch first equals to true. Okay, but I just keep batch first equals to true because it's easier to understand here. So if we go ahead and look at the documentation of pack-padded sequence, then this is what we have. All right, so as you can see here, if batch first equals to true, then inputs of batch size times t are expected. Now, what is t? It's the length of the longest sequence, which is basically the maximum length. All right, so that is what batch first equals to true means. So when you run this to the pack-padded sequence, this is what happens. As you can see that each LSTM receives not the sentence, but a batch of words. Now, these words are from different sentences. So let's see what the first LSTM receives. Okay, first of all, it returns 2 tensors. So the first tensor is the words, and the second tensor is the batch size at each LSTM. So the first LSTM receives a batch size of 6. So you take the first 6 from these tensors. So we take 0.9860, we take this, and this. All of these receive it. All of these get fed into the first LSTM. Okay, so basically, if we go ahead and look at what are these words, they are the first words of every batch. Okay, so 0.85, 0.85, 0.45, 45. This one is here, this one is here, and this one is here. Okay, so what we took is the first words of every batch. Okay, and fed it into the first LSTM. The second one also 6. Okay, so we go ahead and take the next 6, which are all of these. Okay, so we have 1, 2, 3, 4, 5, and 6. Sorry, from here 1, 2, 3, 4, 5, 6. Okay, so we also have 6 words. Well, now what are these 6 words? If we go back again, we see that there are also these words in every batch. Sorry, the second word in every batch. Okay, now the second one is 5. So as you can see, it's all of these words. Okay, then 4, it's all of these words. So it's just ignoring the zeros. So it's feeding the LSTM at each time step. It's feeding the LSTM the words without the zero padding. Okay, and that's what's really happening. The last one, for example, is just 2. So it's just feeding these 2 these 2 words over here. So in essence, what this does, it batchifies your input. Okay, so it ignores the zero padding. All right, so this makes the calculation more efficient, of course, and so you input to your LSTM different batch sizes every time. Okay, and actually that is why PyTorch is powerful. That is one reason, is because it uses dynamic computation graphs. This is where you can finally understand how dynamic computation graphs are very useful. So what we're doing here is, as you can see, at each time step, we're changing the number of inputs. Okay, the batch size number on the input of the LSTM. So that is just like a note to take. So that is how padded sequence work. And now that you've understood how padded sequence works, then you've understood how our sentences were fed in our encoder on the chatbot, and their output. Okay, so their output is also the same thing, these batch of words, okay, without considering the zeros. Now we're going to start speaking about the decoder, and we're going to see how we build it with attention mechanism. So remember how the decoder works, okay? So it generates the prediction, then it passes this prediction to the next GRU, and then the next GRU predicts the second prediction, and the second prediction gets passed to the third GRU, and so on. So I repeat again, this happens only during test time. Now during train time, if you're using teacher forcing, then the same thing happens. Okay, we'll talk about teacher forcing later on. But now just get the basic concept of the decoder. That's how it decodes the information. So we're going to apply this decoder with attention. Now remember attention, we explained attention in the intuition videos, but I repeat again. So it allows the decoder to pay attention to specific parts of your inputs when generating the next word. So basically, if you're using the decoder without attention, then you'd feed your whole content or the whole encoder state that represents the global context of the encoder. So this gets fed into the decoder for all the time steps, and based on only this, then you generate the next words. However, with attention, you pay attention to or you focus on a specific part of your input when generating your word. So you have an additional input coming to your decoder. Okay, and if we go back to our slides where we explained the attention mechanism, then this is what we see. Okay, now I can't show the rest of the screen on the right because this is much bigger than the recording screen. So, but you can see the essence of it, how this thing works. Okay, so you see that the attention mechanism depends on the encoder output as well as the previous hidden state of the decoder. Okay, so that is how attention is generated. So you look at the decoder current hidden state, okay, as well as your encoder output to generate the attention. Okay, so this diagram might confuse you, especially if you're a beginner. So you might not understand what's really happening here, even though it's simple, but somehow it might confuse some people. So I've simplified this and I drew it in another diagram, and actually we're going to look at the other diagram and implement our decoder using by referring to this diagram. Okay, so we're going to refer to the other diagram, which I'm going to show you later on, to implement our decoder step by step. And also remember the attention operation. So this is the attention operation that we discussed also in the intuition. So the first one is just a dot operation. Okay, so you just multiply the hidden state and the encoder output together. So this is actually exactly what we have over here. Okay, so it's just an element-wise multiplication. And the other one is you pass your encoder output through a linear layer and then you multiply it with the hidden state, which is what we have over here. So we're passing the encoder output through the linear layer, and then we're multiplying it with the hidden state. Okay, and this is the third one also. So this is the same concept. We're just concatenate this time the hidden state with the encoder output, then we pass it through a linear layer, and then we pass it through a ton etch layer, and then we multiply it with a vector. Okay, so we won't be implementing the last two. We'll only be implementing this one, which is the simplest one, which is the multiplication part. You only multiply the encoder output with the decoder hidden state. This is what we'll be doing in the attention mechanism. Okay, we'll be doing an element-wise multiplication between the hidden state and the encoder output. Okay, now let's go ahead and start writing the class of the decoder. Okay, so here we have, first of all, we're going to implement attention only. Okay, so we're doing this using a class called attn, which stands for attention. And again, we're going to inherit from the torch.nn.model. Okay, now the initialization of this class receives two arguments. The first argument is the method of attention. So in other words, the attention operation that we just showed you here. Which one do you want, dot or general or concat? And you also need to pass the hidden size in case you want to use it. Now that we define a method of this class called the dot square, now it's just an element-wise multiplication between the current decoder state and the encoder output. Okay, and then we sum across the pixels. So that is why we need to pass two arguments here: the hidden, okay, which is the decoder output, okay, at a certain time step, and your encoder output. Okay, so then you just multiply them together, and then you sum across the pixels. Okay, now we're going to see later on why we put dimension equals to 2. Okay, this is just the function, the general function, but now in the forward function, we're going to observe step-by-step outputs and see why we did all of this. So this is the forward propagation. So this is how the attention is calculated. Okay, when you initiate this class, okay, or when you create an object of this class, then these methods run. Okay, and then when you run this object, okay, and then this is what gets executed, the forward function. So let's see how the forward function works. So if you refer to this diagram, then this is the part we're going to implement. We're going to implement the attention mechanism. Okay, so again, what does it receive? Let's see. The first thing it receives is the encoder output. Okay, we said before that it receives the encoder output. Now remember, the encoder output, we explained this also before in depth. So if you don't know why the encoder output has a shape of maximum length times the batch size times the hidden size, then please refer to the previous videos. Now this is the encoder output. So it has a shape of maximum length times the batch size times the hidden size. Now the decoder output this time has also a length of 1 times the batch size times the hidden size. It's the same exact thing, okay? So it's the same exact thing, but right now the sequence length is 1 because we only have one GRU. So we're implementing one GRU at a time. Okay, that's why we have a sequence of 1. Okay, same thing, 1 batch size times the hidden size. So these are the two shapes of the inputs of to the attention mechanism. Okay, so we have the encoder output and the decoder. And now, okay, so as you can see here, hidden of shape 1 batch size times the hidden size. I repeat again, 1 is because you only have one GRU, okay, or the sequence length is 1. You have one time step. And then the encoder output is of shape maximum length times the batch size times the hidden size. So we got this encoder output previously from the encoder class. Here, as you can see, we're returning the outputs. Okay, so this is where we're going to use this outputs returned. So we start by multiplying them together. So I told you that these two inputs get fed into the attention mechanism, and this attention mechanism is going to be the multiplication, the element-wise multiplication, which is this one over here. So we're just multiplying them together. So that's why we need to call this function, which is dot score. Okay, so we also need to associate it with self because it's an object of the class, as we also explained before, in case you're not familiar with object-oriented programming in Python. So we run this dot score, and remember what we need to pass: the hidden and the encoder output. So it's the same exact thing, hidden, encoder output. We pass them and we get back our attention energies. Now this, when you multiply them together, okay, when you multiply 1 times batch size times hidden size with the maximum length times the batch size times the hidden size, remember you're doing an element-wise multiplication. So this will automatically be extended to fit max length. Okay, so therefore you'd have a final shape of maximum length times the batch size times the hidden size. So let me write it here actually. So if we go ahead and take our hidden, okay, the decoder output, and multiply it with this guy over here, which is the encoder output, we get back this exact same thing. Okay, yep, we get back a tensor of shape maximum length times the batch size times the hidden size. And then we sum across the second dimension. Now the second dimension is this over here. So we sum across the hidden size. Okay? So we get maximum length times the batch size times the hidden size. And now we sum across the hidden. Oh, sorry. Okay, so let me actually show you what summing across this dimension means. Okay, so if I go ahead and okay, first let me import torch. And then let me create a random tensor. So torch dot rand n. Okay. Let's have maximum length of 5, let's say, batch size of 3, and hidden size of 7. Okay. And then we're gonna see that A. So this is what the A tensor looks like. Okay. So we have 5 channels. In each channel, 3 rows and 7 columns. Now, if we go ahead and run torch.sum, okay, torch.sum A across the second dimension, so dimension equals to 2, this is what we get. Okay, so okay, we'll need to see the A so we understand what's really happening. So this is the A, okay, and this is the sum across the hidden. So the sum across the hidden means the sum across the columns. Okay, so for every row here, okay, so for every row, we're summing all the columns. So the sum for all the columns in this row, then the sum of these, and then the sum of these. And that's why you have 3 columns in every row. So if you go ahead and sum all these up, then you'd get 1.1863. Okay, so that's what we're doing. That's what's called summing across the second dimension. So summing across the columns, which are here. So you'd sum all these up. And that is why actually you get back a batch. A shape of maximum length times the batch size only. Okay, so when you sum across the hidden. So this is when we perform torch.sum dimension equals to 2. Okay, so let me delete this first. Okay, we don't want to get things too messed up. So then we need to transpose this maximum length times the batch size tensor because we want to pass it through a softmax function. Okay. We want to find the softmax scores for every batch size, and that's why we need to transpose it right now. So what we do is we use the .c, and .t means transpose this matrix, so it just turns it to the batch size times the maximum length. Okay, the opposite dimension. It just switches or swaps the dimension, so you get back a batch size times the maximum length. And then we run the softmax. Okay, so what we do here is we run the batch size times the maximum length tensor to the softmax. Okay, so you can use the f here as the shortcut. We imported torch.n and .functional as f. So f has the softmax, the relu, and all of these other operations. Okay, so you can use them directly. So f.softmax, and then we need to pass the attention energies, which is the transposed matrix over here, which is of size batch size times the maximum length. And then we need to tell Python that we want the softmax across the first dimension, and this is the first dimension. Okay, so it's across the columns this time. Okay, so we want to take the softmax across the columns, meaning we want the softmax for every row or for every batch size. So for every sample, we want to find this softmax. Okay, so once you find the softmax, you get back a tensor of shape batch size times the maximum length, because you didn't change any shape in the tensor, you just applied the softmax. Okay, and then we just unsqueeze at the first dimension. So the first dimension is here, okay, after the batch size. So unsqueeze 1 means adding a dimension here in this place. So that's why we get back batch size times 1 times maximum length, and that's gonna be clear later on why we did this. Okay, so just before we end, let me show you actually the softmax, something that deals with the softmax output. So if we go ahead, okay, first we need to import torch.nn.functional as f, okay, and then if we go ahead and create a tensor called a, so torch.random, let's have a batch size of, let's say, 5, and then a maximum length of 7. Okay, so this is our batch size times the maximum length. And then if we go ahead and run this, and then we visualize what the A is. This is our A. Okay. Now if we go ahead and apply a softmax, so f dot softmax, and then we pass A, and then the dimension equals to 1. So we want to take the softmax across the columns. Okay, so for every batch we want to find the softmax for every row. Okay, so let's see what that outputs. There we go. This row over here, okay, if you sum all of these, if you sum them together, then you'd end up with 1. Okay, so summing all the columns here in the first row, you'd end up with a 1 right now. So if we actually go ahead and save this as B, okay, and then so B is the same exact thing, and then if we go ahead and index that as B0, then we get back the first row, okay, and then the sum of this first row, okay, is going to be 1, right? So that is proven and demonstrated in this example. Okay, so what we're doing here, we're taking the softmax across the first dimension, which is the maximum length. Okay, so for every batch, for every sample, we're finding the softmax outputs. So we implemented the attention, and now we're going to use this attention to build our decoder. So again, we're going to look at the diagram and follow the diagram step by step. Okay, so let's go ahead and jump to the diagram. So there we go. This is our GRU, okay? And this is the data we have. Remember, our data is of shape maximum length times batch size, okay? This is the thing that we did in the data pre-processing part in section 1 and 2, okay? So the maximum length, which is the number of rows, is basically the sequence length, or how many time steps your GRU includes. How many times did we unroll this GRU? So if we're going to feed in this data one time step at a time, or in other words, one GRU at a time, that means we need to take the first row. Okay, so we need to take row by row and feed them to the GRU. So that is what we're doing here. We have this the tensor of shape maximum length times the batch size, and we're going to feed them. We're going to feed the data one by one, so row by row to every GRU or to every time step. So that's why we take the first row, okay, and we end up with 1 times the batch size, okay? So that will happen at every time step. You take the first row, then you take the second row, then you take the third row, and so on. So at every time step, the input shape going into the GRU is 1 times the batch size, okay, which is 1 row of this tensor over here. And this returns same thing. So if we go back to PyTorch, the documentation over there, okay, we can see that the outputs that are returned, you have your output of shape sequence length times the batch size times the number of directions times the hidden size. Okay, now remember our sequence length is 1 because we're only using 1 time step, okay, 1 cell at a time. Then we have our batch, and finally our hidden size. If our number of directions is 1, that means if we're using if we're not using a bidirectional GRU, okay? If we're using a bidirectional GRU, then we need to multiply it by 2. Okay, but for simplicity, just imagine that this is 1 right now. So you have 1 batch hidden, okay? This is your output. And your hidden is the shape of your last hidden state, okay? So the shape of the last the last GRU cell, okay? In this case, it is the same GRU cell because we only have 1 GRU, okay? So we're not working with a sequence of GRUs. We're only working with 1 GRU at a time. So therefore, the hidden the hidden state of this is the hidden state returned by this GRU is for t equals to 1, okay? Because we're using 1 time step at a time. So this cell returns both the outputs and the hidden state, okay? And again, I repeat, if you had multiple GRUs, then the output of the HN would only be the last hidden state. But since we're using now only 1 GRU, then the hidden state is just for this GRU that we're using. Okay, so the output is of shape number of layers times the number of directions. Again, imagine number of directions is 1. So we have number of layers, batch size, hidden size. So we have number of layers times number of directions, batch size times the hidden size. Okay, so we understood now how the GRU works. Yeah, there's another thing. We need to also give another input in addition to our data. Okay, we need to also give the encoder output. This is only at the first time. Okay, because remember in sequence to sequence models, then the output of the encoder, okay, which is the last layer, sorry, the last hidden state of the hidden state of the last GRU, okay, which is of shape number of layers times number of directions, batch size times hidden size, is going to be fed to the decoder. So at the first time step of the decoder, the input received is the output from the encoder for the last time step of the encoder. Okay, but then at the second time step of the decoder, then the input received, the hidden state received, is going to be the hidden state of the first time step. Okay, the output of the hidden state output of the first time step of the GRU is going to be fed to the next or the second time step of the GRU. Because as you remember, that is how RNNs work. They receive two inputs, the previous hidden state and the current input. Okay, so let's go ahead and start implementing that part in PyTorch. Okay, so let's see how it's done step by step according to this diagram. So first of all, before we begin, we need to define our class variables. Okay, so we have our attention model, okay, which is received here. So whenever we want to initialize or create an object of this class, so when we want to initialize this class with an object, we need to input these arguments. Okay, so the attention model is just the name of the attention operation that we're going to use. The embedding, okay, so remember, even though we didn't discuss this in the diagram, okay, but actually the inputs, which is of shape 1 times the batch size, okay, remember these are only indices of the words. Okay, what we need to transfer them to an embedding. Okay, so you remember that in the intuition videos we did discuss how word embeddings work and how they take indices and transform these each index to a vector of values. Okay, a vector of dense values. So this is to represent the words. This is to represent the features of the word. Okay, so you need to apply an embedding actually every time you're using an RNN or GRU or an LSTM. Whenever you have a word, okay, you need to use a word embedding. So this is something very essential. So therefore, that is why we need to define our embedding layer. Okay, so self of embedding equals embedding, and then we need to define our hidden size. Okay, so it's just this is how many LSTM cells we have. Sorry, GRU cells we have. Okay, or the number of we discussed this previously. I think in the encoder part we discussed in depth what does hidden size mean. Okay, so I'm not going to explain it again because I already did explain it in depth. Okay, so then we have our hidden size over here. Our output size is basically our vocabulary size. Okay, so how many words we're predicting. The number of layers we will set to 1 by default, but then if we wish to change it, we only need to change this argument over here, and then dropout by default we also set to 0.1, but we can change it later on. Okay, so then we associate every one of them with self. Okay, so the self.attention model, self.hidden size, self.output size, number of layers, dropout, embedding. The dropout for embedding also, we're going to use a dropout for embedding. Then the GRU. Okay, so this is the GRU. Okay, if we go back to the PyTorch documentation, then we can see that these are the arguments. Input size, hidden size, number of layers. Basically these are the most important ones. So let's see what we have here. So the input size is this how many features we're expecting, which is the size of our embedding. Hidden size is how many hidden neurons or how many hidden cells in the does the GRU have. The number of layers. Okay, then we also have the dropout. Okay, so let's see what we did over there in the code. So we have our input size as the hidden size. So we set actually the embedding size and the hidden size to be the same. Then we also have our hidden size also. This is the the hidden size. Maybe I should write here embedding size so you guys won't get confused. But most of the time you'll find people using the input size the same as the hidden size. Okay, so that is why we have hidden size here as the input. Then the number of layers, which by default we set to 1. Okay, but later on as I said, we can change it. Then the dropout, we're going to use dropout only if the number of layers are more than 1. Okay, so 0 if number of layers equals to 1. Therefore, if we do not change this, so if we keep it 1, then the dropout is 0. If we did change it, for example, let's say we put 2 or 3 layers, then we need to add some dropout. Now this is not necessary, but it helps your model regularize. So it reduces overfitting. Dropout reduces overfitting. Dropout isn't discussed in this course, but it's discussed in the other course. Okay, the one I showed you at the beginning. So in essence, what dropout does, it just drops some random number of neurons, okay, in each layer, and so it actually zeroes out these neurons, and let me show you the visualization of dropout actually. So this is dropout, okay. This is, you have this standard neural network, and this is after applying dropout. So you at each layer, okay, you randomly disable some of the neurons. So as you can see, these neurons are disabled, therefore they don't give any inputs, and same thing for this layer, and same thing for this layer. So this helps the neurons not to be really dependent on each other. Now this is like in a nutshell what dropout is. Okay, so it helps, it reduces the dependency of the neurons, because for example, if you don't do it, then each neuron would be highly dependent on other neurons over here. So what you're doing over here is at each iteration, you're randomly dropping out some probability of the neurons, and that does not allow neurons to be too dependent on each other. Okay, so as a result, it reduces overfitting. Okay, so let's go back. So we're done with this self.gru. Let's go to self.concat. So this is just in a linear layer, okay? And this is over here, okay? So this is a linear layer. After we concatenate the outputs, the two outputs, okay, after attention, then we need to run it through a linear layer. So this linear layer, the input is of shape hidden size times 2, and we'll understand why it's times 2 later on when we see the output of the concatenation. And then the output of this linear layer is has a shape of hidden size, okay? So the number of neurons is the number of neurons. The number of neurons in this linear layer is basically the hidden size. So that is what we're doing here. We're defining this linear layer. So self.concat equals to n.linear hidden size times 2, the number of input neurons, and hidden size, the number of output neurons. And self.out is basically this over here, which is the hidden size times the vocabulary size. So it's a linear layer also, and same thing. So the number of inputs is the hidden size, okay, which is coming from here actually, and then the number of outputs is the output size, which is the number of vocabulary. And then finally we need to also initialize our attention class. So here, remember, our attention class receives two arguments, the method and the hidden size. So the hidden size is just defined here, okay? So there's no need to worry about this, which is here, okay? So this is the hidden size. It receives the argument from here, which is the input for the input argument for the initialization of the class. So then the attention model, I remember I told you, which is the name of the attention operation, which we also defined here, okay? Which we also defined in self.attention model. So like this, you've initialized an object of the attention class inside the decoder class, okay? And remember, we need to associate each one of them with self, because later on we're going to create an object of this class, and each of these are going to be an attribute of an object. So that's why we need to associate it with self. So we're going to build the forward propagation function of the decoder. And this is going to be very simple if you do understand the diagram. So we're going to follow this diagram when we're building the forward propagation function. So once you understand this, it's going to be very simple. It's going to be like a piece of cake, okay? So I repeat again, the forward function in this class, which we inherited from the NN.model class, is responsible for the forward propagation. Okay, now every class of NN.model has the forward function. So what we're doing here is we're overriding this forward function. Okay, and this is the function again responsible for the forward propagation. Okay, so let's get going. So what are the arguments that we need to enter in the forward function? Okay, we need to first the input step. Okay, remember the data is arranged of shape maximum length times the batch size. So let's look at this diagram actually. As you can see, here's our data of shape maximum length times the batch size. Okay, so what we're going to do is we're going to take one row or one sample and feed it to the GRU. So therefore, our input is of shape 1 times the batch size. Again, what inputs do we have to the GRU? We have this input, the last hidden state of the encoder, which is of shape number of layers times the number of directions, times the batch size times the hidden size. Okay, remember the number of directions is 2 because we're using a bidirectional GRU. And finally, we're going to also need to use the encoder output because we're going to implement the attention mechanism. So therefore, we need to pass this encoder output as an argument to the forward function. Okay, so this is the shape of the encoder output: maximum length times the batch size times the hidden size. And this is exactly what we have over here. The input step, 1 times the batch size. The last hidden, which is the final hidden state of the encoder's GRU, which is of shape number of layers times the number of directions, batch size, hidden size. Okay, this is not layer. It might be confusing. Final hidden state of the GRU. Then the encoder output is the encoder model's output of shape sequence length, or in our diagram it was called maximum length. It's the same thing. Batch times the hidden size. Okay, number of directions is 2. Okay. So again, we're gonna run this one step at a time. So at each time step, we're going to take a batch of words and run it through the GRU. Okay, so we run the step, we run, let's say, batch of words at a time. Okay, let's say, let's just write it more clear. Okay, so we take a batch of words and we feed it through the GRU. So let's get going. First of all, we need to embed our input step. So remember, and we talked about word embedding. Okay, so we need to represent the words as features, okay, or as dense values. So this is what we do here. We pass it through an embedding layer at the beginning. And why we define self.embedding here, okay, as a global variable, as a global class variable. Okay, so this is a class variable because we're going to use it here. Okay, so if we this is just a note on OOP. If we didn't want to use the self.embedding here, then we wouldn't need to define this as a class variable. Okay, but since we're going to use it here, then we need to define it actually as a class variable. Okay, because we need to pass it to other functions. So you can think of the variables as global variables for all the class. Okay, so they're shared variables for all the class, meaning that all the methods do recognize these class variables. Okay, and that's why it's called the class actually, because everything is related to each other. So the class variables and the methods use these class variables. Okay, so then we use dropout. Okay, we use a dropout layer on our embedding layer. So also we spoke about dropout before and what it does. Alright, and then we forward through our GRU. So self.gru, remember we defined the GRU here. Okay, so we go ahead and forward this the embedding and the last hidden through the GRU. Now let's go to the diagram and see what the GRU receives. So this is the PyTorch documentation. As you can see, in order to feed an input to the GRU, then we the two things that we need to specify for inputs to the GRU is our input step and our hidden state. Okay, which is basically here. This is the input step and this is the hidden state. So remember, the hidden state in this case, in the first GRU, is our hidden state, our last hidden state of the encoder. Okay, so this is what we have here exactly. This is the input step and this is the last hidden. Remember, the last hidden is the final hidden state of the GRU of it, okay, of the encoder GRU. This is to be more clear and obvious. And let's go see what this outputs. It outputs the output, okay, which is of shape sequence length, which is 1 in this case, times the batch size times the hidden size, okay, and it outputs also the last hidden state, okay, which is of shape number of layers times number of directions, batch size times the hidden size. So this is exactly what we have in our diagram. It outputs 1 times the batch size times the hidden size, and number of layers times the number of directions, batch size times hidden size. So this is the RNN output, and actually if we want to, let's do a small comment, okay, to arranged. Okay, so here I've written it. Okay, so we have the RNN output of shape 1, which is the sequence length, because we're using one time step at a time, the batch size and the number of directions times the hidden size, and then the hidden of shape number of layers times the number of directions, batch size, hidden size. Alright, then we go ahead and calculate the attention weights from the current GRU output. So in the attention mechanism that we designed before, remember that we use the hidden state of the current time step of the decoder and the encoder output. Okay, so remember that we've already designed this using here, alright, self-attention. So we've already specified or initiated the attention model. So all we have to do right now is just use self-attention or call self-attention, which is basically calling the forward function. Okay, so remember this will return the softmax of the attention energies, okay, across the first dimension, which is the batch size times 1 times the maximum length. So basically that is what we're doing here. We're calling the attention weights, so self-attention, and we pass the RNN outputs, okay, which we got from here, and the encoder outputs. So this is exactly what we have here. Okay, we have our output of the GRU, and this is the hidden state of the GRU. So we pass the output of the GRU. In this case, actually, the output is very similar to the hidden state because we're using one time step at a time. Okay, so we're passing the output and the encoder output to the attention mechanism. So let's go to the diagram and see what we need to do next. So we have our attention mechanism over here, and this produces the attention mechanism, remember, returns batch size 1 times the maximum length, which is this over here, batch size 1 times the maximum length. So this is what it returns. And remember, we then need to multiply the output of the attention mechanism with the encoder output, okay, because we need to find the context vector, which is what to focus on from our input. So that's why we need to multiply our encoder output, okay, which is our input sequence, times the attention output. And now, since we're multiplying a three-dimensional tensor, okay, so we have this three-dimensional tensor and this three-dimensional tensor, then we can use the batch multiply function in PyTorch. Now this multiplies just like normal matrix multiplication. Now in matrix multiplication, for example, if you have a 3 times 2 and a 2 times 4, then you'll end up with a 3 times 4 matrix. Okay, so you're multiplying two matrices with each other. Here we have 3D tensors. Okay, so we're multiplying these 3D tensors with each other. Okay, so we can use the batch multiply function in PyTorch. Now what we want to do is we want to multiply our attention weights, okay, which we got here, with our encoder outputs. So we have batch size 1 maximum length. We're going to multiply it with batch size maximum length hidden. Okay, now normally in 2D tensors you'll have these two multiplied with these two. Okay, so in batch multiply we just take this batch size apart here. So we have this batch size, and then it's just normal multiplication like a 2D tensor. So 1 times the maximum length times the maximum length times the hidden. So you'll end up with 1 times the hidden. Okay, so that's why we have our final tensor after we batch multiply as batch size times 1 times hidden. So our context vector here is of shape batch size times 1 times hidden. Alright, now remember, then we need to concatenate the context vector with the GRU output. Okay, but before we do that, we need to do some processing of the tensors. So we have our RNN output size as 1 times the batch size times the hidden size, and what we want to do is we want to get rid of this one because it doesn't mean anything. Okay, so we just want to keep it batch size times the hidden size. So therefore, a function to do this, which we learned also in the introduction to PyTorch section, is squeeze. Okay, so we want to squeeze this tensor, and we're going to also need to specify in which dimension we want to squeeze. So in this case, we want to squeeze it at dimension number 0. So we want to get rid of this one. So we end up with batch size times the hidden size. This is exactly what we have over here, or an output that's squeeze 0. Okay, so this will return a tensor of batch size times the hidden size. And then our context vector, okay, which is of shape batch size times 1 times hidden size, we also want to get rid of this one. Okay, so we need to also squeeze it at this dimension, which is 1. Okay, so you have this dimension as 0, this is 1, this is 2. Okay, because we start at 0 in Python. So this dimension is 1. So therefore we also squeeze this at dimension number 1, and therefore we also have a shape of batch size times the hidden size. Okay, so both of these are batch size times the hidden size. Now what we need to do is just concatenate them together. Okay, and we want to concatenate them along the first dimension. So basically what we'll have is batch size times the hidden size times 2. Okay, because we're concatenating them along the columns. Okay, so this is exactly what we have over here. Torch.cat is to concatenate. Then we need to specify in tuples what we want to concatenate. In this case, we want to concatenate the RNN output and the context vector. Okay, and then we need to specify in which dimension we want to concatenate them. And in this case, we want to concatenate them along the columns. Okay, so this is why we put dimension number 1 over here. And we'll end up with batch size times the hidden size times 2. Okay. So finally, we just run it through a tanh function. So tangent function. Therefore, this is what we have over here. But first, remember that we need to find another representation of this tensor. Okay, so we run it through a linear layer. And this is basically the purpose of this linear layer is to find another representation of shape batch size times the hidden size. Okay, so therefore that is why we run it through the self.concat, okay, which is a linear layer of shape hidden size times 2, and then the output of this linear layer is a hidden size. So therefore we have here an output of this when we run this concatenated input, okay, through this linear layer of self.concat, then we have the batch size times the hidden size. And then we take this batch size times the hidden size, we take this representation, we run it through a tanh function. So that is what we're doing here. We're using torch.tanh, and then we're running all of this representation over here. And then we finally have our last, okay, let me, alright, so the screen wasn't fitting. Then finally we have our last fully connected layer, which is basically generating our vocabulary size, and this is of shape hidden size times the vocabulary size. Okay, so the inputs to this layer should be the outputs of the last layer, which is hidden size. So that is why we have hidden size as the number of neurons in the input layer, and the number of outputs in the the number of neurons in the output layer is basically how many classes we want to predict. In this case, is the number of words we have in our vocabulary. So that is why it's of shape vocabulary size. And remember, we did specify the linear layer for this here. So we have a linear layer of shape hidden size times the output size. And then so all we have to do right now is just run this concatenated output through the linear layer, which is self.out, and then we'll end up with a tensor of shape batch size times the vocabulary size. Okay, so this is the predicted this is the output tensor that's returned, which is the batch size times the vocabulary size, which represents the distribution along each word in the vocabulary. Okay, so this is what we have over here. And then finally, in order to take the maximum, okay, of this layer, of this output layer, then we pass it through a softmax function to squash all our outputs between 0 and 1. And then by taking the maximum of these outputs, then we basically get the prediction. Okay, so we're just squashing them between 0 and 1 along the first dimension, which is along the columns. And remember, the columns represent the distribution of the vocabulary words. So that's why we want to take the dimension equals to 1 over here. So therefore, we have our final output as a softmaxed output of this over here. okay? And then we just return them. We just return the outputs, which we got over here, okay? And the hidden, and remember the hidden is basically over here, the one that we got from the GRU, which is the last hidden state of this current time step that we're working with, okay? Which is yeah, not the last hidden state, because there's only one time step, so it's basically just the hidden state of the GRU, of the current time step of the GRU that we're working with. Because remember, with this output, with the hidden state output of this current time step, we need to pass it to the next time step, okay? Because that is why this is how an RNN works, okay? We need to pass the hidden state of this time step to the next time step. So that is why we need to also return this output. And we're finally done with the forward function of this decoder. Alright, now we're done building with the architecture. So we've built our encoder, and then the attention mechanism, and then the decoder with attention. And now we're ready to go to the training code. So this section is fully on training the model. Alright, so before we go into training, we need to define a function that calculates the loss, that considers the loss only for the non-zero elements. Remember, here in the sequence we did pad the sequence, okay? So if we go back to this image over here, we can see that the short sequence of, for example, if we take this one, then this is the sentence, okay? So we've arranged the sentence from the longest sentence to the shortest sentence, and the shorter sentence have been padded with zeros. And then when we transpose them, then we still have some zeros in every batch. Okay, so remember, we're taking across the batch size, which is the number of columns, and realize that in some of the batches over here, so for example in this batch, and this batch, and this batch, and in this batch, we do have some zeros. So we don't want to consider these zeros when calculating the loss. That's what we need to do. We need to write a function to get rid of these zeros. Okay, so let's go back to our training codes. Okay, where is it? All right, here. So first of all, we're going to take, okay, before we begin, there's these arguments. So the decoder out, and the target, and the mask. Now the mask is the one returned here. Okay, if we go back here, this is the mask. So you're returning the mask of this sequence, which is of shape maximum length times the batch size. So this mask represents how many ones we have. For example, at this element over here, we do have a 0. At this element over here, we do have a 1. So this mask represents the elements that are present and the elements that are zeros. So, okay, so this is a representation of this tensor over here. So this is the first thing we need to consider, the mask. And the target variable is the one that I just showed you, the tensor of the target. And then the decoder out. So what we do is we take our mask and take the sum of it. Now when you take the sum of ones and zeros, then eventually you'll get how many ones do you have, okay? Or in other words, how many non-zero elements do you have? So you're taking the number of elements that you should consider, okay? So let me write a comment here. How many elements should we consider, okay? Oh, I think I spelled this wrongly. Elements should we consider. So this is n total represents how many ones or how many elements present, or how many non-zero elements. Now we're going to take our targets and we're going to reshape it to be of batch size times 1. Okay, so this is why we're doing this, is because we're going to use it in torch.gather later on. So whatever the shape of the target, okay, we're going to reshape it to be of -1. Okay, -1 means we just let Python decide what's this dimension, what this dimension should be. Okay, and so whatever this should be, Python just sets it. In this case, it's going to be batch size, and then we tell Python that I want my second dimension to be 1. So the number of columns is only 1. Okay, so that's how you do it. Target.view -1 1. Okay, so then after we have our targets, okay, and our output from the decoder, we need to calculate the loss between the decoder output and the target. So what we do is we first need to gather them together. So we use a function called torch.gather to gather these two together. And don't worry if you don't understand this, because later on when we're going to visualize this step by step. Okay, so you're actually going to see what torch.gather does, and we're going to print it out and we're going to print the shape of it. Okay, so then we calculate the loss, and in this case we're using the NLL loss. NLL loss stands for negative log likelihood loss. Okay, so that is what NLL stands for. So negative means it's negative. Okay, and the log, we need to take torch.log, and then this we're going to calculate the loss for what is for the gathered tensor. Okay, so this is what we call the negative log likelihood loss. And remember that we did not consider all elements. We're not going to consider all elements because some of them are zeros. So we need to remove these elements according to this mask that we got over here, right? So this is where we need to use our mask. So we use a function called masked select, then mask. So what this does, according to the ones in this mask, it only takes the elements, the corresponding elements in this cross entropy tensor. Okay, so what you end up doing is the loss is only for the elements of non-zeros, because here you selected the elements that are non-zeros, okay, which represent a 1 in the mask. And then we just calculate the mean of the loss. So this is very easy, just loss.mean, and then we just transform it to CUDA if we do have a GPU. Otherwise, it will be transformed to a CPU. And finally, we return the loss and also the total items. So the total elements that we considered, which is, remember here we calculated n total. Okay. All right, now we're going to visualize the training step by step. So we're going to actually see a live training of our chatbots. Okay, during each step we're going to print out the shapes of the tensor, and we're going to do this for one complete iteration. Okay, so this is very important to understand and comprehend how the training process works. All right, now before we move on, I'd like to introduce to you the concept of teacher forcing, since we're going to use it in our training. So let me show you the diagram that I'll be explaining. All right, and that is what we have over here. So that illustrates the concepts of teacher forcing. Okay, now let me start with no teacher forcing. When you don't have teacher forcing, what happens? Now during the training of your sequence-to-sequence models, then there's two situations. So there's two ways of training. The first way is that you do not use teacher forcing. Now what does that mean? So we have our encoder that encodes the input sequence into a feature vector, and then this feature vector gets passed to the decoder, and then it decodes this feature vector into a description in natural language. So what happens when you're not using teacher forcing is that you generate the next words at the first time step. Okay, so you generate the first word at the first time step, and then you pass this generated word to the next time step. And now this generated word acts as the input to this second time step, and then generates the second word, and then the second word acts as an input to the third time step, and so on. So what you're doing is that your input is being supplied from your previous output. So we are supplying the inputs depending on the output of the previous time step. So that is exactly what we're doing in testing time. Therefore, what's happening here is that training and testing, the process of training and testing is exactly the same. Okay, you predict, and then you pass this predicted word to the next time step. So that is what normally happens at testing time. And when you're not using teacher forcing, then that also happens at training time. So in conclusion, when you're not using teacher forcing, then you're supplying the output of the time step to the next to the input of the next time step. So the inputs of every time step depend on the output of the previous time step. Okay, so this depends on this, this depends on this, this depends on this. Now, for example, if you end up generating a wrong word, okay, that's gonna mess everything up. Okay, because you're gonna take this wrong word and you're gonna supply it as the input, and then this thing might predict a word that is completely out of the context. Okay, so that is one disadvantage of not using teacher forcing. Now, what happens in teacher forcing? Instead of supplying the previous output generated by the LSTM, okay, we supply the actual input. Okay, we supply the actual label. So regardless of what this time step, what this LSTM generates, okay, we don't care what it generates. We're still supplying the correct label. Okay, so the inputs that they receive are the actual labels. Okay, so we are supplying the inputs regardless of the last word generated. So we don't care what this word what this time step generates. If it generates a wrong word, we're still safe. Okay, because we're still supplying the actual word that should be generated over here to the next time step, to the next LSTM. So that is what teacher forcing is. So basically, you're forcing the network to learn, or sorry, you're forcing the inputs of the decoder to be correct. Okay, so that is what happens in teacher forcing. Now, there is also, of course, a disadvantage of teacher forcing, and it's that it does not mimic real-time situations. Because in testing time, this does not happen. In testing time, we don't have our these labels to supply as an input. Therefore, we only therefore in testing time we're depending on the generated word. Okay, so during testing time, whatever this LSTM generates, so for example generates I, then we're going to supply this I to the next LSTM. So all of the inputs of every time step are depending on the previous time step outputs. Okay, so basically each one has an advantage. Okay, but when you're not using teacher forcing, then you are really you do mimic the real-time situation. Okay, now when you use teacher forcing, then you're not allowing the network to learn as situations in real time. Okay, so that is basically the concept of teacher forcing. Now, I told you that each one has an advantage. So basically what we do is a 50-50. Okay, so we set a teacher forcing ratio, which later you're going to see in the code is 0.5. And so 0.5 of the training time is without using teacher forcing, and 0.5 of the training time is with using teacher forcing. All right, so now that you've understood the concept of teacher forcing, let's go back to the code. And now that you've understood everything, we're ready to go to the training. So we're going to visualize the training. I repeat again, here we're going to visualize the training step by step. So we're going to see a live training for one complete iteration. Okay? So let's get going. First of all, we're going to define a small batch size of 5. Okay, and we're going to run our batch to train data. So this is exactly what we did right here. Okay, so this is what we have. Okay, we have a small batch size of 5, and then we got our batches by running the batch to train data. Okay, if we go down here, we're gonna see that it's the exact same thing. So up until here is the exact same thing. So we're gonna print out our input variable, then the length, and then our target variable, which is the reply of the question, then the mask and the maximum target length. Now let's do a very small and fast revision. Okay, so our input variable, remember, which is the questions, is of shape maximum length times the batch size. Okay, and here the length of the tensor specifies the length of each sentence or each question, which is basically here, for example, 10, then you have 8, 8, 5, 5. Okay, and then the target variable is the reply of this question. So again, it's of shape maximum length times the batch size, and then finally our mask is to we're going to use this mask when calculating the loss. So we don't want to consider the 0 elements here in every batch, so therefore we specify zeros to just ignore them. All right. So this is a small recap. Now let's get going to the training. So here we go. So this is up until here. There's nothing new. Okay, here we're gonna start the new stuff. So we have our hidden size as 500, and remember the hidden size is how many GRU cells you have. So it's how many hidden neurons you have. So the dimension of the hidden state, or sorry, the hidden cell. So we have 500. That means we have 500 hidden cells, hidden GRU cells in every time step. Okay. And then we have 2 layers for the encoder and 2 layers for the decoder. Okay, so these are arbitrary. You can put 1. It's up to you. You can even put 3 if you want. Dropout is 0.1. So we're going to set dropout. We explained briefly about dropout previously in previous sections. So we usually set it to 0.5, but we're going to use 0.1 over here. Okay, attention model. We're going to use the dot operation. So if you go back here, then we have these 3 types of attention operations, and we're going to use the dot operation. Remember, which is just an element-wise multiplication between the hidden state and the encoder outputs. If you're not sure of how this works, then please refer to the intuition videos. We explained this in depth. Okay, and then we're going to define our embedding layer. So we explained also embedding in the PyTorch in the introduction to PyTorch section. So we had a section that introduces embedding. Okay, so embedding, I repeat, is representing the words as features. So you present a single word as multiple values, okay, which are dense values that represent the word itself. Okay, so in order to do that, we need to define an embedding layer, and it's also one of the nn.model class functions or classes. Sorry. So we're going to inherit from the nn.model class, and what we're going to specify is the embedding layer this time. Okay. Now remember, the embedding takes 2 arguments. First of all, how many words you have. Okay, and so this is the number of words. Remember, we used our vocabulary class. So this VOC is the object of the vocabulary class that we created, and the attribute number of words. If you go back here to the vocabulary class that we created, then you're going to see an attribute called the number of words. Okay, so this is the vocabulary class, and the number of words, as you can see, is an attribute right here. Okay, and so it starts out with 3, and then we increment it every time we add a new word. So at the end, you'd end up this number of words giving you the total number of words in your data sets, in the process data set, sorry. Okay, so here this is the number of words, and then the dimensions of the embedding. So basically how many values you want to represent each word. This is what the hidden size is. Okay, so basically we're using 500 values for each word. So the dimension of the embedding is 500. Okay, we're just using the same value of the hidden size. However, you can change it. Normal one is 256. Sometimes people use, but usually it's set to the same value of the hidden size. So this is the embedding. Now we're going to create an object of our encoder and decoder. So remember, we have 2 classes, one defining the encoder, okay, which is over here. So this is the encoder, and then the decoder, which implements also the attention class, is over here. So we're going to create an object of these 2 classes right now. So the first one is the encoder, and we're going to call that class the encoder RNN. And remember the arguments that the encoder RNN class receives. It receives the hidden size, the embedding, the encoder the number of layers in the encoder, and the dropout. Okay, so you can visualize them here. You can see them here. This is what we need to specify. When we initialize the class, we need to specify all of these. Okay, so hidden size, embedding, number of layers, and dropout. Okay, so this is what we're doing right here. We're passing these arguments to the encoder RNN. And then we're going to create an object of the decoder. Okay, so the decoder, this is the class of the decoder. And remember, we need to pass all of these. So let's go ahead and see what we need to pass. The attention model, the embedding, the hidden size, output size, number of layers, and dropout. And this is exactly what we're doing right here. Okay, so the attention model is the dots, then the embedding, and then the hidden size, the number of words, the number of layers in the decoder, and the dropout. And remember, the attention is the attention class is implemented inside here. Okay, so if you can see here, then we have this attention we were creating an object of the attention class inside the decoder. Okay, so the attention is actually included inside the decoder class. Okay, and the attention model is what we're passing over here. So the attention model, which is the dot, is getting passed over here. Okay, so we've created an object. Oh, sorry, this is quite irritating sometimes. Okay, so we've created an object of the decoder. Okay, and then we're going to pass the encoder and the decoder to our device. So if we're using a GPU, we're going to move the model to the GPU. If we're using a CPU, then we're going to move the model to the CPU. Okay, we need to do this because I don't know if you're using a CPU or a GPU. So these two lines ends up passing your model to what you really have. Okay, remember we need to pass the models to the GPU or the CPU, as well as our images and labels, as we're going to see later on over here. Okay, and then we're going to set the encoder and the decoder to training modes. Now remember, whenever we have batch normalization and dropout, then these two, they act differently in training and in testing time or inference time. So therefore we need to tell PyTorch when it's training time and when it's testing time, and we do that by using encoder.train. Okay, and then decoder.train also. So this is to ensure that batch normalization and dropout are acting they're acting how they should be in training and later on in testing time. Okay, now the optimization. Now we need to define the optimization. We're going to use Adam optimization. Now unfortunately Adam optimization is not discussed in this course. Okay, but it's in the other course I referenced at the beginning of this course. Adam optimization is a way of optimizing your neural network. So it's one of the methods of back propagation. Okay, and basically it stands for adaptive moment estimation. So this is what Adam stands for. So I repeat, it's just a method to update the weights rather than the normal gradient descent approach. Okay, so this is proven to be, I think until now, it's the best one, and many papers use it until now. Okay, so most of the time Adam optimization is used. So in this case, we're going to use Adam optimization, and we define it by using the optim class. Remember, we did import the optim class from the torch library, and we're going to use it right here. So from optim, we're going to use .adam. And what we need to specify is our parameters, so the weights that we want to update, and finally our learning rates. And our weights that we need to update comes from our encoder. Okay, so basically we have two optimizers, one for the encoder and one for the decoder. So when we're using the encoder, we need to specify the weights of the parameters of the encoder by specifying encoder.parameters. Okay, so the encoder over here that we created right here, the encoder class, okay, which in turn inherits also from the n.model, has one of the attributes, which is the parameters, and specify its associated weights. Okay, so therefore that's how we specify the weights, encoder.parameters. And then the learning rate, we're going to set the learning rate to 0.0001. Now you can change this, but remember it cannot be very small, very big. So this is a good option to start with. But remember, when it's big, okay, when your learning rate is large, then you might never reach the optimal point. Okay, again, the learning rate is not discussed. The theory of the learning rates are not discussed over here and in this course, but it's also discussed in the referenced course at the beginning. Finally, so here we've defined our optimizers, and then we're going to run the zero grad function. Now the zero grad function basically zeroes out the gradient, so it removes the gradients after every iteration, because remember, we don't want to stack the gradients. We don't want to stack the when we're going to update the weights, we don't want the gradients of the previous iteration to be considered, okay, or to be stacked with the current gradient. So that's why we need to zero out the gradients of the previous iterations. Okay, now that is in other frameworks like TensorFlow. I don't think this you need to do this, okay, because it's already done in the function that's responsible for training. But in PyTorch, you need to write it manually. Okay? So then remember we have our input variables, which we got over here from the batch to train data, and we have our target variables. So remember we're going to use these in training. So we first need to transfer them to the CPU or the GPU, okay? Because remember they're going to be used. They are basically going to be propagated through the network. So therefore, we need to transfer them to the respective device, either a CPU or a GPU. Okay, and then we're going to initialize the loss to 0, and then we're going to print. Then we're going to define a new list, an empty list, which stores the losses. Okay, and then we're going to define also a variable which is total, and it's going to be initialized to 0. You'll understand these later on. Now we're going to forward the input sequence, okay, the input variable that we got from the batch to train data function. Okay, we're going to forward this input sequence through the encoder. Now remember, the forward function of the encoder is responsible. So if we go back to the encoder forward function, which is here, remember it receives two things: the input sequence and the input length. And by default, the hidden is none. Okay, so that's what we have to pass through the forward function. So we're going to pass our input variable and our length, and hidden by default it's none. Now this will return two things: the encoder outputs and the encoder hidden, which we discussed previously. Okay, I think you should have no doubt by now. So this is what it returns: the encoder outputs and the hidden. So we receive these two returned variables, or the sorry, I'm losing this. Okay, the encoder, we receive the encoder output and the encoder hidden. Okay, and then we're going to print the shapes of these two. We're going to print the shape of the encoder output, and then we're going to print the shape of the encoder hidden. So that's how we do it: encoder output.shape, this is a tensor, and then encoder hidden.shape. Remember, these two are tensors. So we're going to print the shape of them. Then we're going to create the decoder input. Now the decoder input is, remember, the start of sentence token. Now we're going to do this for how many batches do we have? So in this case, we're using 5 batches. Small batch size is 5. So we're going to create the start of sentence token, okay, 5 times in this case. All right. So this is, we're going to specify a torch.long tensor. We've covered torch.long tensor in the introduction to PyTorch also. So please refer to this if you're still having problems understanding what's a torch.long tensor. So what's the difference between long and a normal tensor? It's described there. So we create a start of sentence token, okay, and we do this 5 times. So we use a for loop for 5 times. And then we're going to pass this to our GPU or our CPU, depending on what we have. So we also need to do this. And then we're going to print the shape. So you're going to see the shape of this later on. And then we're going to actually print these tokens. So we're going to print the start of sentence tokens over here. And then we're going to set the initial decoder hidden state to the encoder final hidden state. Remember, in the sequence to sequence modeling, okay, what we learned in the intuition videos, the encoder passes the feature vector to the decoder, right? So that is exactly what we're doing right here. We're passing the encoder hidden state, the final encoder hidden state, to the decoder. So that's how we do it. We're going to prepare this decoder hidden state by taking the encoder hidden, which is returned here from the encoder. Okay, so we're taking this, and depending on how many layers we have, then we're considering all of these. So here the number of layers is 2. So we're going to take the first 2 returned hidden states of the encoder. So in this case, we're going to pass this decoder hidden to the decoder. This is the initial decoder hidden state. So that is basically the whole concept of sequence to sequence models. We're passing the encoder hidden state to the decoder. So we're going to print the shape of this decoder hidden. Okay, and now we're going to print a sign so we can know that we've started to decode. So now let's look what's happening in every time step of the GRU. Okay, so this is where we start. Okay, let's start by using this, by observing this snippet of code So to visualize what's happening in every time step. So now for visualization, we're just going to assume that you are using teacher forcing. Okay, but later we have an if-else statement, so it's up to you to choose. All right, or maybe you can put 0.5, so 0.5 of the time you're using teacher forcing and the other time not. Okay, but here we're just visualizing, so we're just going to assume that we're going to use teacher forcing. So then you loop through all the time steps that you have. Now remember, how do we determine the number of time steps? This was a question discussed in the quiz of the RNN section. Okay, and also I think we did mention it in the RNN intuition videos. So how do you determine the number of time steps of the decoder? You take your process data set and you look at the sentence that has the maximum length. So how many words does this sentence have is basically the number of time steps. So it's basically the number of time steps, again, is the maximum words you have. Okay, the sentence that includes the maximum amount of words. Okay, these words, these number of words are basically the number of time steps that you have. Okay, so we're going to loop through. So let's just consider that the maximum target length is what we had over here. Okay, you're going to see that later on when we print it. So for example, if it's 30, then we're going to loop 30 times. Okay, so we're going to pass the decoder inputs, the decoder hidden, and the encoder output through our decoder, the object that we created previously. Remember, our decoder, if we go back here, okay, then the forward function takes the input step, the last hidden, and the encoder output. And it returns the output and the hidden. So this is exactly what's happening right here. Okay, we're passing the decoder inputs, the decoder hidden, which we got over here, which is, remember, the final hidden state of the encoder, and then we're the encoder outputs. Okay, and we're gonna get back our outputs, the decoder outputs. So this, remember, the decoder returns the decoder outputs and the decoder hidden. Okay, and then we're gonna print the shapes of these two. And then, remember, since we're assuming that we're using teacher forcing, then basically the next input is the current targets. So we're going to take this target variable, and then we're going to change the shape of it. So we're going to shape it to be 1 times something. Okay, so the -1 means what's left, and you basically let Python decide. Okay, so that is okay. So you know it's 1 because you're using 1 time step, and you let Python decide the rest. And we're going to see what that -1 is later on, because we're going to print the shape. So we're going to print the target variable at the current time step before reshaping, and then the target variable at the current time step shape before reshaping. So here we're just printing the target. Here we're printing the shape of the target, and then we're going to reshape it, and we're going to print the decoder input shape when we reshape the target variable. So what we did over here, okay, the decoder input, we're going to print the shape of it. And then we're going to print the mask at the current time step. So we're going to print the binary mask, and then we're going to print the shape of that binary mask. And then we're going to run the mask NNL loss, the negative log likelihood loss function. Okay, and we're going to get the output, which is the mask loss and the n total, and then we're going to print them out. And then we're going to accumulate the loss over here. So remember, the loss is initially 0, and then we're going to accumulate this. And then we're going to append that loss to the list. So that's how we append a number to a list, print losses dot append. And then we're going to append this mask loss that we got over here. And remember, mask loss is a tensor. So in order to extract a value out of a tensor, then we need to reference dot item. And this is for one value only, so we're going to multiply it by how many total values we have, the total number of values that we have, which is also returned by the mask NLL loss. So we're going to append this to this list, and then we're going to print that list, and then we're going to basically increment the total numbers. So we're just going to increment by the n total returned here, okay? And then finally, we're going to update our weights. So this is how we update the weights. We use the dot step function. So the dot step is basically the function that's used to update the weights of the neural network. So remember, we're using this. So again, sorry, before we continue, the dot step is a method of the optimizer that we defined here. Remember, we have two optimizers, one for the encoder and one for the decoder. So we basically do both, do for both, because we're updating the weights for the encoder and for the decoder. And then we're just going to print, so we're going to take this list of print losses and we're going to sum them up and divide it by the number of totals. So this is the returned loss, and then we're going to print it out. And then finally, we're just going to print that we've done one time step at a time. You'll understand this much better when we're going to print, we're going to run this, and we're going to see the shapes and see the tensors themselves. Okay, so you'll get more understanding later on. Okay, so let's run this and see the results. So I'm going to run this, and there we go. It's printing out. So, yep, I think it's done. So let's visualize the results. So the input variable shape, remember, is of shape maximum length times the batch size. Therefore, the maximum length here is 9, and the batch size is 5. Okay, and then the length is basically the shape of the length, or basically how many elements do you have in the length, is of course corresponding to the batch size. We're using 5 samples, so therefore it's also 5. Then the target variable is of shape 6 times 5. So this time the maximum length of the targets is 6, and the batch size is 5. And the mask shape is also same as the target variable, okay, because we're going to mask that target variable, so it should be the same shape, which is 6 times 5. The maximum target length is 6. Okay, here which is the same exact thing here. Okay, the first dimension, which is 6. The encoder output shape is 9 times 5 times 500. 9 is the maximum length, okay, which or the number of time steps that you have. 5 is the batch size. 500 is the hidden dimension. We explained this in detail when we were discussing about the architecture. Okay, we had a diagram also to visualize it. So please refer to the diagram in the previous videos if you still don't understand this. The last encoder hidden shape is exactly, we also discussed this in the previous videos, so please refer to the diagram if you don't understand this. It should be of shape number of layers times 2 times the batch size times the hidden size. Number of layers is 2, and the number of directions is 2, so number of layers times number of directions, which is 2 times 2, and that gives you 4. Okay, and batch size is 5, hidden size is 500. The initial decoder input shape is 1 times 5. Okay, 1 is because we're using 1 time step, and 5 is the batch size. And then this is what we have from our, if we go ahead and see what we're printing, then we're printing actually the initial decoder input shape. Oh, sorry, not this one. It's this one over here. We're printing the decoder input. So this is the decoder input, which is basically the start of sentence token, which is 1. So basically it's 5 ones because we're using a batch size of 5. So we're going to pass this all to the first time step of the decoder. Now the initial decoder hidden state shape is of shape 2 times 5 times 500. Same exact thing. 2 is because you have 2 layers, 5 is the batch size, and 500 is the hidden size dimension. So now let's observe what's happening at every time step of the GRU. Now what I'm going to do is I'm just going to explain one, because the others are just like a repeated version of the first one. Okay, but we're going to see how the losses accumulated over here. So there we go. We have our decoder output shape, 5 times 7,826. Now 5 is the batch size, and then 7,826 is the number of words that you have. Okay, so this is the output, number of output neurons. Then the decoder hidden shape is of shape number of layers times 5 times 500. 5 is the batch size, and 500 is the hidden dimension size. Now the target variable at the current time step before we reshape it. So this is the target variable. So this is the expected output. Okay, remember these are the indices of the expected output words. Okay, so these are the 5 indices. Remember, it has a shape of 5 because there's 5 elements only, because we have a batch size of 5. And then the decoder input shape, okay, which so here we reshape the target variable. Okay, so initially it was a 1 dimension only, but now we made it 2 dimensions, so it's the same exact thing. but we just added another dimension to this target tensor. So it became from 5, we turned it to 1 times 5. Now the mask at the current time step, okay, is 1, 1, 1, 1, 1. Now this is for one time step only. So basically what we're doing here is we're telling that there's no padded batch right here. Okay, at this time step there's no zeros. Okay, later on you see if that we're going to have a 0, for example, here, then this would be 0. But now here in this batch there's no 0, there's no padding. So therefore we want to consider all of these for the loss function. Therefore the mask is all 1. Now the mask at the current time step is the shape of it, it's 5 because we only have 5 elements. And then the loss is, for example, 8.9. Now this is the beginning, so of course it should be very high. Okay, so the mask loss is 8.9, okay, and then the total is 5. And this is basically, we've appended this number, so we've multiplied this number by 5, and if you multiply this number by 5, then you get the accumulated loss. So we've appended this accumulated loss to the list, which is 44.679 you get, and we've appended that, and then finally the returned loss is 8.9, which is basically the same thing. We're just extracting, so basically the dot item extracts this value from this tensor and it returns it. So this is what we get, 8.93. So we take the extracted item from this tensor, we multiply it by 5. Okay, so this gives until now this is what we get. Okay, so we multiplied it by 5. We got the printed loss, okay, which is 44.679, and then we take this 44.679 and we divide it by the number of total. Number of total until now is 5, okay, which we also printed it here. So when we divide it by 5, we get 8.935, okay, which we printed over here. Now we're done with one time step. Now we go to the second time step. It's the same exact thing. The only thing is changing right now is the loss. Okay, so here realize that we've appended another value. Okay, and if we take this, so what we're doing right now is we're summing the two of them. Okay, so here we have sum of printed loss. Printed losses, okay, printed losses is remember is the list, so we're summing up these two values of the list, and then we're also incrementing the number of total variable, okay, and we're dividing this sum by 10, and we're getting back 8.95. So same exact thing. You append the new one, you add them all together, divide by 15, you get 8.98. So slowly this is going to minimize, actually. The loss is going to be minimized. So that is basically the process. So this we're doing this for one complete time step, which is the maximum target length. Okay, and the maximum target length is here 6. So we're doing this for 6 times. Okay, so you've understood basically the training function. Okay. And now what we have over here is exactly the same thing. So we're not changing any single thing. All right? We're just plugging everything into a function. So I'm not going to explain this because it's the same exact thing. The only difference is the teacher forcing. So this is how we determine if we're using teacher forcing or not. So we just pick a random number. So we random at random. Let me, for example, show you what random does. Okay? If we run this, then this gives you a random number. Okay, if we run it again, it gives you another random number. Run it again, it gives you another random number. So we just randomly get a number. Okay, and if this number is smaller than 0.5, then it's true. Else, it's false. So then, depending on this random number, we're going to have either true for teacher forcing, or false for teacher forcing. Okay, so if it's true, we're going to implement teacher forcing, which is what we discussed previously. If it's not true, then we're not going to implement teacher forcing. And the only thing that we're changing here, remember, we're not supplying the actual targets as input. Instead, we're supplying the top prediction, okay, the output of the previous time step. We're supplying it to the input of the next time step. So this is what we're doing. We're top I. We're taking top I. So this is how we determine top I. We take the decoder output, okay, which is the distribution of the words, and then we take the top K, which is 1. So k is 1 here, so we're taking basically the top element of the decoder outputs. We're taking the top element and then we're supplying it instead of supplying the target, the actual target. So that's the only difference between the two. Okay, so this is the training function. And then finally, this was not covered. So loss.backward is to perform the back propagation. Okay, so right here we had optimizer.step, right? But we just updated the weights, but we did not back propagate because we didn't call loss.backwards. Okay, so what you need to do is basically first call loss.backwards and then update the steps. So you need to back propagate and then update the steps. Okay, so then we're going to implement gradient clipping. All right, now remember RNNs, we discussed this in the intuition videos, they suffer from the vanishing gradient problem and the exploding gradient problem. And one technique to prevent the exploding gradient problem from happening is gradient clipping. So basically, we're preventing gradients from becoming too large. So once they become too large, we just clip them off. And we clip them off to a certain value, which is defined by this clip value over here. So if we go to the PyTorch documentation, then this is the function we have. So you need to supply the parameters as the first argument. What happened? Okay. You need to supply the parameters as the first argument and the value you want to clip as the second argument. Okay, so that's what we're doing here. Remember, we have two neural networks. One is the encoder and one for the decoder. So we need to create two clip gradient normal functions. Okay. So the first one is the encoder.parameters and the second one is the decoder.parameters. I repeat, parameters are the weights of your model, which is in this case the encoder and then the decoder. And the clip value is going to be supplied later on, okay, when we define the hyperparameters. So this is actually one of the input arguments to this function. Okay.